Don't worry.
Thank you, sir. Thank you.
ये Pragya and Akaksha, what is the session room meeting room? I'll ask my PhD students to attend. They're attending here and there.
Sir, this is number four, sir.
All number four. Okay, I've just
So,
sent them.
actually, you can send that link which we have given. Anyone can join that link.
Okay, okay, sure, sure. Thank you.
Yeah, directly they will enter here only.
Sure, sure, sure. So Professor Chin will start in 5 minutes.
Thank you.
It's 11:55 now. Yes.
Okay.
So Venki, you are here. I think you joined. I shared the link.
Sir, I'm here.
So can you ask our PhD scholars to join and attend the talk? I have emailed them the link. Just yes. Yes, so Professor Chin, we are on time. It's 11 o'clock here. So maybe we can start if you're ready. So I welcome all the participants and delegates to Icee 2020 hosted by Indians of Technology Delhi. And we have today our invited guest, Professor Albert Chin from NCTU Taiwan. Professor Chin received his doctorate degree in electrical engineering from University of Michigan, and then he worked with AT&T Bell Labs, then GE Research, then Texas Instruments, SPDC, and he was a he's still, I think, he's a visiting professor at NUS Singapore, and he's currently chair professor at National Chiao Tung University, Taiwan, and Professor K is a pioneer on low DC power and high K CMOS and high K flash memory, low dynamic switching power 3D IC, and high RF power symmetric MOSFETs, silicon terahertz devices, and resonant cavity photodetector. He has published more than 500 papers and more than 100 scientific reports, physics papers. Between 2017 and 19, one of his paper was highly cited as device physics of applied in device physics of applied physics letters. And he has also seven highly cited papers. His paper citation index is 55 H index, and the top tier research. He's a top tier researcher among electrical electronics engineering field in Taiwan, and he's also fellow of IEEE. And he has served as subcommittee chair and SAN arrangements chair of international IDM meetings. And he is editor of IEEE EDL, IEEE EDS Society SRC chair, and two technical committee chairs in electronic materials and compound semiconductor devices and circuits. As I have already mentioned, he's fellow IEEE and also a fellow Optical Society, Asia Pacific Academy of Materials academician. So with this, Professor Chin, I welcome you to Icee 2020 to give the invited talk. And Professor Chin will give a talk on unipolar CMOS-like logic. So I welcome Professor Chin to give a talk. So we will have 30 minutes talk from you.
Thank you for your introduction.
Yes.
Good morning, ladies and gentlemen. This is my honor to give the invited talk in such nice conference. The title of my talk is the Unipolar CMOS-like logic. My name is Albert Chin, and the co-author is my PhD student. We coming from Taiwan. Here shows the outline. The first one is introduction and motivation. Then unipolar logic with all almost design. We are going to study the VPH of we also propose a label restoring technique to recover the VT loss. Then is experiment verification. So we did the fabricate the chip and do the major. Next one will be the potential for unipolar logic. The final one is a conclusion. Here shows the introduction and the motivation. It is difficult to build the CMOS logic for MOS emerging substrate beyond the single wafer. Because they have the power involved that increase the difficulty to fabricate CMOS logic. First, considerably poor hole mobility. As we can see that most of the 3-5 compound semiconductor has very high electron mobility, but the hole mobility is even less than silicon. Besides, although the gallium nitride has close mobility with silicon, the electron mobility and the hole mobility difference are huge. So the layout size between NMOS and PMOS is huge. The next challenge is lack of PMOS transistor. For the PMOS, mobility is only one concern. The others are the dopant activity, good ohmic contact, etc. So up to now, we do not have a default device for those compound semiconductor device. Therefore, we study unified logic scheme is proposed for implementing logic functions by using a design not only includes N-mode traders without DMOS. This design is suitable for those emerging substrates other than silicon. The concept of device level unified CMOS like logic was proposed during 2011, but with little progress. And here is the first circuit level experimental implementation based on 40 nanometer silicon technology. Another advantage is that if we have all N-mode transistors without the form DMOS, the fabrication complexity can be much simplified. Only N-mode transistors are needed. Here shows the comparison for conventional regular CMOS, and this is the layout. And here shows the configuration and the layout. So you can see huge difference between the NMOS and the PMOS. While in addition to much synchronize the process, the Uniprot scheme also saves area by eliminating P-well, N-well isolation and share the source ramp. So we can share the source ramp without the acceleration, so the area can be much. Next up, it will be unified logic with all NMOS design. We are going to discuss the VT loss part and our proposed level restoring technique to recover the VT loss part. Here shows the unified logic with all NMOS design. This is a conventional unified logic with the diffusion mode, load, NMOS. These architectures can be proposed about a half century ago, but as you know, the major problem of the diffusion mode NMOS is the high DC liquid current. So thus it was replaced by the conventional CMOS. We have NMOS, CMOS here, to decrease the DC current over here. But the major problem is that this is a uniform CMOS-like logic with all NMOS. So here we use a pair of pull up and pull down NMOS transistors. Those are controlled by the clock and the clock bar. So the DC current can be as low as a CMOS. But the problem is that we have VT loss here. So what is the VT loss problem? The pull-up NMOS only operate in either saturation or cut-off mode. And the saturation current of this pull-up NMOS is given by the well-known equation. V clock bar minus V out minus VTH. So when the clock bar becomes 1, all the V equals VDD, the pull-up NMOS is expected to recharge the output. Then the drain current gradually reduces to 0 as the output charge toward the VTH, toward the VDD minus VTH, which means the V out for logic 1 cannot be higher than VDD minus VDH. So the VT loss problem causes a degraded logic 1, not because the more severe as the supply voltage decrease. Here is our stable restoring technique. This is the typical 2-input NAND circuit. The output of NAND circuit is connected to second stage, which will become the AND. Those NAND and AND logic made of all NMOS trained CMOS. Label restoring technique is proposed based on the existing charge pumping concept to recover the VT loss problem as we mentioned earlier. The label restorer is developed to boost up the degraded voltage of logic 1 of the output back to required voltage level by using this circuit. Here shows the timing diagram of the label restoring technique. This is a circuit as we showed in the previous slide, and here shows the clock bar VS1. VS1 is the terminal here, and the name voltage output is showing here. Set of pre-charge and diversion phases. Pre-charge and the diversion phases consists of complete computing cycle. Complete computing cycle is divided into 2 intervals. The T1 cycle, when clock equals to 0, represent the pre-charge stage, and the T2 clock equals to 1 represent the diversion stage. As we can see that the output of VS1 can only charge to VDD minus VDH, as we mentioned earlier, that is VT loss problem. However, the output of NAND output can be charged to a voltage level even larger than the VDD. Here is a comparison of the logic without the label restorer and with the label restorer. The flex curve is a clock, and the red one is a NAND. As we can see that the NAND cannot recover VDD. However, with the label restorer circuit, it's completely different. The S1 can reach as high as VDD minus VDH. The NAND already becomes a floating gate at the end of the period of T1 with voltage peaks at VDD minus VDH. This voltage level can be pushed up by S1 to slightly above the VDD as a result. So the internal node of S1 S2 of the label restorer can push up the voltage levels of output and its complement, respectively. Here we present the detailed circuit analysis during T1 cycle when clock equals to 0, and during T2 cycle when clock equals to 1. The total charge stored in the output can be obtained by voltage multiple the capacitance, which equal to this equation. Well, VS1 initial is the initial voltage, and CS of the capacitor here. During T2, the total charge can be calculated as from this equation, where the output here of VS1 will be VDD minus VDS, as we already said. However, because of the capacitor, we can increase the output here and also increase the output at the VS1. So by applying the charge conservation principle between T1 and T2, we have this equation. This term can compensate the VDH loss. That is from the circuit analysis. The next topic will be experiment verification. We increment the basic or NMOS logic and therefore restoring a network into a 40 nanometer or NMOS. And here is the result. Here shows the fabricated chip, and this is the enlargement of the chip, which we have unipolar logic and output buffer and built-in oscillator. So before applying the proposed unipolar logic to emerging substrate other than silicon, which are unfortunately currently unavailable to fabricate the unipolar logic circuit yet, we first realized the head chip using the 40 nanometer silicon technology. This is the fabricated chip. Here shows experimental measurement IV result. This is a major standby sequence that goes through the VDD of logic gate. With clock is turned off and the VDD of typical 0.9 volt, the standby power is only 10 nanowatt from the of current leakage, showing the CMOS-like low DC power consumption. This is the merit over the conventional unipolar logic with differential mode low, which suffer from large standby power. This is another experiment result. This is a waveform, measured waveform for 2 in 2 in off and not the function. As we can see that those logic are successfully demonstrated using all NMOS transistors. Here the input signal change with a path width of a nanosecond. That is generated using an inbuilt circuit application. The next topic will be the potential of unipolar logic. To fully probe the potential of unipolar logic, we have simulated the logic gate at a higher operation rate at the path width of 0.5 nanosecond. The previous video result is designed at 8 nanosecond. With post layout parasitics. This is in1, in2. This is the end function or function and not function. As we can see that the fundamental and or and not function are all successfully simulated even at a very fast 0.5 nanosecond. Here shows the post simulation power delay product, PDP, and as a function of voltage, and the dynamic power loss of an AND gate is 1 gigahertz for CMOS and unipower logic. As we can see that the slightly inferior power delay product is originated from the label restoring delay. However, the superior dynamic loss of unipower logic to CMOS is due to the lower pre-charging voltage to VDD minus VDH rather than the which is typical for the CMOS. Conclusions. First, we propose a unipolar CMOS logic for implementing logic by using design not only include the NMOS transistors. The unipolar scheme is suitable for emerging substrate using material other than silicon, like silicon carbide, gallium arsenide, indium gallium arsenide, indium arsenide, gallium nitride, etc. The success of this study has been verified by simulation and experiment measurement of basic and or not the logic implemented on 40 nanometer silicon chip. Thank you for your attention.
Thank you, Professor Chin, for excellent talk. So I would open the floor for question and answer session. Any questions from participants?
If no question, thanks for your attendance. Thanks again.
Yes. So, Professor Chin, one small query that this unipolar logic we are trying to explore to as an alternative to CMOS IC for high temperature and harsh environmental conditions, right?
Yes.
And okay, so then still in this NMOS based, all MFET based transistor logic, we are still using silicon.
We hope to use like a silicon carbide.
Silicon carbide.
Yes.
Okay, okay. Okay. Thank you so much.
Thank you. Bye-bye.
Thank you so much for the talk. So we will see our next speaker, Professor Himanshu Thapliel is already here. So Akanksha, can you check? Akanksha, you are there.
Yes, sir, I'm here, but I don't see him in the participants list yet.
Okay.
So maybe we can wait for
Yes.
5 minutes because
Sure.
we have finished before time in this talk.
Sure.
Okay, sir.
Okay, so participant, we're waiting for Professor Himanshu Thapliyal, our next speaker, who is currently a faculty member in the Department of Electrical and Computer Engineering in University of Kentucky, Lexington, Kentucky, USA. And he will give a talk on emerging technologies for energy efficient and secure Internet of Things devices, IoT devices. So Akanksha, we have emailed them all the details to all the speakers.
Sir, actually, he still is not available. I have emailed him and I'm still trying to get his contact.
Sure.
We have no choice but to wait for now.
And Professor Atmesh Srivastava is scheduled, right? At 12.
He has a schedule at 12 o'clock and he is also from US, so we also have to wait for him.
Yes. Maybe early morning.
Yes. So both of them from US, so maybe that's why.
Yes. Yes, so Professor Thapliyal.
Yes, hi. Actually,
Yes. Hi, welcome. So I should say very good morning to you. Maybe in US it's early morning, I hope.
right. Actually, yeah. So it is actually 1 a.m. here.
So,
So
I mean, you'll have sleepless night today. Anyway, so Professor Thapliyal, welcome to ICEE 2020, hosted by Indian Institute of Technology Delhi. And thank you for accepting to give an invited talk in ICEE 2020 conference. So we are on schedule. So I would, Professor Thapliyal, you can share your screen. And in the meantime, I will read your biography to the audience.
so can you see my screen now?
Yes, we can see your screen.
Just give me a minute. I will be back in a minute, and then we'll start. Just give me just 1 minute. Okay?
Sure, no problem. Please take your time. Professor Srivastava, I can see you. Maybe your video is on. So welcome to ICE 2020, Professor Srivastava. I think your talk is after Professor Thapliyal's talk. Schedule.
Yes. So I'm back,
Yes.
and
Okay. Thank you so much. So let me read your bio to the audience and participants. Now, dear participants, we have Professor Himanshu Thapliyal. He is currently associate professor and endowed Robley D. Evans Faculty Fellow with the Department of Electrical and Computer Engineering, University of Kentucky, Lexington, USA. And from 2019, he's the co-director of Cybersecurity Certification Program at University of Kentucky. He has received his doctorate degree in computer science and engineering from University of South Florida, Tampa in 2011, and where he received the Distinguished Graduate Achievement Award. And from 2012 to 2014, he worked as a designer of processor test solutions at Qualcomm, where he received the Qualcomm World Star Award for contributions to memory built-in self-tests. And his bio is very long, so I would shorten it, that he has authored over 150 publications, including over 40 journal articles, and he has received numerous best paper awards at various international conferences and forums. So, Professor Thaplia, without wasting much time, I welcome you to ICE 2020 to give an invited talk. And Professor Thaplia will give a talk on emerging technologies. I think I can see your talk title, Energy Recovery, Computing for Low Energy and Secure IoT Devices. Thank you so much, Professor Thaplia. I welcome
Yeah.
you. Can start. Yes.
Thank you very much, and it's a great honor to give a talk here, and I like to thank the organizers. So we'll start the talk, and after that, I will be happy to take any questions from the audience. So
30 minutes, maybe 25 to 30 minutes. Okay.
sure. Okay. So if you see in the current scenario, you know that everybody is talking about Internet of Things, and IoT is a big revolution now, right? So as can be evident from this slide, there is a significant growth of Internet of Things devices, and it is expected that there will be billions.
Professor Thapli, I'm sorry to interrupt. Can you make it the presentation mode, full screen, so that we can see?
Okay, sure.
Thank you so much. Not yet, but I think we will see soon.
Let me know if you cannot, because I'm sharing. Can you see it now or not?
No, the screen is small. I think I can see
Okay.
slide 25 slide modes.
Setting from hold on, actually,
Sure. Please take your time.
Get slides. How about
Get slide. I see the same screen. We have now it's fine.
now? It's fine. Okay.
Looks fine.
Okay, very good. Okay, so great. So if you can see from this slide that there are Internet of Things devices, and there is significant growth of an IoT devices. They have application on the wearable device, smart home, location intelligence, and several of the other applications. So now when you want to design Internet of Things devices, there are some constraints. The constraints are the example of this energy efficiency and the security, right? So as can be evident from this slide. So these are major challenges because most of these IoT devices, as you can see from this particular slide, are battery operated. And so you need to design some circuit which are energy efficient. And since nowadays you can say these IoT devices can be also vulnerable to different type of like the hardware or the malware based attacks. There could be also some sort of side channel attack. The side channel attacks can be of type like power analysis based attack, which I will talk today. Then it can be also possible some such as electromagnetic based attacks. There are also issues related to IC piracy, IC counterfeiting, and hardware trojan detection. So the issue with these IoT devices that you can see that the cyber attacks are threat to the reliability, safety, consumer personal information. So, and moreover, sometimes you can say when a company is designing, they are putting a lot of efforts and the time to develop this intellectual property. So people can steal your intellectual properties. In that case, it can also result in some sort of revenue loss. So there are major challenges. This is one such example of side channel attack. It is called a differential and correlation based power analysis attack. The underlying idea, suppose you can think in this case, there is a cryptographic device. And suppose as an attacker, what you can do is that you can measure the power consumption of the device. And so as you can see from this right hand side, there could be possible attack that is input data. And then you can also, in which this input data you are putting to the actual device. And then on that other side, you can also make some sort of a hypothetical model. And those two models you can correlate through some statistical analysis. And based on that, you can identify the key of your cryptographic circuit. So it is called a power analysis based attacks. And this can fall into the differential or the correlation based power analysis based attack, right? So people can measure the power, and based on that, they can decipher your key. So this is one example which will try to show that the methods that how we can overcome that. So this is some of the like the differential power analysis based countermeasures. The countermeasures can be a type of algorithmic level or also can be like the circuit design level. And today we'll talk about the circuit design approaches. So you can think in this case, this is a very nice slide. Actually, it is from the paper number 1. This is published in 2018. It is a paper by the team from Intel. And so what they have shown is that if you look into this slide, that there can be different types of circuit design approaches for developing chips which are resilient against these power analysis based attacks. But the interesting thing, you can say that whenever you plan to make your circuit resilience, there is some overhead, and that overhead is usually in terms of increase in power consumption, because you are trying to make your circuit resilience against these attacks. And these all these results are based on actual silicon prototyping. And so you can see that one of the method that I'm going to talk in this talk today, it is called energy recovery computing, and that is shown in the green color in this table. And this can be evident from this one that only energy recovery computing is the method which make the circuit resilience against this power analysis based attack while reducing the power consumption. So you have to think in this case, the other techniques provide the security, but they do increase the power consumption, while the adiabatic logic or the energy recovery computing that I'm going to talk today is the only method which will increase the resilience of your circuit against the side channel attacks while further reducing the power consumption. So that is the key contribution that I like to talk about today. So this is the talk overview. I will talk about this energy recovery logic for low power and DP resistant circuit. Then I will talk about slightly about this FinFET and tunnel FET based energy recovery logic families. Then I will show some example of this in the actual benchmark circuit of a lightweight cryptographic algorithm. Then I will talk about that how can you develop some sort of this energy recovery based physically unclonable functions, and also how can you detect some sort of hardware Trojan detection, and what are the challenges that are there to make these things practically for the actual adoption for the industry. So what are the challenges there? So this is the talk that I'm going to talk about today. So this is the underlying idea of the energy recovery logic. So if you can see in this case, in this circuit, you can say that normally you have a constant VDD that is driving your circuit. But the type of logic family that we are talking about, it is called energy recovery logic. And here you can think in this case, you have a clock. So it's a V clock. And this V clock, you can think in this case is going to go up and then it's going to fall down. So this is represented by the seesaw diagram. You can think in this case when the clock goes from 0 to VDD and then it remains constant. So what happened during this time? The energy is supplied from this clock. So in this case, you can say when you have a constant VDD, but in this case, you have a power clock. And when the clock goes up, the energy has to be supplied from this clock source to your output node that is being represented by this F and F. Because it's a dual rail logic, so you have both the F as well as complement function F bar available. So the energy goes to these nodes. But if you look into the conventional CMOS, whenever you flip from 1 to 0, you dissipate that energy to the ground. So that's why there is some dissipation in the conventional CMOS. In the adiabatic logic, this clock again after some time start falling down. That is represented in this again by this seesaw structure, in which you can say that this energy has to be recovered from your output nodes again back to your clock source. So in that case, instead of dissipating the energy, we are recycling the energy back to our power clock source. So that's why these circuits are low power in nature and there is less dissipation. This is another example is being illustrated here. So you can say in this case that whenever this power clock source goes from 0 to VDD, there is some transition time that is being represented by T, and the power dissipation in these type of circuit, these adiabatic circuits, is given by E dissipation RC by T C VDD square, right? So now you can think in this case, if T goes to infinity, then your power dissipation is almost going to be 0, right? Because it is in the denominator. Of course, if you make T bigger and bigger, then your circuit is going to work slow and slow. So the underlying idea is that we can make the T substantially big, because in IoT applications, our circuit usually run at, let's say, at megahertz, for example, 12.5 megahertz, 50 megahertz, or 100 megahertz. So we have a lot of leverage because we can make this T bigger. And by making this T bigger, we can reduce the power dissipation. So that is the underlying idea that why these adiabatic circuits are comparatively consume low energy compared to the standard CMOS-based approaches. So now what you can think in this case, this is an example, illustrative example of a circuit. Here we have represented a CMOS-based inverter. And this is the another approach, that is the figure number A represent the CMOS-based inverter. Figure number B represent a countermeasure that is developed based on CMOS, and the C represent the adiabatic or the energy recovery logic based countermeasure that we have developed. So now if you see in figure A, as you transition from like say from 0 to 1, 1 to 1, and 1 to 0, you can say that the red color is represent your current profile. So now you can see that the current profile is non-uniform in the conventional CMOS case, so people can understand that what is going in your circuit, because you can say that suddenly you have low peak, suddenly the peak goes very high, around 1600 microampere in the standard CMOS. Now, so that is the way the people can attack your circuit, because they can identify the power profile, and based on the power profile, they can understand what is going in your circuit. So the figure B shows that you can say that now the power profile has become uniform, and they have used dual rail logic, but you see the peak current has gone to 142 microampere. So in other words, you can say that your power dissipation is going to get increased in the conventional CMOS way if you try to make it secure against this attack. While the figure C, you can say that we use adiabatic logic, and the underlying idea is that the peak current has suppressed. The peak current is only 1.8 microampere in our case. That's why this circuit will have very, very low power dissipations. And you can see that the current profile is also uniform, and that will make this circuit resilient against these power analysis-based attacks. So the underlying idea is that if you can use adiabatic logic, so we are solving two things. First of all, you can say that this energy consumption, and the second is the vulnerability, right? So if you use this adiabatic logic or the energy recovery logic, what you can do, it can provide you the security that is being shown in the log, and it can also increase the battery life of your circuit. So in other words, you can design circuit which have very, very low power in nature and also secure against this attack, which could have applications in the domain of IoT, wearables, smart home, smart healthcare. So several applications in the smart consumer electronics. So those are the areas we are talking about. So what we did, we proposed one of the logic style. It's called symmetric pass gate adiabatic logic. This is being illustrated in this example here. So if you see in this picture, in between this F and F bar represent the Boolean function that you can implement. And in between the circuit represent like the charge recovery circuit. That is a cross couple inverter that has been shown here. And the top, there is a V clock, that is, you can say it is a four phase clock that we are going to talk about, right? This is being represented in this figure. For example, you can say it's a T1, T2, T3, T4, and T5. So this is a 4-phase clocking scheme that we are using here. It's a trapezoidal waveform. So without going into too much detail, the underlying idea is that you can use some of these transistors. For example, M1, M2 can be used for recovering the energy from the load capacitors, and M3 and M4 can be used for performing the logic operation. So this M3 and M4 can be replaced by a logic function. Suppose you want to implement an XOR gate, XNOR gate, or whatever logic function you want to implement. So that's how these logic gates can be designed. Now, this is an illustrative waveform of an XOR gate through this logic. You can see that based on the transitions, like for example, your input is transitioning from 0, 0 to 0, 1 to 1, 0 to 1, 1. You can see that your current profile is very uniform. So that's why these circuits are resilient against these power analysis based side channel attacks, because you can see that irrespective of the input transitions, your current profile is always very uniform. So now what you can do in this case, so now you have get an idea that a high level idea that how can you design some circuit. So now this is an example of AES cryptographic algorithm, and it has different components. So you can see that is being shown in the red color. The S box that is being represented here is the major source of the power consumption. It is consuming almost 75% of the power consumption of the AES algorithm. That is represented like a one round of that algorithm. So now the underlying idea is that we try to develop some customized hardware for this like this SBox circuit using the proposed approach. And these are some of the results that we discussed. So these are some of the results that you can see in this case. So this is the proposed method, and you can say in this case we are able to have substantial low energy. You can say the energy dissipation in our case is 0.8 to 5 picojoule. These are mostly the cadence-based simulation results, actually. Okay, so this is 0.8.2 per picojoule. So you can say that it has substantially low energy dissipation compared to the standard CMOS-based approaches. So now what we can see that now the issue is that, of course, by using this energy recovery method, you can save the dynamic power but what about the leakage power? So the underlying idea is that you can use these emerging devices, and some of the emerging devices you can use is, for example, FinFET or the tunnel FET, and these devices, or it can be future devices. For example, some of our work are recently using this, which I may not be able to talk today, but we are also using some sort of spintronic based circuit for saving this leakage power and trying to merge with this energy recovery logic. So the underlying idea is that you can save the dynamic power by using this adiabatic logic technique, and you can save the leakage power by using these low leakage emerging devices. And these are example of the FinFET and the tunnel FET, right? That I'm going to show you some result. So this is an illustrative example of, we run some simulation on tunnel FET, and you can say that this is the 20 nanometer technology for the tunnel FET. We have run the simulations. And so you can say that current is in microampere. So you can say the peak current is very much suppressed. And as I showed to you, the current profile is very uniform for the XOR gate, right? Now what we did after that, we tried to implement, this is another, because we are talking about this IoT devices. We took an algorithm, it is called a present AT algorithm. It is designed for IoT application because it is lightweight in nature. So it has substantially low gate count. So we tried to implement this present AT algorithm by using the proposed adiabatic logic style. So I'm going to show you some of the results. So these are some of the results of this technology at the simulation at 12.5 megahertz, because we are targeting the IoT application. So that's why we run our simulation at 12.5 megahertz. So you can say this is the standard CMOS based approach that has been represented by 1. 2 is the adiabatic CMOS. Now, this adiabatic CMOS can be implemented in FinFET, that is represented by 3. This adiabatic, again, this logic style can be also implemented in tunnel FET, that is represented by 4. So you can say that as you go for these low leakage devices, you will have better numbers in terms of energy dissipation and the power dissipation. You can say the average energy is substantially low if you implement in tunnel FET, and again, this average energy is also substantially low compared to the CMOS based and the FinFET based approaches. So that is the underlying idea. Now, once you implement these devices, now what we can do, we can, again, as I showed you, if you remember that, we can put some sort of statistical analysis. So we perform a DP attack, that is differential power based attack, to identify the key. And the figure number A represents the CMOS circuit, and you can say in the CMOS based circuit, after nearly 5,000 measurements, you are able to decipher the key. So the attacker is able to reveal the key because by doing some sort of statistical analysis that is being shown here, because the correlation coefficient, you can see this red color is shown the key. The key is 6, and it has come out after nearly 5233 measurements. Okay. While if you try to implement this circuit using some sort of adiabatic logic style, the figure B represents with tunnel FET, you can see that here the correlation coefficient is almost like 0.2, 0.4, 0.6, the scale, while in the tunnel FET, you can say it is 0.2. So it is almost 10 to power minus 3, almost less correlation coefficient in these emerging technologies of merging with this adiabatic logic. And you can say that key is hidden even after almost like 40,000 traces. And it is all simulations, and you can say there is no noise. So it is more accurate in that nature. So you can say even after 40,000 simulation, the key is hidden. So that's why you can say that by using this merging of this adiabatic logic and with emerging technologies, you can develop circuits which are low power, while as well as resilience against these differential power analysis based attacks. So now now we develop the cryptographic hardware. Now we can develop some sort of other hardware security primitives. And one such hardware security primitive is called physically unclonable function. So physically unclonable function is more like, you can say, the DNA of us. For example, let's say each one of us has a DNA, and our DNA is unique. That makes us distinguish from one person to the other person. Similarly, when you fabricate some chip, because of the process variation, one chip is going to behave differently compared to other chip. So you can say that is the challenges, and this is variability sensitivity circuit, and then you have the response. So that is being illustrated here. So you develop a physically unclonable function that can be a circuit that you can develop. So if you pass a challenge to puff1 and puff2, you can see that because of the process variation, they won't be same. That's why you can uniquely identify one device compared to the other device. So these types of puffs have several applications. For example, they can be used for key generation. They can be used for identifying the counterfeit devices. So they have so much application actually. Some of my students are also looking into applying this and developing software protocols for this puff for automotive security. So this is one illustrative example at the circuit level. So what we did, you can say this is more like, you can say it is similar to like an SRAM cell-based structure. So it's a cross-coupled structure, but instead of the constant VDD, you have the power clock. And because of this threshold variations, you can say this R and R bar, you don't know where it will settle. R can be 1 or R bar can be 0 also, based on this threshold value. So based on that, we created like a unique, like 128-bit number, and that can be a unique identity. We call it a puff. So this simulation was done at 45 nanometer technology, and the puff is usually measured in terms of some metrics, for example, uniformity, reliability, and all those things. And so we got very, very low numbers. And this is an illustrative example of our this adiabatic puff compared to other approaches. You can say at 45 nanometer, at 1 volt around that, the uniqueness of this puff is very strong, and the power consumption of this puff is also very low. So you can say you can develop again this low power security primitive called puff by using these energy recovery based methods. And these are some of the references. If you want to look into more details, this work has been published in ACM Journal of Emerging Technologies in 2020. This is a very recent work actually. Now what you can also look into that case, that sometimes people may have malicious intention, right? So if they have the malicious intention, they can put some sort of hardware Trojan or some, you can say, hardware virus in your circuit, right? This is a illustrative example. They can have very negative consequences. So as we discussed to you that by using these some sort of circuit techniques, adiabatic logic scale circuit techniques, your power profile is going to be uniform. So that is being illustrated in the part A in the up one. And suppose you have some hardware Trojan trigger, and it triggers and it tries to perform some malfunction. So what will happen in this case? The power profile will become non-uniform. That is being illustrated in this B figure. So you can say by identifying, or now you're doing the reverse engineering in that way, because previously you are using the uniform power consumption to make your circuit secure. Now we know that our circuit should have uniform power consumption, and if somebody has put some sort of malicious hardware in that, we are saying that the power profile is not going to be uniform, and by using that method you can identify the malicious hardware. That's what this the summary of this slide, and that's why this adiabatic logic techniques can be used for this hardware Trojan detection. Now, of course, I told you so many nice things about these technologies, but of course, nothing is free in this world, right? There are some challenges. So what are the challenges to make these technologies a widely adoption technologies for the industry application? So that's what we are looking right now. So as I discussed with you that previously, we are not using a constant VDD, we are using a power clock in this case. So what we need in order to derive this or run this adiabatic core, we need a power clock generator, right? So when you will be actually evaluating the power consumption of these devices, you need to also consider the power efficiency or the energy efficiency of this clock generator. If your clock generator is not good, it is dissipating a lot of energy, then how much nice circuit you are going to design, it has zero value, right? Because it's going to consume low power. So some of the challenges right now is that how can you design this power clock generator which is energy efficient in nature? These are some of the challenges that my group are addressing right now. We are looking into efficient power clock generators. Now, another underlying idea is that right now, because most of these technologies are dual rail in nature, so that's why let's say if somebody who is accustomed of writing very long codes, it is difficult to map these types of circuit to this, like say example, to these type of technologies because they are dual rail. Further, they operate in phases. So there are some challenges. These are illustrated in this case. For example, you can have the floor planning, placement, clock tree synthesis, signal routing. So in other words, right now we need to also develop some sort of CAD flow so that this industry standard tools such as Cadence can be, or the Synopsys or other like mental graphics tools can be directly deployed in that, because right now all of our work is based on customized circuit. We hand draw everything by using Cadence, we lay out everything. So that is a lot of work. So we need to automate this process. In other words, we need to develop some standard cell libraries, some automatic tools. And again, as I told you, we also need to develop some sort of automated routing techniques, right? For example, so what are the challenges and how we are trying to address that? So now we initially in our study, we validated that it is going to work. So now we are trying to make it more and more practical. So one of the underlying idea that we plan to use, I will illustrate you in this case. So instead of the multi-phase scheme, we plan to use the two-phase clocking scheme. So in the two-phase clocking scheme, the circuit is very simple because in this case, it is more like you have the VDD and the ground. So what in this case, instead of VDD and the ground, we will have the clock and the clock bar. Where the clock bar is almost like the ground type of node. So that's what we are trying to look into this case, because now we don't have to write multiple clock. We have to just route the signal similar like how you write power and the ground in your conventional VLSI circuit. So that's why we are looking into the two-phase clocking scheme. And because of that, the interconnects area reduces. You have to route less number of clocks. And so this is some of the underlying idea that we are trying to explore right now. So this is one illustrative study that we did right now. This is the, as I discussed with you, this is the V clock and the V clock bar that you can consider.
Professor Thaplial, 5 minutes max.
Okay, sure.
Thank you
so
so
now,
much.
yes, thank you. So what we can see in this case, by using this type of things, we have this power clock generator also integrated, and you can see that almost at low frequencies, we are having the almost like 80% energy saving compared to standard CMOS. As the frequency increases, the power dissipation and the energy numbers are getting worse, but they are still around 20%. So right now, my research group is looking into how to make them more energy efficient around, like say example, 50 megahertz, 100 megahertz. So these are some of the future research direction we are looking. Okay. So in conclusion, this energy recovery computing is a promising candidate to implement hardware security primitives for IoT devices. And it is specifically useful for those areas where you have power constraint. In other words, which are battery operated, and you need to develop some sort of low power solution as well as which are secure in nature. So these are some of the promising applications. So with that, I like to conclude my talk, and I will happy to take any questions that you may have.
Thank you so much, Professor Thaplial. So the hall is open for question and answer session.
Hello, sir. Thank you for your talk. I'd like to ask you that as we go for excessive scaling of supply voltage to reduce the dynamic power, we also build parts for high leakage currents. So as you mentioned that you are maintaining the dynamic power by reducing the leakage, we could take care of that. But what happens to the speed of the circuit while we take care of the dissipation?
Yes, that's a very good question actually. Okay, so the point is this one, right? Because see, because as I first of all I discussed with you, you need to identify the target application. So right now we are looking into the low frequency application, right? For example, 12.5 megahertz, 25 megahertz, where the speed is not much of a constraint. Okay. However, if you need to look into high speed such as 1 gigahertz, 500 megahertz, then there are also solutions which I did not discuss, but you have to do more circuit innovation there, and actually it's an open research area.
Okay.
Yeah.
So
It's a-
in that way, we can always work on how to achieve a satisfactory trade-off between the energy and the operating frequency.
Oh, absolutely. Actually, that's again, it's again, so let's think in this case, right? On if you take like y-axis in which you can put some sort of a graph of leakage, dynamic, power dissipation, and this is adiabatic technique. So they have there also like an adiabatic loss. Okay. So if you plot that graph, you will see that at one frequency you will have the minimum of both. In other words, you have the minimum leakage power, minimum dynamic power. So if you run the simulation, you will identify a one frequency which is the optimum frequency for operation.
Okay. So, sir,
Yeah.
which tool are you using Cadence for simulating all these circuits?
Yeah, all these are based on cadence simulations. Yeah.
Okay. Thank you.
Yes. So, more questions from the audience? Yeah. So, Professor Thaplial, so you said that these are low frequency IoT applications, and we have this energy recovery from the output node.
Right.
And so then there are some adiabatic losses. So can you throw some light on these adiabatic losses that we expect?
Yes. So usually you can think in this case, there are two type of things. For example, adiabatic losses depend on the frequency, right? Okay.
Right.
So the lower the frequency you will run, the for example, this adiabatic losses is dependent on RC by T, the denominator T, right? So in other words, if you make the transition time bigger and bigger, you can have say example the lower adiabatic losses. So in other words, the slower you will run, the lesser adiabatic loss you will have, right? Okay. But there is another constraint that is of also importance is that because you want to make sure that whenever you turn on your device, the potential difference between the two nodes is almost zero. Okay. That is not always possible. Okay. Because a circuit design technique, sometimes you can say you need some sort of a like threshold voltage to turn on your device, right? Okay.
Right.
Times you cannot minimize those types of losses. So you can say because of the what is called implicit properties of this circuit, right? For example, for CMOS, you need at least a voltage greater than VTS to turn on your device, right? Okay.
Right.
So these are some of the challenges. So, but however, you can still try to intelligently design your circuit such that these losses can be minimized, right? But again, it's so what I'm trying to convey to you, ideally it could be the zero power dissipation because of this properties of these devices, it's not possible to have the complete zero power dissipation, right? Yeah.
Okay. Thank you so much. So, if there are no further questions, let's thank Professor Thaplial for the excellent talk and illuminating us about these energy efficient and secure IoT devices, R&D. So, thank you, Professor Thaplial, for the talk. And now we will welcome. We have our next speaker, Professor Atmesh Srivastava. And Professor Atmesh Srivastava. So, are you ready now?
Yeah, hi. Can you hear me all right?
Yes. So you can share your screen. In the meantime, I will read your bio to the audience.
Okay, perfect.
Yes, so Professor Atmesh Srivastava is currently an assistant professor with the Electrical and Computer Engineering Department at Northeastern University, Boston, Massachusetts, US, and he has authored and co-authored more than 40 research papers and is the inventor of 18 granted US patents with several patents pending. He obtained his PhD from University of Virginia and worked for Texas Instruments in Bangalore and Dallas. He also worked for an IoT startup, Everactive, in Virginia, where he led the development of self-powered wake-up radios. After Everactive, he joined Northeastern University to pursue his academic career. So, Professor Atmesh Srivastava, welcome to ICEE 2020, hosted by Indian Institute of Technology, Delhi. And the hall is open for your talk on chip design of ultra-low power sensor. Yes.
Hi, can everyone hear me all right?
Yes, we can hear your voice.
Okay, thank you so much for the introduction and thank you for the invitation. So I'm going to talk about like this general theme about chip design for ultra low power sensors, and like what is going on and what it entails to like design these really low power sensors that are going into IoT devices, as well as some of them are also finding application in biomedical space. So, I mean, as Professor Thaplial was introducing this IoT context, just to like emphasize a little bit more, they're everywhere, and like smart electronics is getting integrated into like everyday objects, and the challenge is how do you go about like providing energy for these devices, and as you might have experienced, like the more devices you have, the less you feel like charging them. Like you cannot like keep on connecting hundreds of IoT devices to battery to wall to take power. And so like how do you make them self-powered or energy autonomous? So we're going to talk a little bit about that. To give you a context, this is a slightly old slide, but like by 2018, this was 50 billion. The number has increased significantly. Number of connected devices to the internet. And in this context, a biomedical application is also very, very interesting, because in biomedical application as well, the kind of challenges that you see in IoT space is also like present. So you want like sensors that are continuously monitoring the health of a person. Sometimes they are implantable, so you cannot like replace batteries for them. So they're also like how do you meet the energy needs is also very, very important. One of the things in this context is also very interesting, which is a pacemaker. Initially, like when pacemakers were being deployed, usual battery life was like 10 years, but a lot of people are outliving the life of pacemakers. So additional surgery, complicated surgery has to be performed at an older age just because the battery needs to be replaced. So batteries are kind of like in IoT space is a big problem, and how do you go about making them autonomous? Also, some of the other challenges in IoT space include, which is like which is not and which is there in conventional computing, but it becomes even more challenging in IoT space. And as Professor Thaplial was setting light on them, like hardware security, side channel leakage, Trojan insertion. Because these devices are having much limited compute capability, security infrastructure is almost very limited always. So it also becomes very challenging to meet their security needs. So we'll briefly discuss a little bit about them as well. But like a lot of this is going to be high level. So if you have any questions, please let me know. So chip design for ultra low power sensors. So conventional, like this is like an old paper on which I was one of the co-authors in early papers in Journal of Solid State Circuits. So this is a very simple architecture. If you're sensing for IoT or even for like biomedical application, typically you have like an analog front end AFE, and you acquire the signal and then you digitize it, analog to digital converter, and then it will go through the different stages of computing in digital. There might be a microcontroller. You may need to store it. Sometimes you can compute and store. You can store, compute, and then store. And then there would be a power management. This is part of the digital system where like you kind of change the power supply level so that digitally controlled, so that you meet the optimal energy efficiency point. Typically, after computing, you will have a RF to remotely communicate with a base station or something that is acting like a base station. For example, like a phone might be an example of that. And then you have all sorts of infrastructure circuits, which I call it infrastructure circuits, because you need these to like perform basic functionality such as power delivery. So power management would be one. Energy needs through energy harvesting or batteries, clock sources. These are like ultra low power systems, but you still need to maintain a clock. So this is like a very basic high level architecture of ultra low power chip. Sometimes also known, they are also called SoCs. but in like in like a conventional definition, the compute capability is rather limited, and that is also because they are catering to very specific applications. So some of the challenge. So as you could see, as the computing is happening from a sensing point of view, you have analog front end, analog to digital converters. So at each stage, conventional design approaches, which has been traditional, in the sense like the way these things were perceived from say a application platform in mobile phones, or microprocessors, microcontrollers, system on chip, things like that. That approach usually does not apply when you're looking for ultra low power sensors, and that is because power consumption requirement is often very low, very stringent. So as you can see here, this was in 2013, and the overall system was designed with 19 microwatt. Okay, so the DC power consumption, an average power consumption of the whole chip was 19 microwatt. So when you have that kind of power budget, you have to look into everything that is out there, and how do you go about managing energy. So part of this talk would be about that. So so just to give you an idea, this is a self-powered sensors energy flow, how the energy is acquired and how it is being used, and this was part of a paper that we wrote in TCAS1, transaction circuit and system one, a few years ago, 2017. And we detailed how energy is consumed in a sensor, and what are the points where you need to optimize to make sure that you have a very well optimized system or usage of energy. So you have ambient source, which can be solar or thermoelectric generator, RF, etc. You harvest energy using energy harvesting unit. You store it on a capacitor or a battery, also represented here using a capacitor. And then once the energy is stored, you use it to generate different power supplies. And then these power supplies are used for system processing and communication. So as as a student of physics, you see that there are multiple stages in which the energy is flowing, right? The first stage is the ambient source itself, which is solar or thermoelectric generator, and then we use an energy harvesting circuit to harvest that energy. So there is one step change of energy, then another step which is some kind of solar to some kind of physical activity, temperature difference or solar or RF, etc., to an electrical energy form stored on a capacitor. And then after that, another stage is the power management, which is electrical to electrical, and that generates different power supplies for system processing and communication. So that, as you can see, there are 2 or 3 steps before the energy is actually being used. There are losses associated with it, and so when you go about designing these systems, you have to be careful about some of the steps. So you want to harvest whatever is available. When you're talking about energy harvesting, you have to make sure that the harvesting efficiency is very good. There are different variants of design that you can use, but you have to be careful what works really well. And then you have to look at this is storage on a capacitor or in a battery. You want to make sure that all the energy that is available should be used before the system turns off. So that's an important consideration here, and we did some work on that. And that is to make sure that you are utilizing everything that is stored on a capacitor or a battery. And then finally, the final step is the power management. Power management has different power delivery circuits like low drop out regulators, DC-DC converters, switched capacitor converters. So how do you use it? What do you go about design? How do you go about designing those? Some work on there as well. This is to make sure that the loss in this step of energy conversion is minimized. And then finally, you have system processing and communication, big ticket item, the design choices that you make here determines how much energy you're going to save or lose for the target application that is intended, right? So radios, analog, subthreshold digital, and low power sensing. So my lab recently has some work here on a different aspect of computing, analog computing, and we have done some work on this, and I will briefly talk about that as well. So that to reduce the power consumption for system processing and communication. And finally, you have like infrastructure circuits like clock sources, reference voltages. They used to be very traditional, like often considered like the research on those topics being like settled. But as IoT space evolved, those became very, very critical. So crystal oscillators, band gap references, current references, things like that are also very critical in IoT space. So, so energy harvesting, I'll briefly talk about. There are different sources for energy harvesting. Here is an example of a DC energy harvesting. This is a thermoelectric generator. It's very simple circuit. So on the left side is an equivalent model of a thermoelectric generator. You have a thermoelectric generator as a voltage source, followed by a series resistor of Rn. And when you are harvesting energy, you want to make sure that you're maximizing the energy transfer. And everyone who has taken electrical engineering basic RC circuits, would know that the energy transfer is maximum when the equivalent resistance of the load here is equal to Rn, and that's when you will operate the energy harvester at the maximum power point. And so whatever converter you are using, it can be a switched capacitor converter based energy harvester, it can be a DC-DC converter, say a boost converter, and whatever you use, you have to make sure that these two are matched. The impedance is matched at the other end, and that's when you will harvest the maximum energy. So this is just to give you an example. This is the maximum power point, and this is where you should be operating your design. Now that is before you design, whatever you do for your energy harvesting circuit, whatever topology you choose, before that you have to make sure that you're operating at maximum power point. And then after that comes the energy harvesting circuit. So here is an example of this is giving you an example of one of the circuits that we designed and was published in JSSC 2015. And this is basically it's a thermoelectric generator, and its open circuit voltage was rated at 50 millivolt. And as you can see that when we started operating this, the average voltage was around 25 millivolts, so it was operating at its maximum power point. And it's like one of the lowest voltage boost converter circuit that is out there. It can work up to like 10 millivolts, so it meets some of the goals that we laid out. One was harvest whatever is out there, so 50 millivolt, 25 millivolts, these are very low voltages to harvest energy from. And then and then also operate at maximum power point. So we are also operating at maximum power point. So efficiency numbers are also very good for medium range voltages, like 300 millivolt. We have 84% efficiency. So this is an example of a DC energy harvesting circuit. And similarly, so this is one of the projects that is going on in my lab is a RF energy harvesting. So I mean, it's an application of RF energy harvesting, and this is basically trying to operate like a neural implant, where you can inject a lot of neural implants into brain and then sense it, or at least stimulate particular area of the brain. And so for that, you cannot use a battery because their sizes are going to be bigger, and then also you need to replace them because even for rechargeable batteries, they have a certain lifetime. So we need to provide as RF energy harvesting, because that's one of the means where you can send energy through RF media, and the brain, the implantable device would be harvesting that energy. So we did this recently. We did this chip. So what we did was, so in RF design, you have to make sure that when you're sending input, sending energy, there needs to be a matching, and oftentimes this matching network was off chip, so you get good performance. But we ensured that we make sure that this was on chip, and so you can see here, this is the chip micrograph of the RF energy harvester. And it has two inductors, small inductors, and then there's a small capacitor that completes the matching network. So once the system is matched, then it is followed by a rectifier design. So we are in the process of publishing, so I haven't provided a lot of details about the rectifier design, but some numbers are provided here. So this rectifier is like, I think it has been doing really, really good with respect to like, on-chip rectifier with matching network topologies are concerned. And here you can see that when you sweep the load, it's around 100K. You would see like, maximum efficiency of around like 38% is what we've seen. Although 38% looks like, it's not that great, but it's one of the best numbers that is available for RF energy harvesting. And that is because, there are a lot of losses associated with RF energy harvesting. The on-chip inductors that we use are not good quality. Their quality factor is like 8, like, on off-chip inductors, for that kind of value, you can get like, 80 to 200, very, very good, and even higher, like, if you use some other, like, electromechanical components. So anyway, so 100K, why did we choose 100K? So 100K was the load for the neural, like, the electrode they use for stimulating. So that was the kind of like, DC load for of 100K, and that's why 100K was used for maximizing efficiency. Then moving on, so this was the energy needs. So moving on, we are going to talk a little bit about analog computing. So what has happened recently, and this is like, this is a very current and kind of like well-known phenomenon. Everyone is aware of that. So because the scaling has kind of stopped, so people have started realizing the limits of digital computing. That is that, like, I mean, scaling is no longer trivial, and you cannot predict a roadmap for certain applications just via CMOS scaling. What do I mean by that? Like, so, or what I mean by that is like, in old days when you are thinking about, say, certain kind of application that runs on a supercomputer, you can predict that, okay, 5 years to 10 years down the line, when the scaling reaches that particular process node, that computing capability would be in your like mobile phone or on your computer. That is no longer possible. I mean, the people have started predicting that it is. I mean, some of them have predicted that the scaling will end by like a certain date, and even though it has not ended, it has become very, very expensive for people who really want to do scaling, and that basically means only certain kind of applications are possible. So there are different approaches to so I mean, before I say that, like, there is still need for like enhancing compute capability, and then there are different approaches about enhancing computing capability. In-memory computing is one of them. One of the things that we are looking at is analog computing. A lot of I'm not the only one who's looking at it. A lot of people are looking at it, and it is very different. It is different from digital computing. It has, I mean, people who have like studied electronics and has historically studied electronics, would know that like in early computers were analog. So why is it coming back again? Because analog can still deliver if you're designed carefully. Also, mixed computing, like another theme is that designing certain critical parts in analog and then you interface it with digital to take advantage of both. So this particularly this analog computing theme is being used in our lab for one of the biomedical applications. So this is in conventional computing, as I was discussing, like you have analog front end, analog to digital converter, and then you digitize it, and then you do like digital filtering. And this is a very simple example of a SVM classifier built in like in digital domain, where you like divide the EEG signal into different frequency bands, and then after that take their power as like features, and then come up with an SVM classifier to detect whether a seizure is happening or not. So this was a conventional digital, and so we proposed that we will do everything in analog, and the way we went about doing this is that the critical computing task that was being done in digital was a power extraction, and so we came up with RSSI amplifier, which is basically an amplifier circuit, and you can read more details in this paper, but it's an amplifier circuit which actually gives you the log of the input signal. So so log is a representation of the power. So like, we what we did was we didn't use an AFE. We broke the signal down into different filter banks, and then we put it into RSSI amplifier. And so once that is obtained, then it would divide the signal into different power, different frequency band, and then each frequency band will have its own power, and then we will train a model, and then we do the SVM classifier for that. So this was NSF. This our sponsor for this project is NSF, and we show you a conceptual architecture. This was like, this is a bunch of filter banks, RSSI, analog extraction, and then saying whether there's a seizure or not. And there will be some other infrastructure circuits like memory, power, etc., which is not discussed in detail right now. So this is the output with a conventional. This is the output of a seizure detection for different subjects using Boston Children's Hospital database. And what we saw was that our classification accuracy was competitive, and in fact, in some cases, better than conventional approaches. This is all using analog computing. So the results were very, very encouraging, and we are in the process of publishing this. So that was part of like how you can go about developing an analog computing system. And then I'll briefly talk about hardware security. So hardware security is also a very important aspect of IoT devices. And as well as like biomedical implants or biomedical devices. So the main challenge in this space is power, and power. When I say power, it's not just like like what it takes to like do the certain compute activity, but like in general, like what is the DC power. So as Professor Thaplial was explaining, physically unclonable functions, PUF, is something that we have also worked on. And this is purely coming from analog domain. So this is in some of the conventional approach. Some of the approaches for PUF design includes like bit cell in memory and like ring oscillator. So we approached it from a conventional analog design, and what we used was the native mismatch between two transistors, like just two transistors, not like a bit cell, not like a ring oscillator, but just between two transistors, and then amplifying them to get a digital output. So if typically because of some device mismatch, one transistor will not be similar to the other, and they might differ by a small amount. But even when they differ by a small amount, we can extract that as a digital output, and then and get the signal out. So each chip, so as you can see over here, they are like, it is talking about 16-bit, but then you can have 8 in parallel and do 128. So each chip will have, different value of this, like, this bit cell, like, each chip will have a different value because, they are purely random in nature, why the mismatch is caused. And we exploit like analog layout techniques to make sure that actually the mismatch between them is purely random. So and then it is followed by an amplifier which is completely compensated. So whatever comes out is the mismatch between these two transistors, or like any pair that you choose. And one of the main important criteria for these kind of circuits is that they need to have like very uniform distribution, meaning that say equal number of bits will have 1 and 0, and like as you can see over here, there are like output voltages that are like separated by them by like a huge margin, noise margin, where like there is no value. And on the other side, if you convert it into purely digital, almost equal amount of bits are 0 and 1. And so now if you look at like how many bits are 1 in a 16-bit key, and then you can like have 8 more, and then that is 128. And you see like it is purely uniform, and the number of ones, it's purely normal here, and then autocorrelation was 0.98. So it was also, these are also very good numbers. So, and the next topic that that is something that my group has worked on is correlation power attack. It was introduced in the last talk as well. So basically, when you have any cipher like AES or other ciphers that you can think about, when you send a key, it has a very strong. It is computationally secure. They say when you try to break it using conventional means or brute force technique, it doesn't break. But what people have figured out because of the hardware design that although it is computationally secure, but if you look at some other side channels, power being one of them, if you start looking at the power consumption, then they would show certain kind of correlation which can be exploited to break a key. So the number of attempts it take to break so-called computationally secure cipher is much lower when side channel leakages are considered. Okay, so here's just giving you an example, you have n ciphertext coming out and you're just observing and correlating it with your attempt of a key, you're attempting some key and what you're seeing, and then if you look at just the power consumption corresponding to that particular key and getting computed, you would start seeing that there is a correlation here. Just to illustrate the example, you would see high and low and something like that, the changes in the power consumption. So that's one of the ways to break ciphers, power attack, differential power attack, correlation power attack, etc. And the way they do it is before they add a voltage source, they will put like a resistor, and then they will observe and they will keep feeding the ciphertext. This is like a very popular paper in 1998 by Kucher, and showed how power attacks can be used to break the key. So and this is another one of my collaborators, Professor Yancy Face. He has done a lot of work on side channel attacks, and this is from her lab. Basically, there are two examples. One is for FPGA. They're observing power consumption in FPGA, and then they showed correlation for byte 12, and similarly you can obtain for different bytes. And the other one is from Intel Atom, and they also showed correlation there as well. Relatively quickly, I think this one was with 100 power traces, and this one was like 500 or something. I don't remember on top of my head. So my group actually, because we have done a lot of work on power delivery circuits, we look into these things from power perspective, power delivery design. So this is an example of a switched capacitor circuit that we built. So in order to prevent leakage of your cipher going out, as Professor Taplial was mentioning, it is to not let the switching pattern leak outside. Basically, that's that's the general idea. If at the observation point, which is outside, if you are constantly seeing a DC current value or fixed current value, then there is no leakage. Of course, you cannot have an equalized or ECL kind of logic, because the power consumption will be so high. So one approach was discussed in the previous talk. Our approach is to make sure that before this power is before the power is extracted from outside world, off chip world, always an equalized charge is drawn, or always the same amount of current is drawn. So you kind of you can think about certain kind of averaging. If you kind of average it, you cannot see the leakage. The way we do it is basically in this example, there is a switched capacitor circuit that is being considered, and what we do is basically before we connect switched capacitor which is drawing charge from outside world, we equalize this charge and make sure that that charge is that charge is kind of recycled in certain way. So we are in the process of publishing this idea as well. And you can see over here, this was simulation, but if you look at the energy drawn from outside world, or the current or the power, it's each switching cycle it draws equal amount of power, and consequently, if you look at correlation, there was no correlation. Okay. So that is a little bit on this on the PME designed for side channel leakage prevention. But also important is that these converters are very efficient, so making sure that the losses are maintained, are kept.
So Srivastava, 5 minutes maximum.
Okay. So I'm actually completing my talk.
Thank you so much. Yes.
So, and then there are other infrastructure circuits such as crystal oscillator, very important because you have to maintain time. So you want to make sure that you have like a really low power crystal oscillator. So this was in 2016 we published in a 1 nanowatt crystal oscillator, like a circuit that maintains the time but consumes just 1 nanowatt as the measurement results. And then band gap reference. Band gap reference, why is it used? It is used to maintain a meter. Band gap is like a voltage reference. It's like a meter, a scale that you use to do other activity on the chip. And so you need to maintain this as well. Particularly for power delivery circuits, you need like a reference voltage. So we did this in ISSCC 2015. This was switched capacitor converter based DC band gap reference, and it's a very cool design. It works at 500 millivolt and consumes very low power, 32 nanowatt. And then when you apply a lot of these ideas, you will find that the energy saved would be like 4 times at high power consumption and over 70 times at lower power consumption because of the design constraints. And one of the chips that we later on did was is shown on the left, and this chip's average power consumption was reduced to 6 microwatt. It was published in 2015 ISSCC. So to summarize, we talked about energy harvesting, RF energy harvesting, and DC energy harvesting. We talked about analog computing as an alternate to digital computing, which can save significant amount of power because analog makes use of the entire computing, entire voltage and current range for a transistor. So the compute per unit transistor and per unit transistor and per unit power is very high compute capability. Sorry about that. And then we talked a little bit about hardware security challenges and briefly discussed other infrastructure circuits. Some of the other projects going on, Wake Up Radio that I didn't talk about is very interesting. In the scope of COVID-19, we have a SpO2 project going on, which is used for sensing the oxygen saturation, ultra low power sensing again. And then hardware security, I haven't talked about analog Trojan. We recently published a TVLSI paper on analog Trojan, which is also very, very interesting. So opportunities, I just wanted to take this opportunity to also discuss, advertise, there are always opportunities in my lab, participate in chip design, build real system, validate them, and apply them for real world problems. Hardware for AI is one of the topic. Hardware security is another one. IoT devices and self-powered systems are another one. So with that, I will conclude my talk. Thank you so much. And I would be happy to take any question that you may have.
Thank you, Professor Srivastava, for the excellent talk. So hall is open for question answer session.
Hello, Atmesh, this is very nice talk. I have a question for you actually, for example, regarding your energy harvester, right?
Mm-hmm.
So just to get an idea, so let's say when you have the rectifier and you finally, this energy harvester circuit will be running some circuit, right? For example, an IoT circuit or whatever, right? Okay.
Mm-hmm.
So how much of the energy is in dissipated of rectifier, in percentage?
So in this, so the one that we did recently, so here we are seeing 38% efficiency. So so basically, it's so in this case, inductor is also kind of very lossy. Okay, so the rectifier itself, you can design. Some people, people have made claims about 40% to 80%. Sometimes people also say 80% rectifier. Usually it is just for one load. And the reason is that you have switching loss associated with it and conduction loss associated with it. So they balance out for a given load. So if your load at the output is small, then switching loss might be more, the RF that RF power that you're taking to switch these diodes, that would be more. And if your load is very high, then conduction loss starts dominating. So it's kind of like a balance, as you can see in this plot. like balanced. So rectifier itself can be a little bit more efficient for a given load, but then matching networks losses are also play a role. The reflection also plays a role. Like whatever is, you may not be able to at all frequency you may not be able to match it properly. We did a good job matching it at 1 GHz, but quality factor of the inductor was like 8. So I think it was almost 25% was lost in the inductor, and then remaining out of 62, if I say 37 was lost in the rectifier before it went out.
This is the on-chip inductor, right? This is on-chip.
Yes, on chip.
So what is the range? This is nano. What is the range actually? What is the around?
I think it's 2 nanohenry each, so 4 nanohenry inductor. And we have to take care of a little bit of bond wire parasitic, basically, because bond wire, you need to bond wire. This chip was actually, you can see it's inside a chip, so we didn't cut it, so we have a little bit longer bond wire on one side. But yeah, this was not bonded out. Because of that, and because of that project for implantable application, we had to see its performance on chip without a bond wire, without taking it out on a board, etc.
Thank you.
Yes, any more questions? Yes, please go.
Yes, sir. Thank you for your talk, sir. This is just a general question asking how well these energy harvesting sensor systems go with the harsh environment. I mean, what effect does temperature have on these energy harvesting sensor systems?
So depends on application. For example, generally speaking, the circuits themselves, they would, for example, these rectifiers here, they would behave differently, at for example, okay. There are the depending on how they are biased, because it's a lot of things going on. So suppose if you are, say, if you're harvesting 0 dBm, which is higher amount of power, then these typically diodes will operate more likely than not. They may operate in actually regular saturation region, and then their I drive actually drops at higher temperature. So the efficiency would. But if you're harvesting lower energy, then they might be operating near threshold or sub-threshold, and their conductivity increases with temperature. Okay, so they would become a little bit more efficient. So that kind of trade-off happens. But there are other factors that might also play a role. The inductor would become a little bit more lossy, and so this is for RF. For solar cells, I would say if you're using a DC-DC converter, inductor-based DC-DC converter, you would see very little difference with temperature, because the efficiency is largely determined by the inductor and the current that is flowing through the inductor. The losses, conduction loss would increase, but maybe the switching loss would drop or something like that.
Okay, sir. Thank you.
Yes, so any more questions? So, Professor Srivastava, a very small question. So, when we are speaking about this hardware security of ULP IoT, then there was some talk on mismatch amplitude, the mismatch between transistors that can be amplified, right?
Yes.
So, this mismatch parameter is your threshold voltage or on current or off current. So, basically, which parameters we deal with in transistor, MOS transistor?
We deal with difference in I drive. No threshold. You can say that it is a slight. If you translate it, it will translate into slightly different, slight difference in threshold voltage. If you take a DC equivalent, so it would. You can say that it's a threshold voltage difference. But essentially, when you make two transistors, their length might be slightly. These are min-sized transistors. So their length might be slightly different, their width might be slightly different, their doping might be slightly different. So,
Okay.
so basically, yeah. So that's But yes, threshold voltage difference would say, but they are biased in threshold. Yeah.
So when we take the random pair of these transistors, what should the sample size for some accuracy when you say analog mismatch techniques to make these mismatch randomized? So there should be a statistical sample size that these many mismatch pairs we should take.
Oh, how much we did? Yeah. So we have a chip coming back. Actually, the chip is back. We will be measuring it. But this was done on simulation, right? I think we used like 2000. Yeah, 2000. You can see 2000 samples is 2000.
Okay. Thank you. Yes. So any more questions? If not, let's thank Professor Srivastava for an outstanding and illuminating talk. And on behalf of Icee 2020 organizing committee, I thank Professor Srivastava for accepting and giving excellent invited talk. So now next we have, thank you, Professor Srivastava. So next we have, I think, one oral presentation by PhD scholar, Ms. Icee, right? Icee from IIT Delhi. Are you ready, Icee?
Yes, sir. Good afternoon, sir.
Yes, good afternoon. Please share your presentation.
Okay, sir.
So Arthi is going to give a talk on her research on modeling of 180 nanometer RF bulk and SOI planar MOSFETs using industry standard DC model. Yes, please go ahead. And you have 15 minutes as scheduled.
Okay, sir. Thank you so much, sir.
Yes.
Good afternoon, everyone. Myself, Aarti Rathi. I'm a research scholar in electrical engineering at IIT Delhi under Professor Abhishek Dikshit. I'm going to present on modeling of 180 nanometer RF bulk and SOI planar MOSFETs using industry standard VC models. In this presentation, I will be discussing motivation behind doing this work and its importance in introduction section, followed by the device description which I have used for this purpose, approach and related results and discussion, and finally what are the observations and conclusion drawn. So starting with it, CMOS technology is appearing as a boon for RF technology in terms of integration, power, cost and speed. As using this technology, RF front-end modules, digital circuits, other low frequency analog circuits can also be integrated on a single chip, thus making a system on chip so that we can have everything on a single chip. But with increasing demand of high speed and miniaturization, we need to do scaling. But like that, with something good, there are other issues also. Like with short channels, with short channel devices, we face other issues like short channel effects. So in order to tackle those short channel effects, various technological changes in structure have also been incorporated, and one of them is silicon on insulator. So silicon and insulator devices provide strong immunity against short channel effects, radiation. If we see in terms of reliability also, they are more better than bulk devices. After the devices we have, then we need a compact model for predictive simulation at circuit level. Also, they offer fast and reliable simulations at complex circuits, and later we can use those circuits for our application. In our work, we have used ring oscillator and LNA. For this work, we have used Semiconductor Laboratories wafer, that is of SEL Chandigarh. We have used bulk and SOI NFET and PFETs of two. We have used devices of two channel lengths, that is of 10 micrometer and 180 nanometer with varying width. So initially for the comparison of performance of SOI and bulk devices, DC characteristics of P and NFETs are initially compared. So if we see in figure 1A, B and C, here we have compared for NFETs for bulk and SOI for the comparison, and in the figure 1D, E and F, performance of PFET of bulk and SOI devices are compared. And after comparison, we have seen that the ITP, that is on to off current ratio, is better for SOI devices than of the bulk, and other characteristics have also been seen which are better in case of SOI devices as compared to the bulk devices. So for the compact model extraction of bulk devices, we start with DC parameter extraction first, followed by the RF parameter extraction. Here in figure 2A and B, For this is for the 10 micrometer channel and device. For different body biases, VBS 0, minus 0.9 and minus 1.8 volt, we have correlated the IDVG characteristics for different drain biases. That is for 0.1 and 1.8, and it has been done in two steps. First, we have done it for the low drain bias by extracting different parameters related to low field mobility and other scattering parameters, and later we did it for high drain biases by extracting parameters like saturation velocity, PSAT, VSAT, and later at the final step we correlated IDVD characteristics for different gate to source voltage by extracting double parameters and transconductance parameters also. In the previous slide, transfer and output characteristics were seen fitting properly. So derivative of those transfer and output characteristics are also fitted are also correlated properly, and it can be seen in figure in figure 3a and b, where the derivative of IDVG at low drain bias, and in figure b at high drain bias. For the all the three body biases have been correlated properly, and for the transconductance also we have correlated the data well. After the correlation for long channel devices, moving to the 180 nanometer N and P FETs devices for channel length 180 nanometer, IDVG, IDVDs for both PFET and NFET at different drain biases, that is at low drain bias, at high drain bias, in IDVD for varying gate to source voltages. We have correlated the data properly, and its perfectness shows that the model is accurately capturing all the effects in every regime. After finishing or after extracting the DC parameters, we have extracted the RF parameters by correlating output conductance, transconductance, gate to source, gate to drain, and drain to source capacitance along with the current gain also. And we have extracted these parameters, these are figure of merits, conductance, transconductance, and everything from the S parameter measurement. In the plots, we can see a reasonable fit between the measured data that has been shown with the blue color data, blue colored, and the simulated results are shown by the red or orange color. This one. So with all these extracted parameters, for DC and along with RF, we have extracted a compact model for bulk 180 nanometer device. So our first task of extracting compact model for 180 nanometer bulk devices have been completed here. So moving towards the SOI devices, we used BCM SOI model for parameter extraction. Using the same method, that extracting parameters at long channel and then moving towards the short channel devices. Here in this slide, characteristics have been shown, IDVG and IDVD for low and high drain biases, and their derivative have also been shown fitting properly by extracting different parameters. Actually initially the geometry independent parameters have been extracted by correlating capacitance and capacitance versus voltage characteristic, which I'll be showing in the next slide. And after that, the next task was to fit IDVG at low drain bias, that is shown by the blue data, and later at high drain bias, that is shown by the red data, and later the its derivatives and IDVD scores. After the long channel device, after the long channel device, 180 nanometer channel length device, here for N and P FETs both are correlated at different body biases, at different biases, 0.1 and 1.8 volt. Measure data is correlating with the simulated one. That the thing which I was telling in the previous slide, that is for the extraction of geometry independent parameters, which is extracted by correlating the capacitance versus voltage, which is done in both bulk and SOI devices, and later moving to short channel to long channel device, and then fitting the short channel devices also. So if we have to make use of the model for non-linearities also, we correlate N and P FETs up to the second derivative also, first GM and its second derivative to It helps us in the analysis of nonlinearities, discontinuity, and distortion in RF devices and circuits, which cannot be just investigated, or we cannot study it by just analyzing or seeing the results of IDVG characteristics. If we see that this slide is repeated, but it has its own importance. We have presented that DC and RF parameters are extracted for bulk devices, but we do not have access to RF SOI device. And since SOI FETs and bulk FETs have been fabricated using similar P cell, so we have made a simplification and assumed that all the parasitics that exist between the metal lines and the device will be the same for both bulk and SOI FETs. So this helped us in assuming that the sub-circuit RF model sub-circuit which we have extracted in case of bulk RF FETs, we have used that RF sub-circuit for SOI FETs. So for SOI FETs, what we did a coupling. First we extracted the parameters from DC BCM SOI model by fitting it properly, and later using the RF sub-circuit which was used for the RF bulb, and use it for the PCM SOI. So here a coupling methodology we adopted. And the simulate, as we do not have hardware data, so here we can see that the data the result shown by the yellow one is just the simulated one by the SOI model. The blue one is for is the data of BSIM, is the hardware data for BSIM for bulk devices. Red one is for the simulated data of BSIM bulk, and yellow one is the simulated data of BSIM SOI. So in this way, we have extracted two RF compact models, and using those two compact models, we simulated two circuits. We can simulate any circuit, but we prefer to choose these two circuits, LNA and ring oscillator. So in order to compare the performance of these circuits using bulk and SOI devices, we have used the same circuit for ring oscillator and LNA in case of both bulk and SOI devices. So devices with SOI FETs are better in performance, and so is their circuit, which can be seen in terms of noise figure and maximum oscillation frequency. So if we see in figure 10A, for maximum frequency or maximum oscillation frequency for the SOI devices is much larger than that as compared with the bulk devices. And same when we see the noise figure in figure 10B, the blue one represented by bulk devices is higher in case of bulk devices, and lower in SOI devices, stating that it is better in case of bulk SOI devices. So in the concluding slide, I'll say the parameters are extracted for scalable DC and RF models of bulk and SOI MOSFETs using industry standard models, so they can be used anywhere. The model shows a high degree of correlation across geometries, bias, and frequencies, and this has been extracted up to the second derivative. We can use these compact models. Any circuit can be simulated, and the performance can be compared. This technology is made in India, so it is also having a different different approach and usefulness. This PDA can be used for further design and simulation of analog and mixed signal RF products of national importance and other things also. Thank you.
Yes, so thank you, Arti, for the excellent talk. So the hall is open for question answer session to Arti.
Arti Rani?
Yes, sir.
The beginning slide, you have compared the transfer characteristics for both SOI and bulk.
Yes, sir.
In that I can see that SOI case the current is very high compared to how what changes some same effective width for the current high.
Yes, sir. Sir, it is a normal. Yes, sir. Sir, it is a normalized one. For the normalized effective width.
Same effective width. The current should be same or can be different for SOI.
Sir, it will be higher, na, sir.
What make changes to get higher behavior?
So can you repeat, please? Actually,
What changes results in higher current?
if we see for the RF, for in the first, in this one A, B, and C for the NFETs, the bulk FETs shown by this blue one and the SOI with this one, we can clearly see that the even after comparing in the another sheets, we have seen that the ratio is higher and other parameters in terms of reliability also we have seen that this is better one after comparing.
The physics, that's what I understood that SOI is a short channel effect immunity will win. Case of drive current improve how for the same effective and it should be same effect.
Yes, sir. But the drive current is higher na in case of SOI.
What physics might be behind?
Yeah, so your VT, so mobility is also high in case of, okay, you're asking for physics. So here as parasitics are less in case of SOI devices, so it will be also impacting the drive current also.
Parasitic might be mainly due to RF capacitance. So, in terms of drive current, DC drive current.
So,
In terms of DC, means this is drive current is DC analysis, right?
yes, sir.
DC analysis use only capacitance.
So VT,
Parasitic
say, mhm. So,
you consider same effective from same dimension, similar dimension for both bulk and gate, right?
yes, sir.
Speed and everything.
Okay, so any other questions from the audience? Yes, so Arthi, so a few basic questions. So what is the safety if you extrapolate that AC current gain
Yes,
frequency performance?
yes,
What is
sir.
the unity gain cutoff frequency for your devices?
So for our devices, it was around 40 gigahertz. It was coming around that.
Okay, and on can you go to previous slide, please? Slide eight. Next slide. Next slide eight, number eight.
Okay, slide number 8. Okay.
Here, so in that CV characterization, so if you look at
Yes,
the
sir.
accumulation side, there is a mismatch, right, between the model and data. So can you comment on that mismatch?
It actually say we compared with the other one also, but so we considered that it may be some measurement artifact. So
Okay. So the data is in hardware data, right?
yes,
Experimental
data.
data.
Yes, sir.
And what is the small signal frequency for these measurements that you use for the static small signal frequency for your
So
model?
some model. So we have so we from the megahertz range to gigahertz range up to 10 gigahertz.
Okay. And that noise figure plot, there was a noise figure plot. I don't remember the slide number
Yes, sir.
28 or
I'll
something.
move it to this.
Yes. So in this noise figure, so can you enlighten us about what are the noises which are dominant below 2 gigahertz and what are the noises which are affecting above 3 gigahertz? Because if I see that you said curve.
Okay, sir. So at the low this so it was also dependent on the biases and the inductor also because here this data this one data is in we have used any arbitrary values of inductance and resistance here. There was no matching, so just there was a kind of simulation only for the comparison purpose only. So
Okay.
here we didn't try to match anything, neither impedance matching at the input impedance matching, neither there was any output impedance matching. We just simulated for the sake of comparison purpose.
So the depending about around the minima point where the noise figure is dropping, right?
Yes,
So
sir.
some kind of noise is getting added up, right, within the amplifier.
Yes, sir.
So what kind of noise are dominant in that valley region?
Okay, here you are asking.
Yes. Well, what happens, some signal to noise ratio, output of a signal to noise ratio input. So some noise is getting added up, getting amplified.
Yes, sir.
First frequency 2 gigahertz. This is silicon technology, right? 180
Yes, sir,
nanometer.
silicon. Yes, sir, silicon technology.
Okay, okay. No, you can find out. You can find out.
Okay, sir. Surely I'll see this, sir.
It will be a good piece of investigation. Yes. Okay.
Okay,
Thank you.
sir.
So,
Thank you so
any
much, sir.
questions to Aarti? No more questions. Then let's thank Aarti. It's a lunch break time. So we can meet at 1:30 because already we're running late because 1:30 we have, I think, fast talk by myself and after that Professor Sri Prakash Tiwari of IIT Jodhpur at 2 o'clock. So Ankur, who is going to be the host because I am the invited speaker at 1:30. Ankur, you are there?
Sir,
Yes, sir. Sir, Dr.
Thanks,
Abhishek
sir.
Srivastava will be the next
Okay.
session chair, sir.
Fine, fine. So we'll meet around 1:25, 30.
Yeah, 1:30, sir. 1:30, sir.
Oh, okay. Thank you so much.
Thank you.
So
Thank you.
all of us can gather at 1:30 for 25 minutes, 20 minutes. Thank you.
Thank you. Thank you, sir.
Hello, Dr. Kaushik. This is Abhishek here.
Hi, Professor Abhishek.
Yeah, how are you?
Fine, fine.
Yeah, all set. So, yeah, we'll begin in a minute
I can,
at
in the
1:30.
meantime, I can share my screen if you allow me.
Sure. Yeah, that is perfectly fine. Thank you.
Is my screen visible?
Yes, I can see your screen.
Oh, thank you.
Thanks. Hello everyone, welcome and very good afternoon. Let us start this session of ICEE 2020, and I'm very happy to introduce you all to our first speaker, Professor Kaushik Nayak. Professor Nayak has earned his PhD and MTech degrees in microelectronics from IIT Bombay in 2014 and 2007, and he earned his BE degree in electronics and telecommunication from Utkal University, Bhubaneswar. And since August 2015, he has been working as assistant professor in the Department of Electrical Engineering at IIT Hyderabad. And before this, He was working in nanoscale electronic device designs and modeling with IBM Semiconductor Research at Bangalore and New York. He also worked with Frontier Research Center, Tokyo Institute of Technology, Yokohama, Japan, and he also worked with Global Foundries, Singapore. His research interests include solid-state cells, mesoscopic electronic devices, physics, modeling, and carrier transport phenomenon. So I am very, happy and glad to introduce and present Dr. Kaushik Nayak for this wonderful talk. We are very excited. So, Professor Nayak, you may please take on from here.
Yes, so thank you so much, Professor Srivastava. And so let me start. So you can hear me and you can see my screen.
Yes, we can hear you and your screen is visible.
Yes, so I'll be talking on one research my PhD student Puleya is carrying out on these oxygen-terminated diamond MOS devices, which are very high wide bandgap semiconductors for extreme environment and high voltage applications. So today my talk will I will briefly tell you about the benefits of wide gap semiconductor materials, then key few examples of high voltage, high temperature applications, then what are the types of diamond semiconductor devices evolving, the H and O terminated diamond FETs, and then we'll look at the because diamond being a new wide band gap semiconductor material. I mean, we are also there is not much literature on PCAD simulation framework on diamond and its deck calibration. So my student is now currently pursuing that. So we'll be discussing that. Then I will be concluding my talk. So let's start with there is a big demand for wide bandgap semiconductors nowadays because of this extreme and harsh environmental application. Then high power electronics and power electronics also requires to go beyond silicon towards these wide bandgap semiconductors. You can see currently the popular wide bandgap semiconductor in the last 2 decades have emerged as silicon carbide, gallium nitride, the diamond is ongoing, and aluminum nitride, very wide band gap, 6.2 electron volt. The key benefits are these from device point of view. Because of wider band gap, they have a very low carrier concentration. In fact, diamond has 10 to the minus 27 per cubic centimeter at room temperature. And all these materials, because of the wider band gap, very low Ni. And that leads to very low leakage current, especially when your device is off state or you are reverse biasing and you're switching. So this junction leakage current, for example, the bipolar junctions, bipolar devices, or even in unipolar devices, you have PN junction. The junction leakage current, which is dependent on this parameter, intrinsic carrier concentration, is further reduced. Plus, because of wider band gap, they have very large generation rate. In fact, if you know that silicon has millisecond to microsecond to minutes, depending on the traps you have, but this one, you will be surprised to know diamond, because of this band gap, which is about 5.5 electron volt, 10 to the 31 years, which is more than a stable lifetime of proton or any fundamental particle that we know, which is 10 to the 26 years, more than the age of the universe. Now, another big advantage of having wide bandgap semiconductor is very high carrier saturation velocity under large electric field transport. The reason is they have large optical phonon energy. Saturation velocity is related to optical phonon energy. Especially if you look at silicon, this is 63 MeV, and diamond, it is 160 MeV. And this is the conductivity effective mass of the mobile carriers. We'll look at those features. This is just a diagram to showcase the current power devices based on silicon carbide, gallium nitride, how they're exploiting this high voltage, high frequency, and high temperature application. They are the key material and physical properties and parameters. Another good exhibit or key benefit of using wide bandgap semiconductor you will see is this a large breakdown voltage. Okay, so that again is related to this wider band gap. Plus, if you look at all these conventional device physics formulations, the two important breakdown mechanisms are avalanche, because of impact ionization of generation of carriers, and
you have Zener breakdown, which is a band-to-band tunneling. In both cases, these breakdown voltages, they scale with band gap. You have wider band gap, the breakdown voltages are also large. Then these semiconductors are also known as green semiconductors. In many foundries, they are naming them that they are thermally and chemically stable and making them well suited for electronic devices in harsh environment and high temperature applications. So currently all the wide bandgap semiconductors based on silicon carbide, gallium nitride, and many heterogeneous junctions and this emerging diamond are used in being explored for high power, high frequency, photonic, extreme environment, and high temperature applications. There are some plots that shows that the power handling capacity and operational frequency range of most of these power semiconductor devices. But this is important. So what is happening, the projected landscape for next decade to next decade, that especially in automobile sector, you will see lots of electric vehicles. Okay, there will be battery operated, plug-in battery operated hybrid, full hybrid, mild hybrid, and that may be exponential growth that we expect post-pandemic era. Then the automobile electronics will use semiconductor devices which can withstand high temperature, high power, and high voltage applications. Then you will have this emergence of wider usage of wide band gaps power semiconductor device solutions. The goal is these devices with low switching, conduction losses can also reduce the carbon footprint of your electronic gadget. And that's why they are known as also green semiconductors. And to meet increasing demand for high power systems aimed at electric vehicles, which is a boom that's coming, renewable energy, data centers, and other markets. So there is a big surge in wide gap semiconductor. In fact, when I asked Professor Chin in the morning, he said that this is silicon carbide based FX. That's the unipolar CMOS logic they were exploring at 40 nanometer node. So you can see that how many industry and many researchers are exploring these wide bandgap semiconductor research and R&D endeavors. So some of these materials, if you map for different power ranges, the current handling capabilities to high voltage handling capabilities, you can see because a wider bandgap diamond sits here. If you compare silicon carbide, we should have a bandgap between silicon and diamond somewhere between 2 point. So silicon carbide has 250 polytypes. Okay, so you have various polytypes, and you can have a tunable band gap. Then gallium nitride. So you can see the application range here. The main aim is to minimize losses. Silicon-based power devices, or even if you use all these bipolar devices, silicon-based or any Schottky diode based and all. The problem is the high conduction losses and high voltages. Then, bipolar devices also have an issue of stored charges in the quasi-neutral region. So the switching response plus the switching losses will also be high. So you want to use devices which will have less stored charges, like unipolar devices, like field effect transistors. That's one motivation of going to a diamond FETs. Now, silicon carbide, gallium nitride based devices are already being explored in all these Schottky barrier diodes and MOSFETs, which are being realized by replacing silicon. They have low switching, conduction losses, and high breakdown voltages, high temperature operation, high switching operation, because this is also very important. If you can use more unipolar devices, then the switching frequency can be enhanced. Now, the diamond is also elemental semiconductor. Okay, silicon carbide is like between silicon and diamond, hybrid, compound semiconductor, but it's elemental semiconductor. That's one big motivation. It might have some potential. That too, the CVD grown electronic grade diamond can have band gaps and impurity density, which are pretty less for electronic applications. Let's go to next. See, if you compare our standard silicon microelectronics wafer sizes, right, which are like pizza size wafer sizes, 300 millimeter, 450 millimeter, 30 centimeter, 45 centimeter. If you compare like 12-inch and bigger size chunks of single crystal wafers, the diamond technology is still old school, not to that level. So you can see using CVD, you can have a 0.5 to 3.5 inch single crystal sizes. Using high pressure, high temperature method, which is followed and copied from nature, how natural diamond forms, using that you can grow 10 to 15 millimeter size of 1 centimeter to 1.5 centimeter size single crystal diamond. Now, if you are using HPST, the defect density, dislocation density is high. If you are using single crystal CVD, then you can reduce the dislocation or defect density, making it an electronic grade semiconductor. We need 1 part per billion impurity concentration for electronic grade. Maybe this can be used for metallurgical grade, where 1 part per million impurities are allowed. So there are lots of work to be done in diamond-based microelectronics technology. Okay. What are the key features of diamond, the electronic grade CVD diamond? You can see very wider band gap. So I will just note and highlight this boxed parameter, very large breakdown field. If you look at thermal conductivity, this is in watts per centimeter Kelvin is 24. If you want to convert in per meter Kelvin, that's 2400 compared to silicon 148, close to 150 watts per meter Kelvin. You can see very high thermal conductivity. So for high power application, that's a big benefit. And so the device application benefits have been mentioned here. Carrier mobilities are high. You see, when bulk silicon with very low impurity concentration at room temperature, you can see electron and hole. To compare, is 4,500 for electrons, 3,800 for holes. And one can ask, what's the issue? Issue is, can you make mobile carriers available in conduction band and valence band easily? It's a very large band gap. And, the intrinsic carrier concentration at room temperature is then your minus 27 per cc. So that's the challenge. If you can make it available, large amount of free charge carriers in the channels, then they can exhibit very large mobility, because the electron phonon coupling is weak in diamond. The reason is divide temperature is far away from the room temperature. So you will have acoustic phonon scattering dominating beyond 400 Kelvin of temperature. But 300 to 400 Kelvin, almost they can exhibit very high velocities. Dielectric constant is a big parameter, because there are few figure of merits when you use for this high frequency, high power application, like Johnson's figure of merit, Kay's figure of merit, Baliga figure of merit, where this dielectric constant also comes into picture. So you can see Johnson's figure of merit, which is for power frequency product, which is related to high breakdown electric field and very high saturation velocity of diamond. Very large compared to silicon carbide or even gallium nitride. Key's figure of merit is also very large. Baliga's figure of merit, which is for high frequency and low frequency case, both is very large if you compare silicon, gallium nitride and silicon carbide. So this CVD electronic grade elemental diamond semiconductor, wide gap semiconductor, has lots of advantage starting from high temperature, high voltage, high power and high frequency microwave applications. Let's proceed. If you look at literature in the last 2 decades, there have been lots of devices based on diamond that has been being explored. We are focusing on unipolar devices because unipolar devices will have less stored charges compared to bipolar, and you can have lower switching losses. And then, taking advantage of wide band gap property of diamond and high mobility of carriers, we would like to exploit all the field effect transistor performance benefits. So there are some of the key from literature. So there's a few schematic that Julia has drawn here about few exhibits based on diamond semiconductors. You can have a P plus substrate and the intrinsic layer, then N layer is a pin diode. You have Schottky barrier. You can have surface channel diamond devices. We call it edge terminated surface. You can have bulk channel diamond devices. We call that O terminated diamond substrate. Okay. So this DO stands for O terminated diamond MOSFET, O terminated diamond MOSFET. This is a 2D whole gas based MOSFET. That's a hydrogenated edge terminated surface. This is very important. It has lots of potential applications, starting from a cold cathode emission to logic applications, edge terminated diamond surface, because you can have a hydrogenated electrode on the diamond. So these CH bonds, dipole layers, you can have condensation of water that is required to create this hydrogen electrode monolayer on diamond surface under laboratory conditions. Then what happens? This surface Fermi level of that hydrogen electrode, or you can say that electrochemical potential, is much lower than your diamond, which is typically p-doped diamonds are very common because of low activation energy for boron dopants. And so there is the Fermi level difference will lead to transfer of electrons from valence band to that electrochemical potential of the hydrogen surface electrode. In that process, there is a surface band bending, and you get a triangular potential well, a 2D hole gas, similar to what we see in MOSFET, silicon MOSFETs. The 2D hole gas at equilibrium. But another key feature for this is for device logic applications we are exploring, the hydrogenated diamond MOSFETs. Logic switches. Also, you can use diamond for non-volatile memory application that can be explored. We'll see the key feature why it can be used for a non-volatile memory application. One big thing, if you are using electron guns, you can get a negative electron affinity surface. The CH dipole, it actually lowers the barrier height to vacuum, and you get a negative barrier height. In fact, -1 electron volt negative electron affinity. So you can easily, if you can populate conduction band with electrons, electron can be easily emitted to vacuum. So you can make energy efficient cold cathode electron emitters. Okay, cold cathode for display technologies that can also be explored. So let's come back to this. Some key. I just want to show you a few literature from the hydrogen terminated diamond FETs. You can see you have a HPHT semi-insulating diamond substrate, then CVD grown epitaxial diamond substrate, so it's undoped layer. In the undoped diamond substrate, so you have a hydrogenated surface, then you have 2D hole gas, because in the previous slide we saw there's a 2D hole gas you can form. The problem is that 2D holes, because of this higher surface roughness scattering, boundary scattering, their mobilities are less, 50 to 300 centimeters square per volt second reported, compared to your bulk mobility of 3,800 centimeters square per volt second. Then the gate oxide is popular from technological point of view. Is this alumina glass, aluminum oxide. Then it has lots of issues. Okay, this gate stack has, because of lots of non-ideal charges, lots of issues we'll discuss. So these are the few experimental data that has been published in the last, I think, 1 decade. Lots of in IEDM every year you get one exhibit in diamond FET technology. But this is the 2014 IEDM paper. You can see for H terminated MOSFET is the output characteristics, and this is your, because this is a P channel. You can imagine for output characteristics you have to bias in the negative VDS. So this is a breakdown. This is, I think, IDS and the gate to source was a breakdown characteristic at very high VDS. You can see very large breakdown voltages. This is another literature on O terminated diamond MOSFET. That's what this my PhD scholar Pullia is pursuing for high voltage, high temperature application. So this from FAM's paper, again from IEDM 2017. You can see the HPHT substrates are semi-insulating, highly resistive. They are being used. You need an electrical insulation, right? Some kind of electrical insulation. These HPHT substrates are used. Then there's a p-doped, boron-doped diamond. Boron has lower activation energy. Still, boron's acceptor levels are about 370 milli-electron volt above EV. Not like boron in silicon, where it's just 30 to 40 MeV above EV. So it has large activation energy, but lowest among all dopants. Arsenic, if you look at nitrogen and any other group, 5 elements, N dopants, they have very large activation energy and large, energy required to ionize them. Almost like 400 MeV to 1700 MeV. So this is key characteristic you can see. Let's move to our work that we are pursuing. So we have a TCAD analysis. Just to start with, the 2D TCAD analysis has been initiated by my student Julia, and on oxygen terminated diamond MOSFET. That is my lab, EDR lab. So these to be consistent with the experimental data, especially the FAMS group we are following for our calibration. So these are all the gate to source and gate to drain dimensions you can see, and gate length 3 micron, And you have gate oxide thickness 20 nanometer, that is your aluminum oxide. It has a band gap around 7 electron volt. You have epi layer thickness, this boron doped CVD grown diamond about 230 nanometer, then epi layer boron doping is this. So they are the, when in literature you don't have much data on the TCRAD calibration framework for predictive modeling, you start with semi-classical drift diffusion transport. Because diamond has not been properly explored about its intrinsic device physics, its operation, and like silicon technology. Okay, so we start with drift diffusion, room temperature, and these are the physics models. We know that boron has large ionization energy of 370 MeV. So definitely at room temperature, you are not going to ionize all boron atoms. So what is silicon at 50 Kelvin in a say incomplete ionization, there's a freeze out zone overlapping. That is diamond at 300 Kelvin, room temperature. So the dopants are not all ionized. So that's why you have to use incomplete ionization model. Then different mobility models we have used, doping dependent impurities, because this device is bulk conduction, not the surface channel. So high field saturation, because these targeted applications are in power electronics. Then of course, there is a gate stack here that is depleting the channel to turn off the device. Also, when you reduce the gate voltage and you are accumulating the channel to turn on the device, you need E-normal mobility model. Then, of course, most common trap-induced, mid-gap trap-induced recombination generation model SRH. Then avalanche multiplication for this breakdown analysis. So he is using synopsis TCAD. Okay, these are some of the calibrated parameters to calibrate with the experimental data. You can see here. You note here this beta in Varsini equation of band gap narrowing due to temperature. Imagine this is always close to Debye temperature. We have seen Varsini equation, that is Eg0, Egt is Eg0 minus alpha T square over that beta plus T, that is always close to Debye temperature of that material. It's a large Debye temperature, but that is also a fitting parameter. You have to adjust. So this is what he has. We have calibrated our simulation parameter to experimental data of co-terminated diamond fate. You can see the CV characterization to calibrate the Moss electrostatics. That is number one. Then we'll go for on transfer characteristics. Then, knowing that from literature, that aluminum oxide and diamond interface, we have dominant donor kind of surface states. In donor surface states, you know that they occupy large density of state in the energy scale between mid-gap value and above the valence band top. And they will be very active in disrupting your CV characteristics in flat band and accumulation. They will be very weak effect during inversion. If you have an acceptor type of interface trap, they will have more effect on during inversion operation. Okay, so you can see he was exploring different kinds of distribution of those donor interface or surface states, Gaussian, exponential, level, uniform, experiment. We found that the Gaussian is pretty close to the experimental data, okay, that green one, but here you see the difference. So though Gaussian distribution of interface trap came close, but around flat band there is a mismatch. So that work is still going on. Research work is being pursuing that to model. So what is going on here? What kind of non-ideal oxide charges are present? They are causing some leakage or something and causing this difference. Now this is again to show the normalized capacitors versus CV characteristics of your core diamond Moss structure. It has three regimes in the Moss electrostatics. One is accumulation. The another one is depletion. The another one is deep depletion. It's deep depletion. Okay, that's the DC and AC non-equilibrium in silicon Moss capacitor. So in deep depletion, the reason is that simple. The thermal generation time for these minority carriers to have a channel or all these inversion layer so long. That is 10 to 31 years. So in all these CV characterization, you can never populate and create an inversion layer. The depletion charge will only be responding, then you will always have lower and lower of depletion capacitance and your Moss capacitance decreases. So this is a deep depletion. So now you can exploit this device for non-volatile memory application. You can turn it off, it stays there, some logic state, you can turn it on, some logic state. That I think still undergoing. A non-volatile memory switch can be designed out of O diamond MOS capacitor structures. Going to next. So there is some of the energy band diagrams.
Professor Nayak, sorry to interrupt you.
5 minutes.
So there are about 5 minutes, just to remind you.
I'll quickly go there. There
Yeah,
are
yeah,
bias
sure.
regimes. Okay, just you should remember in a deep depletion, the quasi-Fermi level of holes will be always above the quasi-Fermi level of electron. It's an extraction of carriers. Yeah, this is, you can see the minority carrier generation time map for various wide bandgap semiconductor. Diamond is here. Okay, this is in seconds. So 1 year is around 10^7 seconds. You can see they have 10^31 years. You can see aluminum nitride, and gallium oxide, gallium nitride, very long lifetimes. So there are some of the IDVG calibrations we have done. And this part, because of lots of epi-layer defects that we are still trying to capture, there is some mismatch. And these devices are always on at 0. So you have to turn it off. You have to apply positive bias to make them go to deep depletion because they're P-doped. And the threshold voltage, that margin between, when you turn it off to on, that is the threshold. The transition is 7 volts. So threshold voltage is 7 volt for this deep depletion diamond O MOSFET. These are some of the output characteristics, and these output characteristics exhibit a very nice transistor action. And then we are looking at high temperature operation for diamond. As I told you that beyond 400 and 500 Kelvin, the acoustic phonon scattering dominates. The on current starts reducing. So for the on to off ratio dropped from 10^8 to 10^4 beyond 550 Kelvin temperature. Now at high temperature also, because you have your band gap narrows down, then you have to apply further high VGS to deplete the channel, the bulk channel, and that's what results in ET increasing with temperature. There are also some of the work we are doing, the breakdown analysis, because it's a new semiconductor material. Diamond was never investigated as semiconductor material, the CVD grown, laboratory grown diamond. So we do not have parameters which satisfy avalanche multiplication modeling for diamond semiconductor. So Pulia is still working on all this breakdown modeling. From his calibrated deck, he found minus 270 volt, which is different from the minus 200 volt for one experimental exhibit by FAMS group in IDM 2017. So these are some of the impact ionization rates being reported in literature on diamond. There is wide variation. There is no consistent viewpoint. One thing they are not able to capture is the mean free path, the scattering mean free path. How does it depend on temperature for diamond? So when you use for silicon or silicon carbide, it doesn't work for diamond. So that work is going on. So there are the breakdown characteristic simulations still ongoing. And you can see one key thing is that if you increase temperature, right, your breakdown voltage should increase because the mean free path shortens. Then you have to apply large electric field within the short mean free path for the electrons to gain sufficient kinetic energy to rupture covalent bond. But here, the simulation with the existing model with the advanced TCAD tool showing with increasing temperature, breakdown voltage is decreasing, which is wrong. So still ongoing. Okay? And also there are key features in the CV characteristics and the dependence on frequency, because if you look at here, this is a deep depleted MOS capacitor HFCB. If you look at here, you cannot have inversion there. Okay, no inversion capacitance. But if you look at a very low frequency, it has been observed at high bias voltage and deep depletion. Suddenly, the semiconductor capacitance is rising, which is very odd. So we are still investigating. Why does it happen? Because at low frequency, MOS capacitor gate oxide is not leaky. You cannot have those charging of the interface traps. So CIT can be neglected. CI is not there. Inversion layer to form, you need 10^31 years. You have to wait till the end of universe. But what is causing that rise in depletion capacitance at high voltage, in deep depletion state, then suddenly going towards this at low frequency one modeling work? He's also working on this gate leakage for high frequency CV modeling. And then also, because the RC time constant for all these CV characteristics depends on the charge voltage characteristics, the substrate resistance. The substrate resistance, the epi-layer resistance is also affected by defects. That's also we are trying to capture. In conclusion, we have observed that deep depletion operation of O oxygen terminated diamond FET, which is designed for high temperature operation and high voltage application. Our simulation prediction till date has zeroed in on Gaussian distribution of interface trap, which are donor surface states, which is consistent with experimental capacitance measurement. At high device lattice temperature, current increases due to increased ionization rate of boron dopant ions. But again, the ion current degrades because of more lattice induced scattering rates. So increase plus at high temperature, there are also thermionic leakage currents through traps. That's we are still trying to capture, which also imposes a high temperature operational limit of this O diamond MOSFET. The breakdown characteristic simulation is going on because there's lots of analytical modeling needs to be done with the calibrated deck. It's just minus 270 volt, but the experimental data are very like varying a lot, about minus 700 to minus 1200 volt, like that. So existing electron and hole impact ionization coefficient models in TCAD tools are inadequate to capture breakdown characteristics of experimental oxygen terminated diamond FETs. So new breakdown model development work is also ongoing, along with gate leakage current and this CV characteristic dependence on frequency. With this, I will conclude my talk. Thank you all for your attention and attending. Yes.
Thank you, Professor Kaushik. It was really wonderful, and thanks for introducing us to this exciting and new area of diamond-based devices. So now I'll ask other participants if you have any questions. You may please ask it now. Meanwhile, Professor Kaushik, I have one question.
Yes.
So I was thinking from circuits point of view. So I saw in your curve that the voltages, gate voltages applied were very large, means minus 15 volt to plus 15 volt. So how much is the possibility that we'll see these devices in, replacing kind of existing semiconductor devices in our day-to-day electronics?
So if you are not looking for high power and high voltage applications, maybe this H terminated diamond, right? This 2D whole gas based diamond. So here you can see you can have good current channel conductivity that can be modulated at lower voltages. You can see here -2, -4, -6, and plus the device sizes also has to be reduced for low voltage operation. So in diamond, there is still the technology, the epitaxial growth and CVD growth technologies are still evolving. They have not come to a stage that we can create nanoscale diamond structures. Still diamond structures in microns or in millimeters, centimeters. So we have to apply compromise of high voltage to get some current. So whole gas is a promising device because this 2D whole gas, which is induced again using a hydrogen electrode, surface electrode, under laboratory condition of condensation of water vapor. Then what happens? This electrode is highly reactive, and the problem is if you are exposing it to some other, say humidity changes and the season changes, it's exposed. Then there are lots of foreign impurity atoms coming and sitting. They will in fact disturb surface states, and there will be formulable pinning. Many effects are there. So there are lots of challenges. But this has lots of potential, this H-terminated diamond, because recently using boron, nitrogen, oxygen vacancy combination. So they tried to create a 2D electron gas near diamond surface. Okay. So that is still being explored, recent reports. But using an enhancement and depletion mode of combination, I think using a 2D whole gas diamond FET, we can explore CMOS logic or logic switching applications. Another thing is pole cathode emission, is the negative electron affinity you get.
Yeah, I got the answer, Dr. Kaushik. Thanks. Any other question from any other participant? Okay, Professor Kaushik, thanks again. It was really a wonderful talk, and I will catch up sometime.
Sure. Thank you so much.
Yeah, thanks. Yeah, bye-bye.
Bye.
Now I'm going to introduce our next speaker, Professor Shri Prakash Tiwari, and I'm very happy to introduce him now. So Prasad Tiwari joined IIT Jodhpur in 2011, and he is working as currently as the associate professor in electrical engineering department. And before joining IIT Jodhpur, he worked as a postdoctoral fellow at Icee department at Georgia Tech, Atlanta for 3 years. And he received his PhD from electrical engineering department at IIT Bombay in 2008. During his PhD, he worked at NTU Singapore for about 7 months. And Dr. Tiwari is a senior member of IEEE. He's a Vishwesriya Young Faculty Research Fellow of MITI. And his research includes development of high performance organic FETs, sensors, and RAM devices for flexible electronics. He has published more than 95 research articles, including 48 peer-reviewed journals in very reputed forums, and ACS Applied Materials, Applied Physics Letters, IEEE Transactions on Electronic Devices. So I'm very happy and excited to present, Dr. Prasad Shri Prakash Tiwari for his talk. So Prasad Tiwari, you may please take on. And just I will, after 25 minutes, I will give a buzzer just to, as a gentle reminder. Yeah.
Yes.
Okay,
Thank you, Professor Srivastava, for introducing me. And it's kind of last talk of this session, probably. This is again the area which is not very mature. And let me share the slide. This. Okay. So I think it should be visible now.
Yes, we can see it. Thanks.
Okay. So this is, I'm just talking about one area which is flexible electronics. Obviously, when Dr. Ankur Gupta requested, I thought let us just take this challenge to talk about design and modeling aspects for OTFT. Now, this area is something where each device has different properties. And the areas like silicon where you can produce eventually whatever you want. In these devices, it's very difficult to even compare devices fabricated across the laboratories, across the industry. So that is where modeling and other aspects had been a challenging task. But then I'll just show something, it's more of results, and where I'll just highlight certain things where what could be the challenges. And obviously, the whole talk will pose a kind of a to-do list for all the modeling community, how to take care of this issue where devices are so different and then simulate these things. So let us, so I'll start with broad outline, which I'll not probably even go through in detail, but I'll just talk about transistors, what are the applications. But see, motivation of any of these areas where devices, eventually these transistors are the crucial component of any technology. And right now what we see is we keep consuming or keep buying, keep procuring, you can say systems, devices, as such, apparatus, computers, mobile phones, TV, everything. And we never worry about actually what is the, what happens to these after we use and throw it. Most of the times it's called electronic waste. And as in body, you see certain kind of blockages in the body, and then health is affected. Similarly, for Earth, if these kind of waste is not treated or taken care of well, it is a hazard to the Earth itself. So it's a global challenge. You say, what is the effect on environment? And we are actually not thinking about, we are trying to produce systems, electronic system for our comfort, but we never, most of us, the researchers, we never think about what is happening to the e-waste or mobile phones, which every 2-3 years we are throwing it away. Can we, as research community, can we even think about reducing that effect? And that is where this area came into picture. And this area is, depending on which domain you start with, if you are coming from chemistry, you say it is organic electronics because organic semiconductors are used. Electronics person can say it is flexible electronics because transistors are flexible. Somebody from bio can think about natural materials could be used, it could be biodegradable. But if the whole technology can be produced at lower temperatures, it can be flexible, it is biodegradable. Obviously, this can help us in, again, reducing the effect or impact on environment which we are talking about. And this all thing can be called as organic electronics or flexible electronics. See, but the challenge would be you always compare with silicon electronics. But then the one thing, what say thermal budget, the processes which we use in conventional VLSI technology, the temperatures sometimes go beyond even 1000 degree, and which are the thermal budget is so high, eventually it causes disruption in the whole ecosystem. But then if temperatures are much lower, say about 100 degree or so, obviously things will be much beneficial. But then to summarize the advantages, obviously this technology you aim for low cost, flexibility, process simplicity, low temperature processing, and then large area application where conventional electronics cannot be used. Obviously our group at IIT Jodhpur, we keep producing devices and keep working on device for not only transistors, but like memories and so on, and flexible substrates. And recently we again targeted slightly more also. But then this is all this group is working on flexible transistors. If you see how this area is growing as technology, if you see last 10 years, or you can say this is again coming from this trend for various areas, you say starting from photovoltaics. This is from IDTech, where you can have photovoltaic sensors, logic, memory, conductors, OLED lighting, flexible OLEDs, everything. So combined effect, if you see, which time there is a square kind of increase in the market. So there is market available for this, which is using these technologies. But as a circuit and device person, you always want to know what is happening at circuit aspect. And here in the right side, if you see, you cannot compare something speed at different voltages. So there is a term called voltage normalized frequency. Now this frequency is coming from whenever you make a transistor, obviously you want to make inverter, and then you make ring oscillators, and from that you just try to see what is the operating frequency of operation. You normalize with voltage, so you say what is the frequency per unit volt, and then you see which time that has been, and starting from 1995 up to 2020, you see this trend where this voltage normalized frequency is increasing. It means this research area is actually being strengthened and it is growing. And what you see, initially devices were fabricated on silicon or glass substrate. Then plastic substrates came into picture. And now the green electronics or biodegradability, when these things have come, one talks about devices on paper substrate, which can be cheapest possible substrate and which can be eventually biodegradable. And see, all these systems can be utilized for, when you say smart system, you talk about connected with internet or some systems which can take decisions. So obviously there you talk about transistors as well as sensors as well as interfacing circuitry. And then everything if can be printed through 3D technology, and then there can be hybrid integration. Now what is hybrid integration? There can be some components which can be taken from silicon electronics and then they can put on flexible substrate. Potential devices of this area could be transistor, resistive random access memory, sensors, batteries. Smart, when you say if it is energy autonomous, you can say it can have even printed batteries. Then solar cells and so on. So RFID for tagging particular systems. Subsystems, you can think about smart textile, where you can have cloths with electronics. There can be skin for robotics or even health monitoring. So these patches, these will be the applications. So in general, a lot of applications are there. The area which I'll be, at least the group has been focusing is circuits. And see, this I wanted to show because to again see what could be potential applications when I say monitoring or patches, e-skin. You want something which can be conformable, where silicon and the substrates where silicon related electronics are put, they are mostly rigid. So you eventually aim something like this. But then if you aim something like this, conventional way of putting electrodes cannot work. So in this, you have to, when you design this kind of systems, one has to also think about when you stretch this system or bend this system, even electrodes cannot be in linear fashion. Probably they can be spiral, or the way they can be when stretching can should not damage your system. So these are the skin-like systems which will be the eventual aim. Last, I think, 4 or 5 years, we see this 3D printing is coming into picture. Again, when you talk about prosthetics, and so if 3D printing is somehow utilized for this technology. Now, why 3D printing is very different than conventional technology? Now, conventional technology, or you can say Willis technology, where it's more of a subtractive process. So you do photolithography, you protect all the surfaces, metals, materials, and you protect the one which you want to keep it, and then other photorests you remove and then etch it away. So most of the times this is called subtractive process, where a lot of materials are used, but then you keep only certain part of material. That is subtractive process. Obviously material wastage will be there. 3D printing is such that which is called additive process. Now additive process is whatever structure you want to utilize, whatever amount of material you want to utilize, only that you print. Now that is the advantage. So eventually, if you are using less materials, obviously it is lesser effect on environment. So that longer or broad objective. But see, this technologies are used to demonstrate your circuits and so on. This is, I think, last year's Nature Communication paper, where they had done by 3D printing. So this has potential. Obviously, this is not right now coming the way we wanted. But then there are good review articles which summarize how flexible electronics could be used in broader goals of current IoT era, where you want sensors. Now, transistors, flexible or organic transistors, if you compare with conventional silicon transistors, many times a transistor cannot be used as sensor. But transistors have poor performance, and they affect easily. They are affected easily by environmental conditions. That gives them an edge to be used as sensors also. So because of adding all those things, this gives an edge for using in smart systems, flexible electronic devices. So this is something which is overall scheme of things. But then any medical related fields, if you see conventional EEG kind of systems, if you see, you take the signals, but then the arrangements you do are very different or difficult. But then there are ideas where one can think about flexible electronics to be used in much convenient manner compared to conventional ways of. So all these ideas are there, and they are already demonstrated by people. So this is from University of Minnesota, and these ideas are taken. But then here there can be array kind of structure, and that can be done by flexible electronics. And then obviously wireless transmitter and silicon, this can be rigid electronics, whereas circuits can be done by printed by flexible electronics. These kind of aims are there with this technology. And then eventually, whenever you think about ADCs or any systems, obviously you cannot do with direct fabrication technique. So you have to make a design flow. And to make a design flow, you have to also have PDKs. Now, when you fabricate a device, which is an organic device, most of the time what you get is IV characteristics. So IV characteristics, which is output to end transfer characteristics. And from those, you can make inverter, and then probably the most basic circuit people make is ring oscillator. And then there you take frequencies, you just find out overlaps and characterize various capacitances, and then you make compact device models, and then process. If you have appropriate PDK, then using conventional circuit simulation tools such as Cadence, Virtuoso, and Spice. Again, this group had shown that it can be doable, but they don't have a library for all various materials, but very old material like P3ST and other semiconductors. They had showed that this design strategy can be developed. And if you are successful to make this kind of design strategy, and if your circuits are properly designed, simulated and designed, then if you have an appropriate printer. Now, even printers, printing technology, there are various kind of printers. In this case, they have I spoken about aerosol gel printing system, but then that can be any jet printing system, that can be any roll-to-roll or graver printing system. But then this printing system will take this file and produce this circuitry on a flexible substrate. Now it looks very simple when you say this, but this task has become challenging only because there are no standard devices. Like in silicon technology, you have silicon, you know that silicon is the semiconductor, and you know all the models, what are density of states, what could be traps, what is band gap, and so on. Everything is almost fixed. In that case, any compact modeling and PDKs, those things are much easier when you think about a new technology where every group or every potential semiconductor has different properties. Every device has different aspects. So in that case, all these things are easier said than done, where you talk about a device and simply you make models. So certainly a challenge, and people are working on what could be the solution. The solution could be, until people say that these are the champion set of 2-3 materials, these are the dielectric materials, these are the gate metals, and so on, and this is the best device structure. Until that happens, no universal design strategy can be developed. So that is where, when I said this talk is more like posing a challenge to the research community rather than showing something. So that is why I'm not showing any lot of equations which are mostly based on silicon electronics. So when we say a device is fabricated, the model which we use to extract the mobility event or threshold voltage event, we use simple current equations, which are, say, saturation current equations, which is ID is half mu and C of W by L, VGS minus VT square. And then with square root ID, we try to extract field effect mobility and threshold voltage. Now, the good thing is, most of the times these models fit for a good first-hand estimation of mobility and threshold voltage. But then they are not accurate models for these devices. So obviously, when you fabricate devices, you go ahead with models because they fit in. But one basic difference with these transistors and conventional silicon transistors is enhancement mode transistors work where you have channel inversion. But for organic transistors, they work in accumulation, because there is nothing like inversion as such. So this is overall strategy. And this slide is again when I said smart systems, what could be various components and what are the aspects one can. But just simply talking about OFETs or TFTs, thin film transistors. And this just focuses on what could be semiconductors. I spoke various semiconductors. But say the person working on silicon can say polysilicon, polycrystalline silicon, or even hydrogenated amorphous silicon is there, which could be flexible. Why to go for organic semiconductors? But if you see here, this amorphous silicon, the processing temperature itself is much higher, which are not very suitable for any plastic substrates. Though the numbers what you get carrier mobility with amorphous silicon is around 1 centimeter square per volt second, whereas organic semiconductors can provide you those numbers when they are processed at much lower temperatures. And then they could be even solution processed. So that those are the advantages. And then where do you want to use it? The simplest possible use is these can be driver circuitry in the back plane of your displays. Because when OLED display have come into market, probably back plane circuitry need to be flexible transistors. So that is something which people are working on it to have these transistors with acceptable performance. So obviously, what could be acceptable performance? You want high mobility, low voltage operation, then bias stress stability and repeatability. What is bias stress stability? When you say when your display is on for longer time, now your transistor is having a fixed gate and drain voltage. Now, what if your current is decaying with time? So it means there is bias stress related degradation. So that kind of degradation need not be there. You want it to be stable. And then repeatability. If say there is a dynamic change in display, and in that case, when your device is switching on and switching off for say hundreds of cycles, then your device should not be changing its performance. Oh, these are some common structures people keep use for these devices. Again, very simple structure where depending on where you put gate and source drain, you just name these devices. So if gate is in the bottom of the semiconductor and dielectric and everything, you say bottom gate device. Then source and drain, if they are on top, you say top contact device. And combination of these both gives you name. So you say bottom gate top contact means gate is in the bottom, contacts are in the top. Similarly, top gate bottom contact means gate is in the top and your source and drain are in the bottom. So depending on which labs, which technology is suitable for which material, which device is suitable for, one chooses. But say if you want a device which is protected from ambient, you try to use top gate device. But then if you want a device which offers lesser contact resistance and better currents, maybe you will go for top contact device. So overall, if you say you want to design for high performance, now how do you design a device for high performance? So obviously, first thing you want, say, capacitance. I said current model, obviously capacitance will come into picture. So you want a high K dielectric. You want to reduce interface traps. Probably you can have a buffer layer or something between gate dielectric and semiconductor. Then, say if you are using source and drain, in conventional silicon transistors, you have source drain which are doped. And when they are doped, they are essentially the same material. So it's semiconductor, so semiconductor, you have a depletion region. Here in organic TFTs or flexible TFTs, generally this is a metal or metallic material. Now, any metallic material with semiconductor can cause a Schottky barrier if no proper matching is there of energy levels. So that also you have to think about strategies to reduce that Schottky barrier. And then obviously encapsulation can be there. So challenges are to achieve high mobility and low voltage operation to reduce contact resistance, and then operational and environmental stability you want to achieve. What is the way forward? If something doesn't work, you go for newer materials, newer dielectrics. You want to improve interfaces. See, I will not talk about, all those combinations will be there. So I'll skip many of those things. But then obviously overall design and encapsulation will be the last stage. Simply, I want to put some discussion on what is this contact barrier and energy barrier I'm talking about. So in any device, say there is a metal which is source, and then there is a semiconductor which is organic semiconductor. Now the injection happens from source to semiconductor for your device to be operated. Obviously, gate has to be enough to make a accumulation, and then this source to semiconductor injection will be there. Now, injection of electrons or holes depends on what is the level of semiconductor and what is the level of metal. So in this case, if you see first case for any p-type semiconductor, generally if you see energy bands, now in organic semiconductors, you don't say conduction band or valence band. So you just say highest occupied molecular orbital, which is corresponding to valence band, and then you say lowest unoccupied molecular orbital, which is corresponding to conduction band. Now, if you want electron injection, your metal should be matching with LUMO. If you want hole injection, your metal should be matching with HOMO. Now, for p-type semiconductors, it's very easy because generally the metals which are used, like gold, they match very well with highest occupied molecular orbital, and then carriers can be easily, holes can be easily injected from source to semiconductor. But then for any n-channel device, the problem is either you get a metal which is close to lowest unoccupied molecular orbital, or if you have a metal which is gold, then with LUMO it will just pose a very high energy barrier. So now you want some metal here, but the problem, any metal with lower work function will easily be oxidized. For example, calcium. Now calcium, it cannot stay for even a second in air. It will just, from white, it becomes in seconds black. So you cannot match this LUMO with any metal. So most of the times you have to just negotiate with a metal which is okay in ambient, a bit stable. And if, say, for example, you want to use gold only, then what will be the problem? Obviously, the barrier between LUMO and this work function will be very high. But long back, I think what we thought, many times these devices were actually working. And now what was happening, though you have a barrier between LUMO and this gold source or drain to semiconductor, but when you apply high drain voltage and also high gate voltage, many times this barrier becomes thin. And when this barrier becomes thin, rather than this fermionic or electron jumping over this barrier, it can tunnel through the barrier, and in that case you get a current. Now this current doesn't reflect like a proper output characteristics, but it just gives a S-shaped curve. See, all those strategies were there. But because of this Schottky barrier, you see a contact resistance. Now, if you see this simple structure, this contact resistance, you can say source side contact resistance and drain side contact resistance, essentially coming from Schottky barrier. You just say that is RC. Now, how do you identify a device has high contact resistance? What you do, you simply extract the mobility for devices with varying channel length. Now, devices with varying channel length, what you see, this RCH will be proportional to channel length. But since RS and RD, these are constant, for smaller channel length devices, actually because this RS and RC will be very dominant, you see extracted mobility very low. So it means when you plot this mu versus 1 by L, actually you can find that there is a device is suffering from contact resistance. And see, this equation is simply just trying to see that. And when you see this device is suffering from contact resistance, you have to extract the contact resistance. Now, how do you extract the contact resistance? You just simply say that when drain to source voltage is very small at a particular gate voltage, you just find out R on. R on is nothing but del VDS by del IDS. And R on consists of channel resistance and contact resistance both. And obviously you can write in terms of seat resistance. But then if you see this equation, R on into W is RSHL plus RCW, this gives you some equation more like Y is equal to mx plus c. Because L is something which you are varying and RCW is something which is constant. So this gives you something like Y is equal to mx plus c. Obviously, C can be calculated or extracted if you have data for various channel length and for various voltages. In that case, you can also plot this VGS versus RCW. And some of the strategies which we had used in long back to reduce this contact resistance by some graded junction, we were successful to eliminate this contact resistance. So we'll not go into details of that. Second thing is operational stability of devices. As I said, there can be two things. One is obviously this, here you see first plot where you fabricate a device and characterize for 50 times or 100 times, whatever, and see if all the characteristics are falling on the same path. Whereas second thing, you just fix the device with particular gate and drain voltage and see with time how the current is decaying. Obviously, you can normalize it, IDS-T by IDS-0, and see how it is decaying. But since there are no standards, what will you say that this is bad degradation or how many percentages? So later, I think what we thought, my first PhD students work, that let's talk something which is called T10%. Now you say that if current is less by 10%, you may not even realize that your display is slightly bad and so on. And we try to plot it and see what are T10% of for various devices, and not only the devices which we keep fabricating, but for other technologies. But this is something which I would like to add. Many times when we see this bias stress decay is very bad, but if you give a rest in between in these devices, there had been a tendency to recover this bias stress. So bias stress stability or instability is not a bad thing. If you give not a permanent damage many times, it is there is a recovery thing. But if you just consider this decay, it could be modeled, and I think long back we had tried to just simplify it, and we just found something which is IDS-T by IDS-0. We extracted some of these parameters, and we could fit in, and we could also extract what could be VTH instability with time. So these were something which we had done on those modeling aspects. But then we fabricated devices with say -3 volt operation, and we tried to, so eventually to get a good characteristic, that was the aim. We compared various semiconductors available across the world, which are considered to be the best materials, best device structures, and all those things. So we could demonstrate devices, and we could compare and show that this area has potential. Devices are falling somewhere between, or you can compare these with various thin film technologies, and they are better if you see temperature.
Professor Tiwari, sorry to interrupt you. So it's 25 minutes just to.
Okay. So next 4 minutes I'll just complete. So here, if you see, you can compare technology by benchmarking. So benchmarking, how will you do? You have to benchmark with voltage, you have to benchmark with seat resistance, mobility, and so on, and temperature. So those things we had done. Later, we found a material which is a tip pentacene, which was air stable. We worked on this a lot, fabricated a lot of flexible devices, and obviously this was solution process device. We could go up to 5 volt operation. But then now I'll say there is a strategy which is called mixing semiconductor and polymer, which we had used. Now modeling this kind of device where you do not know what is the thickness of your dielectric actually, and what is the thickness of. So now process optimization wise, we could fabricate a very good device, but how to model this device? That was the problem. Now these kind of devices, to model it, we had to try to actually put on a rigid substrate. Now even if you want to match the device in any TCAD simulation, you have to actually side by side characterize, cut the device and see if sizes are matching. Then you can do some physics based modeling, then matching, tuning, all those things you do. And then you say that you have developed a simulation framework, and with that you can try to see if temperature and other effects are can be taken care of. Those things we had done. And yeah, so obviously for each new device, as I said, we have to do those things. Say for example, this paper, we have fabricated devices which could be even stable up to 6 months and more. So a lot of promise this technology is showing. So these are devices which were fabricated on Captain tape. Now why I'm putting all this, see, nothing is, see, for all these technologies we don't have a PDK. So all these things which we aim to have some access to this whole design flow. But obviously when we make devices, we also try to see what is the performance in circuit. For example, these Captain devices, we could see whether there is a switching when you just simply put this device with a only PMOS logic. And why, as I said, NMOS is very difficult to fabricate with this. Recently, application-wise, we also try to fabricate devices with newer dielectrics, such as our biodegradable dielectrics. One was recently with gelatin, so these devices could be even used as a breath analyzer. So you simply just breathe on these devices, and what you see is they are corresponding to your breath. So now these are some benefits which this technology gives, but obviously to model properly, there a lot of equations are available in the literature, but only thing they are not suitable to what we do. And obviously we have to first champion at least one of these and then put efforts to do all the modeling and simulation and design, everything. And so this, compared to any other technology, this has additional advantage where this could be used as sensors also, these devices. And with this, I would just like to summarize that at least fabrication-wise, high-performance organic transistors could be demonstrated if you do proper optimization techniques. But then appropriate modeling, simulation, and design strategies are still lacking, and one has to take any device and properly model, make some simulation strategy. But then advantage is if all those things are done, they are designed, and if you can print these on unconventional substrates or biodegradable substrates, this could help the environment in a better way. Obviously, these will be the systems which are use and throw kind of system, or short life systems. And obviously they can be used towards robotics also because they will be conformable. And when you can produce something like e-skin, they can be something which everyone of this community is needing, kind of waiting for. So with this, I'll summarize, just acknowledge my PhD students. Obviously, there are many more who could be acknowledged, but then funding agencies and IIT Jodhpur. So with this, thank you. And now I am kind of open for any questions.
Thank you, Professor Tiwari. It was really a wonderful talk. And I personally learned a lot of things about this OTFT and flexible area. So may I request all the participants, if you have any question, then please ask.
Professor Tiwari, Kaushik here.
Yes, Kaushik.
I felt like looking at your PhD research data at IIT Bombay. I remember how this works.
Yeah.
So so I have a small question. Like I know there are in compact modeling community, there is a big issue in modeling contact resistance, especially these AM spice, P spice. They don't have proper contact resistance modeling. And so how does this seat resistance of the film, the organic thin film, or if the thickness of the film is small, it affects the channel resistance or the specific on resistance of the transistors?
That is, see, eventually. So one first mention, I think you are correct, because one of the slides was actually from my, see, this one diagram which I had tried to explain for this barrier, energy barrier, that I had created for my PhD only. So that diagram I like very much. So that I keep for N-channel transistor, that S shape.
Right.
So that slide is actually from my PhD. After that, I had done something from postdoc, and obviously it's a continuous effort. It's not. So see, the problem with all these conductors, if there are vacuum evaporated semiconductors, then you have precise control of semiconductor thickness. Precise control of semiconductor thickness. But the solution process semiconductors, see, any seat resistance and all those things are numbers we just get from equations. But because the, see, if you see across the area, they are not uniform, like TIPS pentacene. Now, TIPS pentacene doesn't give you even a smooth film. It gives something like between source and drain, it will have a crystallite, you can say not rods, it's like a structure which is connected between source and drain. Now, it's precisely telling something, so we just use equations to say this is a seat resistance, just to estimate. But even mobility, you cannot have proper models, but we rely on what current we get from the device, and then what WL we have, what VGS we have. But we expect something like accumulation happens very close to your, maybe within even 5-10 nanometer of the semiconductor. So this question itself for us, it's very difficult, but we just rely on whatever data current we get and what WL and VGS we are applying.
Right. And any this fast principle calculation to estimate these organic semiconductor and these transition metal interfaces to, I mean, are in literature or in your research group, people are working
I think
on that?
we don't actually, that is the limitation of my group have been focusing on demonstration of new devices and
Right.
just but then there were some efforts, but we couldn't carry those works actually. See, a lot of papers are there in this area, but many times I find them more of a fitting something. See, it's like semiconductor, they know that there will be traps at the interface, and then HOMO and LUMO levels, and many these are the models from conventional silicon, and available models are used. So this is something which I personally want to pursue, but then just simplify it like a Schottky barrier, and then certain other aspects we put and just try to fit in. So see, proper physics is not available still. So you don't find even a good semiconductor physics book for organic semiconductors or flexible electronics.
Right.
Each semiconductor will have different properties. Each semiconductor will have different band gap, different HOMO-LUMO, and different way of making the structure. See, some can be polycrystalline, some can be completely amorphous. Now, for amorphous semiconductor, at the interface, something else is there, but between material itself, there will be lot many grain boundaries. Now, the effect what you get outside is actually combined effect of all these grain boundaries. What is the interface? So it's an open area actually, and we want some people to explore at least these aspects. See, fabrication wise, we are very good at producing any kind of device with low voltage operation. So IV we produce now. We can produce nice IVs with very simple techniques. We don't even use now any big equipments. We use drop casting and so on. But then the problem is to match with proper physics models. That is which I think will certainly need a lot of efforts from other scientists.
Yes. I mean, I am seeing in literature that apart from these tunneling contacts to reduce contact resistance, and there can be, if one can make an infinite recombination center, I mean, I'd say infinite recombination current rather than flowing thermoionically crossing barrier or tunneling these Schottky barriers. If you make it, the certain defects or some kind of intrinsic defects, if they can create some deep level
No,
of
I think
gap.
excellent idea. See, first time I suddenly so it can be a very wonderful idea to even think of, so that you eliminate this any kind of Schottky barrier.
A new current injection mechanism, the recombination current, through that large capture cross section mid gap center, that will reduce contact resistance.
Maybe we can even discuss on this. At least I can just put this will be the semiconductor, this will be the metal, and we can put these things.
Yes. Nice. Thank you so much, Professor Tiwari. So yes.
So if there are any questions, more questions, or suggestions.
Yeah. Okay. Are there any other questions from the audience? If not, then I would like to thank Professor Tiwari one more time. Thank you, Professor Tiwari, for your wonderful talk.
Thank you so
And
much.
yeah, I think here we conclude this session. So you all please enjoy rest of your day. Okay.
Yes, thank you, Professor Srivastava, and thank you, Professor Tiwari. Nice
Yeah,
seeing
yeah.
you.
Thank you both of you. Yeah.
Okay, Professor
We'll
Nayak.
discuss. Okay.
Yeah.
Yeah.
Yes.
Bye bye.
Bye.
The poster session for device modeling symposia will happen at 3:30 p.m. today. So I request all of you to be there for the poster session. Good afternoon, all. So we are now starting with the poster presentation here. And the guideline for this is that every speaker is getting 2 minutes, 2.5 minutes at max. And the volunteers will share the screen or the poster with all of you. And if the speaker is present for the particular poster, they can speak about 1.5 minutes. And then for another half minute or 1 minute, the poster will be open for questions to the audience. So we have to complete the poster presentation, one poster presentation in at max 2.5 minutes. So I request all of you to be quick in your poster delivery. So let's start. And first poster is by Pragya Kumar Kaushik. So Pragya, you can start. Pragya, are you there? Pragya? Let me share the screen. Yes, so Pragya, you can start with your presentation.
Yeah, my name is Pragya Kumar Kaushik. I'm a PhD scholar in IIT Delhi. So here I'm going to present the impact of surface trap state on 2DEG and barrier layer conduction band in Elgin-Ganham. So originally the different growth condition leads to the different concentration and energy of the surface state. Though it is legitimate, not very much varied for a single device. So to capture the effect of the surface state, we have just varied the concentration and energy and try to look that what is the effect it's happening on the conduction band of barrier layer and 2DEG channel. So in poster you can see that in figure C, if you look at this, when a generated electric field which is start exceeding by increasing the concentration, the conduction band goes down, and when conduction band goes down, the electron will get transferred from the surface to 2DEG, and here you can see the electron transfer happening. But in between there is a hump over there, so you can see that there is a abrupt change in 2DEG concentration, and as well as in the abrupt change in the slope of the conduction band. Whereas you can when you change the energy of the surface states from, let's say, 0.2 to 1.4, so it's from shallow to deep.
Just 30 seconds for you now.
Yeah, sure. So there is a continuous variation in the 2DEG peak. So here is also you can see from the conduction band, its conduction band is continuously increasing. So what we did, try to look into it, that when we change the concentration, there is a abrupt change in the 2DEG channel as well as in the conduction band, and when we change the energy, there is a linear relation between energy of the surface state and the 2DEG channel. Thank you very much.
Yes, so this audience can ask questions if they have.
Hello, can I ask one question?
Yeah, sure.
Yes, please go ahead.
My question is, how you are changing the surface states and how it is physically related with the device? Energy of the surface states.
It's not audible. Please repeat your question.
How can you physically define the change in the energy of the surface states?
Because different devices have different surface states and their energies also. So what I try to do is I just try to capture the certain range of the carrier surface state concentration.
No, I understood. But your simulations are only for one device, right?
Yeah, it's on one device, definitely.
So within one device, the surface energy states are fixed. So what do you mean by
energy states are fixed for a certain growth conditions? So that's why certain growth condition is not defined in my case.
If the device, suppose if the device, sorry, please continue.
Yes, sure.
See, what I'm saying is, suppose the device is already fabricated, the device is fixed, so the number of surface states that will that will change depending on whether means from
what I'm trying to say, sir, is
yes.
when device is fabricated, it definitely it will fix. But what I'm saying is when device growth condition is different, then surface trap concentration and energy could be the different. So to capture those effects.
Okay. Yes, I got it.
Yes.
Okay. So now, thank you, Pragya. We can move to the next person. And the next poster is by Ram Prasad MB. Are you available?
Yes. Can I start?
Yeah, please.
Yes, please start.
Yeah. Okay. Good afternoon to all. My name is Ram Prasad. I'm from SSN College of Engineering. I'm a graduate from Electronics and Communication Engineering. So our project is on radiation and thermal study on defensive MOSFET. So basically, in our project, we are trying to improve the working conditions of MOSFET. So MOSFET devices are used in various digital circuits. First, there are many disadvantages because of the second order effects what we face in MOSFETs. So our device is going to be an hybrid version of cell box MOSFET and an SOI MOSFET. So in a cell box MOSFET, we are trying to vary the length of the cell box across the channel such that we will find a definite and optimal length where we can find reduced second order effects. So, and we are also going to perform radiation and thermal analysis because MOSFETs are going to be under radiative and many other thermal environments. We are going to perform radiation and thermal analysis to find the optimum length of the cell box length. So through our analysis, we have found out that the length of the oxide layer will be 50 nanometers from the left and right of the MOSFET, and the gap between the oxide layer will be 20 nanometers for a channel.
Ram Prasad, you have just 10 seconds now.
For a length of 50 nanometers channel. So this is our project. Thank you.
You can ask questions if any of the audience members have.
Okay, we can move further. Akansha?
Yes.
Thank you.
Thank you, Ram Prasad. So next we have S. Tyagi.
Yeah.
Are you available? Yes,
yeah.
Go ahead.
Okay, thank you. Good afternoon to all. I am Subodh Tyagi from SSPL, Delhi. Basically, this work was we have carried out to state the thickness and composition of MCT grown. MCT is mercury cadmium telluride layer grown on lattice matched cadmium zinc telluride and alternate substrates such as gallium arsenide. In this case, in the case of lattice match substrate, that is CGT, to calculate the thickness and composition is an easy task. But when it comes to the alternate substrate, since the double layer are involved, so it has become difficult to obtain the thickness of the individual layers. So we have done the matrix simulation for this, and in this case, the layer structure includes the cadmium telluride buffer layer, mercury telluride high cadmium composition layer, absorber layer, and then the passivation layer. So we have determined the thickness and composition of here in this figure. We can see that the cadmium this is the simple layer structure of MCT on cadmium zinc telluride, and this is the double or triple multi-layer structure of MCT on cadmium on gallium arsenide substrates. So we have determined the thickness of MCT with a 0.001 plus minus variation, and in case of
10 seconds.
Please mute yourself.
Now.
Some noise is coming from background.
All of the participants are requested to kindly mute their audio. Just the speaker will speak on this.
In case of cap,
please continue.
The variation is high, that is plus minus 0.1 micron, and this is due to the gradation in the cap layer. So these layers we have, these thickness we have confirmed from the SIMS experiment and SEM scanning electron microscopy experiment.
Please conclude, Mr. Tyagi.
Yes, ma'am, because we have simulated the MCT structure and we have determined the thickness using the SIMS and SEM also. The same are matching.
हाँ जब वो
Yeah,
आएगा ना उसका
done, ma'am.
पिक्चर कर दियो
Okay,
Shweta
पोस्टर तो
sir,
thank
please
you.
mute yourself, please.
हाँ बट वो आ नहीं रहा था हमारे में तो कल में सब यही तो हुआ था
Kindly mute your audio. It's a request. Any questions from the audience for Mr. Tyagi?
You use the MATLAB coding, so can you give a little bit enlightenment on that?
Yeah, please repeat. Hello.
Your topic is MATLAB simulation of thickness. So can you elaborate that what you have used means how you have used MATLAB? A little bit of elaborate on that.
Yeah, in this in this MATLAB simulation, I have used the absorption coefficient of different layers and refractive index of different layer, and temperature was almost at room temperature. And this refractive index it has dependence on wavelength, and we have determined this refractive index, which is shown over here in the figure 1.
See, these are known factors. The coefficients are from experiments, and this is a very known factor that dependence on eta. So what I'm trying to ask you is, with reference to MATLAB, what is the means how you are stating that in MATLAB simulation? I want to know in terms of coding. You got my question?
Yeah. It's basically we used a program, MATLAB program. I developed a MATLAB program in which according to the absorption in above the band gap region and below the band gap region.
Okay, Mr. Tyagi, thank you for your presentation. Let's move ahead. Next, we have PK Mohanty. Are you available? Is the speaker available?
Okay, no problem. Move ahead, Akanksha.
PK Mohanty. Okay, so we can move ahead. Next is Manisha Khurana. Manisha Khurana, are you available?
Yes.
Yes, please go ahead.
Okay. Good afternoon, everyone. I am Manisha Khurana. I am doing my PhD from University of Delhi. My work title is Optical Performance Dependence on Area of Illumination. This is basically a infrared sensor based on tunnel field effect transistor. In our previous work, we have analyzed the basic tunnel field effect transistor with germanium gate. Here, the band gap of the germanium is 0.7 electron volt. That makes the absorption coefficient, the refractive index of germanium, the real refractive index, and the imaginary refractive index make it a suitable absorber layer for infrared radiations. That infrared radiations inside the germanium helps in the generation of photovoltage similar to solar cell. That photovoltage on application of applied gate bias results in a total higher applied gate bias. So this figure 1 shows the drain current characteristics of the device. This under illumination, and here you can see that on application of infrared radiations there is a generation of optical voltage shown by the red graphs. So here
Ms. Manisha, kindly conclude your talk.
Okay, basically the conclusion of this talk is on increasing the area of illumination, as in shown in case 2, the generated optical voltage is higher. So for case 2, the drain current, the sensitivity of the device, the detectivity and the responsivity is higher due to the higher area of illumination for the fixed dimensions, physical dimensions. So this is the conclusion.
Okay, thank you. Please, if anybody has any question, please ask.
Which tool did you use for your simulations?
Yes, please repeat the question.
what tools, which software you have used for simulation?
I have used Atlas device 2D device simulator with Luminous module. This.
Okay, thank you. Thank you.
Okay, thank you, Ms. Manisha. I see that PK Mohanty has joined. Are you there? I think he again gone offline. So let's move ahead. The next poster is from Chandan Kumar Jha.
Am I audible, ma'am?
Yes, you are. Please go ahead.
Hello, everyone. I'm Chandan from IIT Delhi. I'm currently doing PhD under Dr. Abhishek Dikshit. And in this work, I have done heavy ion analysis on stacked nanosets like bulk and SOI nanosets. So when we done our SET simulations, single event transient effect simulations, we found that from figure 3 that the current transients currents maximum spike in transients current occur in bulk nanoset devices as compared to the SOI nanoset devices. Similarly, we have done our analysis with different position of heavy ion strikes, and it is also found that when heavy ion strikes on drain uh, as compared to source, then most transient current spikes occur. So it will be results as the more output state stands in different memory circuits, because if transient current spike is more, then the memory states will change instantaneously for a particular time. So we have done also our analysis with different uh, ion track radius and with different with different fin width. So when we reduce the fin width, the charge collections will be less in the nanoseed devices, in stack nanoseed devices. So it will also less affected
Chandan, please conclude your talk.
So finally, we found that from our conclusion that SOI NSFAT is more immune to the heavy ion transient as compared to the bulk NSFAT devices. Hello, thank you, everyone.
I have two-part question. Can I ask?
Yes,
Go ahead.
The first is you said that with respect to memory devices, it will be very fast. With respect to charge-based memory devices, they have a fixed response time. So how it could be instant? Can you enlighten that aspect?
Actually, when heavy ion strikes on bulk devices, actually we have done simulations only on 3D single fat devices. Memory devices is mainly comprised of many multiple fat devices. So if heavy ion strike at a particular times on nanoseeds on bulk substrate or in silicon channels, so at that times charge carriers will occur in very mammoth-thin manner. So the current spikes will be occur at the particular
Okay. So, sorry to disturb. I want to ask a second part question. Your devices is in the sub 10 nanometer region. So, in respect of quantum effect, what you have taken consideration into your simulations to analyze the quantum effect?
we have to take for quantum corrections density gradient model. So also we have considered for sub 7 nanometer devices, we have considered also the hydrodynamic models and the velocity saturations also considered in these devices.
See, velocity saturation in hydrodynamic model doesn't include the quantum confinement or use quantum effects.
For quantum effects, density gradient models is used for the quantum corrections. So we have taken also the different density of masses for our devices as reference to the other papers.
Okay, thank you, Chandan.
Yes.
Let's move ahead. Next poster
Ma'am,
is by.
Prathyush Kumar Mohanty, ma'am.
Yes, please go ahead. Hello.
Ma'am, PK Mohanty, ma'am.
Okay. Can we do this after this poster? Stay available.
Fine,
Okay.
Fine,
Yeah.
ma'am. Thank you.
Please. So this poster belongs to Atanu Purkayastha. Purkayas, are you available? Mr. Atanu? Okay, so I think we can take PK Mohanty's poster now. Mr. Mohanty, are you there?
Yes, ma'am.
You can start.
Ma'am, can I start now?
Yes, please.
Good afternoon, everyone. My name is Mohanty, and I'm a EC student from SRM of Chennai. So my research topic was estimation of inverter characteristics with 10 nanometer FinFET architectures. So in my project, we try to design a CMOS inverter using a FinFET structure in which we have a FinFET device, and the device was designed in Centaurus TCAD device simulation, in which the N-type dopant was taken as arsenic and P-type dopant we took as boron. So in the FinFET design, we used high K oxide of hafnium oxide, which dielectric constant was 23. And for all the structures, we have used the gate material of titanium nitride of work function 4.3 electron volt. So to mitigate the short channel effect in the FinFET structure, we have used three promising technologies such as spacer technology, in which silicon nitride was used as a hybrid spacer, and the silicide we have used to reduce the contact resistance between metal and the silicon substrate. So the silicide we used was nickel silicide, and we increased the source and drain pin with respect to the channel to reduce the parasitic resistance. So all these three technologies were incorporated into the device, and we designed a CMOS structure. For the CMOS analysis, we did three basic analyses such as voltage transfer characteristics analysis, noise margin analysis, and the propagation delay analysis. For the VTC analysis, the VTC curve was extracted for the proposed structure. From the figure, we can see that the RSD shows the least and the integrator shows the most ideal
Mr. Mohanty,
VTC curve.
please try to conclude.
Okay. So for the noise margin, from noise margin table, we can see that the best structure given by the integrated structure, and the RSD or the race source and drain structure shows the least desirable result. And from the time delay table, we can see that the silicide structure shows the best and that propagation delay, and the race source and drain structure shows the highest propagation delay. So overall, as a conclusion, we can tell that integrated FinFET structure exhibits the best noise margin, while the silicide FinFET structure shows the most effective delay characteristic. Thank you, sir.
Thank you, PK Mohanty. Any questions from the audience? Okay, no questions. Then let's move ahead.
Let me ask Akanksha, if you allow me.
Yes, please. Yes, please, sir.
Yes. So, what's your name? PK Mohanty, full name?
My name is Pratyush Kumar Mohanty, sir.
Okay, Pratyush, fine. So you said the silicide FinFET, and what's the other FinFET you are talking about?
Yes, sir. One is silicide FinFET, one is hybrid FinFET, and third is ray source and drain FinFET, sir.
Okay, now on all these three FinFETs, how does this access resistance to source channel compare?
Sir, can you repeat, sir?
You know, the silicide, all the silicides, right? You have
yes,
all
sir.
these three designs. In all the three designs, the access resistance to source channel and drain channel, how do they compare? Have you evaluated?
No, sir, we haven't evaluated. We have just inverter analysis, sir. That is VTC analysis, noise margin, and propagation delay, sir.
Okay, so for propagation delay, have you taken that resistance into account?
No, sir. So we just simulated the device, sir, all the three devices, and we just took the results, sir.
Okay, fine. Okay, so your, one more question. So you said noise margin, right? And this is what you have done, TCAD simulation, correct?
Yes, sir.
So have you done mixed mode simulation, inverter mixed mode simulation to calculate noise margin or SRAM bit cell simulation?
No, sir. Like, sir, this was our we thought we will do in our next step of our research was mixed mode analysis, sir.
Sure, fine, very good. Well, that's it from my side, Akanksha and Raghav.
Sir, the here time limit given to all the participants is 2 minutes for explaining the poster and 1 minute for question answer. So we have in total 3 minutes for every participant.
Sure. Okay.
Okay, sir. Let's move ahead to the next poster. Mr. Dinesh Gupta.
Yes, ma'am. I'm audible. I'm audible
Yes,
here.
you are audible. Please go ahead.
Okay. So my topic is here terahertz device designed for the size SBT under subroom temperature to the cryogenic conditions. Myself, Dinesh Gupta, presenting here. So here in this work, we have performed TCAD device analysis to investigate the performance matrices, and we have investigated the cutoff frequency and maximum oscillation frequency (Fmax). And also, we have investigated the DC current gain for the size SBT under the cryogenic conditions. So we can see in the top one, we have designed the device, and we have used the germanium mole fraction inside the base, varying from the 0 to 26% maximum value here. And we have also for our device design, we have calibrated with the experimental data in the second plot, the left one, the right one we can see here. So this is at the room temperature. No? Now, in the moving to third figure, this current versus base emitter voltage and this DC current gate, we have obtained this DC current gain at 77 Kelvin simulation, 77 Kelvin temperature. So DC current gain, we have obtained the maximum value of 12,000. So at the 77 Kelvin. Now the fourth plot we can see here, current versus base emitter voltage at the three different cryogenic temperature of 77 Kelvin, 50 Kelvin, and 41 Kelvin. We can see here, and this is while going to lower temperature, there a steep slope is coming, and both are both in the case of collector current and the base current also. Now moving to the fourth down one, gain versus frequency plot. So here we have demonstrated here.
Mr. Dinesh, please conclude.
Yes, ma'am. So in the moving to fifth one, we have obtained the frequency versus collector current, and we have achieved the peak value after this FT and Fmax. In this case, the third one is the frequency versus temperature, and we have found with the decreasing the temperature, this EFT is increasing, and Fmax is also increasing, but after 100 Kelvin is decreases because of the collector with parasitics. Now we can see the table here. We have obtained the maximum peak value of Fmax, that is called maximum oscillation frequency, 974 gigahertz at 41 Kelvin, and Fmax is FT max is FT value is increases in the 77 Kelvin, 460 gigahertz. Now I'm concluding our work. So we can say in the first we have designed our size SBT in the PNPN configuration for the terahertz electronic application, and next we have taken the advantage of band gap engineering in the base using the germanium mole fraction to achieve the high value of the DC current and high value of DC current gain up to 12,000 at 77 Kelvin temperature. Further, we have done
Thank you.
the simulation
Dinesh,
for the
please
77.
conclude, Dinesh.
Yeah, 77
We are
Kelvin
short of
temperature
time.
and 50 Kelvin and 41 Kelvin for the device performance matrices and FT Fmax values, and extracted the peak value of Fmax versus temperature here. So if we see in the table, if we aggregate both FT and Fmax, so this value is going to higher than 1.2 terahertz under cryogenic temperature. So we have achieved from room temperature to cryogenic temperature.
Please, Dinesh,
Without exposing
I
the
think
device. Thank you.
we can stop here. Okay, thank you. Is there any question from the audience? So I see that there is no question. So I thank Dinesh Gupta for the presentation. Moving ahead. Next we have Preetham Yogi. Are you available?
Yes, ma'am.
Okay, please go ahead. Yes,
Yeah.
you are audible.
So in this experiment, we have checked the impact of hot carrier injection on the TIT dose of the FinFETs. So generally people check the reliability testing on either in a HCD or a TID separately, but we expecting the effect of HCD will be more, effect of TID will be more in the stress devices because of the hot carrier for the long-term user of the devices. So because when we use the devices for the long time, so the defects profile will be changed. So we have performed this experiment in a way that first we have stressed the devices for at a higher bias for the some time for 3000 seconds, and then expose the in the gamma radiation and vice versa also, and conclude the results as we expecting the defect profile will be changed due to SCI. So the degradation due to TID will be more in the stress device compared to the fresh device. So you can see the in results in terms of VT and the ITP curve of the transistor, and the that subthreshold slope will be more in that stress device compared to the fresh device. So you can ask if have any doubt. So importance should be given to the HCD also when the people trying to find out the mission life of the space electronics and all.
Okay, thank you, Mr. Preetam Yogi. Please ask questions if you have any.
So Pritam, quick question, okay, quick answer. So this total ionization dose you are doing for gamma radiation?
Yes, sir.
Okay, and typically what is the photon energies when we talk about gamma radiation?
Sorry, sir?
Photon energies of gamma radiation. What are the range of values?
Sorry, sir. Right now I unable to recall, but we have done this at 43 megarad of silicon dose at the gamma chamber of GC1200.
Okay, and have you analyzed any oxide trap creation due to gamma radiation exposure? Non-ideal.
Not directly the defects profile, but we have expecting the defects profile in terms of the subthreshold slope and the IO increases in the devices.
Okay, so you're doing subthreshold characterization and off-current analysis, right?
Yes, sir.
So then how does that subthreshold leakage at VGS0 increases for high VDS?
Yes, sir. And that stress devices, the subthreshold slope change drastically from around 65 to 200 something.
So that means the off-current is increasing, right?
Yes, sir.
Is the
One
off-current
order
increasing?
more in compared to the fresh device degradation in the TID.
Okay, so these off-current increases due to large hot electron creation or defect creation across the junctions?
Yes, sir. The NIT increase in the interface states.
Interface states. Very good. Next. So, yeah, that's all from Akanksha and volunteers.
Thank you, sir.
Okay, thank you, Preetam Yogi. Now we'll move to the next poster. This is by Shweta Sharma. Shweta, are you available?
Yes, ma'am.
Please go ahead.
Okay. Good evening to all, and today I'll be presenting my topic, that is design and fabrication of air bridges based passive elements for low cost RF applications. So our main objectives were to first theoretically simulate using the advanced design system, that is ADS software, passive components. So, and then we also needed to study the effect of change in dimension of the air bridges on the performance of inductor. And then based on the theoretical simulations, our next motive was to fabricate experimentally these old air bridges. So we did the theoretical simulations, and our main aim was to design passive components theoretically whose self resonance frequency is greater than 40 gigahertz, so that experimentally what we achieve is at least in KU band, that is 12 gigahertz to 18 gigahertz, which is the requirement for high frequency power amplifiers. So we designed our mask using ADS only. And then as you can see, there are multiple graphs of SRS, that is SRF self-resonance frequency, function of inductance value, and with the dimensions of air bridge. So SRF was found to decrease drastically with increase in the inductance value. And then if we compare the SRF function as a function of average dimensions, we found that SRF showed only slight variations on change in the average height or width. Also, this result allows that our average dimensions can be of flexible dimensions, and it does not set any limit to that. So based on these simulations,
Ms. Shweta, please conclude.
sure, ma'am. So we experimentally fabricated air bridges using the electroplating setup, and as you can see, there is a fabrication schematic also for the air bridge based spiral inductor, and we found surface roughness versus current density graph also, and as well as thickness versus current density graph. And as you can see, we've also did the cross-sectional SEM characterization of our fabricated air bridge based inductor, and we developed multiple bridge inductor. So it is still underway, and we are going to test them soon for their value. That's all. Thank you.
Thank you, Shweta. Do we have any questions?
Sweta, what have you estimated quality factor for your this structure?
Yes, sir. We did that theoretically. In experimentally, we are under the process of measuring all the RF probing. So theoretically, I have simulated it.
And have you looked at inductive losses?
Yes, sir. I have all the thorough study.
Okay.
Everything.
And you said this will be used for KU band frequencies, right?
Yes, sir.
And you know the modern IEEE microwave band, the KU is no more used. Can you tell us which band this frequency belongs to in the modern nomenclature or IEEE classification? They have named it A, B, C, D like that.
I have not studied about it yet.
Okay. Fine. So that's it.
Okay, thank you, Shweta. Let's move ahead to the next presentation. Next poster is by Achintya Datta. Are you available? Achintya Datta, are you there? We cannot hear you. Achintya, we cannot hear you.
Hello.
Hello. Yes,
Yeah, am I
Achintya.
audible?
Yes, now you are. Please start.
Okay, thanks. So my name is Achintya Datta, and I'll be presenting our work, compact model parameter extraction using modular Q-learning for nanoscale transistor. This was done under Professor Yogesh Chauhan at Nanolab, IIT Kanpur. So we present a reinforcement learning algorithm for the extraction of compact model parameters. The compact models come in between an empirical model and a physical model, and they have these parameters which signify the various effects. And their values are normally calculated by doing multidimensional optimization across various curves such as IDVG, IDVD, first derivative, second derivative, etc. We have proposed this algorithm, and you can see the compact model equations which we have used, and this has been taken from the BSAP 4 manual. And we are attempting to extract 9 compact models, which can be seen at the bottom left corner of the screen. The algorithm which we've used, we've defined 6 reinforcement learning agents. This segregation has been done on the effect of the parameters on the IDVG and IDVD curves. So as you can see, VTH affects the point where the transconductance goes above a certain value. Similarly, UA and VSAT have a large effect on the IDVG curve. Just like that, you can see the other parameters have an effect on either the IDVD or the IDVD curve in a specific parameter in the specific current range. Now, the algorithm which we've used is a standard Q-learning algorithm with an epsilon naught, epsilon greedy algorithm to select the action. Once an action is selected, it calculates the predicted current curve using our predicted parameters. It calculates an error, which is the comparison between the ideal curve and a predicted curve. It assigns a reward based on that, and that iterates into a loop, and then it selects an action based on the previous error which it has achieved.
Achintya, please
Yeah, I'll just
conclude.
conclude. Yeah, I'll just conclude. So if you see our simulation results, the average and maximum relative errors are between 0.1 to 1%. And this was the first time in literature which was done for more than 4 parameters. The previous was only 4 parameters. We could do it for 9 parameters. You can see the worst fitting plots are shown and they have very good overlap. So in conclusion, yeah, so our algorithm reduced computation. It took interdependencies account. It optimized over both the IDVs and IDVD curves and successfully extracted parameters with maximum and average relative error to 0.1 to 1%. Thank you.
Thank you, Achintya. We are open for questions.
So Achintya, for which CMOS logic node this compact model can work?
This was used for the BSM4, which is a normal MOSFET compact model.
Planar MOSFET.
Yes.
So can it be translated for FinFET and NanoSheet platform?
Yes, sir. We are doing it for the BSM CMG model, which is for a multi-gate FET.
Okay.
We are doing that.
And when we turn on a transistor, right? When we turn on a transistor beyond VT, suddenly from off, it goes into saturation, right?
Yes.
So when it goes into saturation, and after certain VGS, it goes into linear mode, correct?
Yes.
Okay, so that the saturation, as the current changes from saturation to linear, so how are you capturing? Quickly, can you answer in your compact model? At high VGS?
Yes, sir. So that was a iterative process we used, and we actually found that once we set the value and then we iterate around it, it does not matter because it's an absolute value which we don't need the actual value. So if we assume it to be a certain value, which we fix it, and then we iterate using that value for all the parameters, then it doesn't matter.
Okay, thank you.
Thank you, Achintya.
Thank you.
Let's move ahead to the next poster. Next, we have Reshma S. Kumar. Reshma, are you there?
Yeah.
Yes.
Hello. Am I audible?
Yes, please go ahead. Yes, yes.
Good evening to one and all present here. I, Reshma S. Kumar from Delhi Technological University, would like to present my work, which is a simulation-based study to analyze the effect of introduction of the recent ferroelectric silicon doped stack of MOSFETs, TFETs, and their junctionless and dopingless variants, the structures of which are depicted in the first column. These structures have been studied for their characteristic IDVG, IDVD relations, gate-gate capacitance of gate voltage relation, and dependence of transconductance over gate voltage as shown through the extensive graphs in the second column. We observe that the presence of ferroelectric layer and the difference in values of drain current in the forward and reverse sweep, obtaining a hysteretic curve, and this hysteresis is more pronounced in case of DGFE defects than the corresponding FET configurations. In this column, we presented the comparative IDG obtained after varying the geometrical parameters, that is, the thickness of FE layer from initial to 10 and channel lengths of 50 nanometer, 70 nanometer, and 100 nanometer. And the ferroelectric parameters, coercive field EC, and spontaneous emission PS, which are incremented by 10% and 80% of their initial value.
So Reshma, please try to conclude.
Analysis, we note that the DGFE TFET exhibits considerable in the drain current as EC and PS are increased in comparison to the FET devices, and also note that the FET devices manifest change in ID very simple parameters at a lower threshold voltage as compared to the TFETs, which demonstrate change much beyond that of FETs. So, the conclusion of our study. Thank you.
Thank you, Reshma.
Thank you.
Yeah, Reshma, so for low power applications, the TFETs are very useful. And you said you have reduced VT, right? Low VT.
Yeah, as we introduce, the VT reduces, right?
What is the reason for that VT reduction when you have ferroelectric insulating layer?
dependent on many other factors like capacitance reduction, etc. But I'll not be able to point out to one reason for this right now.
Okay, and have you tried to compare with multi-gate MOSFET like tri-gate or FinFET?
As of now, we have not tried comparing it with multi-gate structures.
Okay, okay. And what is your subthreshold swing for your TFET? Subthreshold swing?
Like functionless variant of the TFET, it was around 23. But for the FET, it was around 59 to 68 only. So it's a bit sub-threshold swing.
Okay, fine. Thank you.
Okay, thank you, Reshma. Next, we have a poster by S. Radhakrishnan. Radhakrishnan, are you there?
Yes. Yes. Am I audible?
Yes, you are audible. Go
Yes.
ahead.
Yes. Good afternoon to all. Actually, we worked towards an FIR filter, finite impulse response filter. So in this work, we have actually combined two different structures, namely hybrid adder and booth multiplier. So quite often we use this hybrid adder and multiplier in most of the architectures, but we made some modifications in hybrid adder and as well as in booth multiplier. So what we did in hybrid adder is, so instead of taking a mono adder, that is either carry select adder or carry look ahead adder. So we have variety of adders which can be used as an adder, but here we especially combined two different adders as hybrid adder. So if you take a 16-bit adder, so we have combined carry look ahead and carry select adder together to form a hybrid adder. So what we did here, we have changed the bits with, if we take 2-bit for carry select and 14-bit has been selected for carry look ahead. And the same thing can also be extended for different bit widths. If you select 4-bit carry select, then we have taken 12-bit for carry look ahead. So likewise, variety of bit width combinations can be taken as part of 16-bit hybrid adder. And we have also taken one more thing as modified booth multiplier. So booth multiplier is already available, but we have modified the structure by the way of reducing the partial product rows. So instead of having more rows while doing addition, we have reduced the partial product rows further. By that way, we have reduced the complexity of performance. Okay, so by including
Please
both these,
conclude, Mr.
yes, yes.
Radhakrishnan.
So we have combined this hybrid and as well as modified booth multiplier, and we made one MAC, that is multiplier accumulator unit, to provide a FIR filter. So we achieved a good percentage of improvement in terms of delay and as well as in terms of power. Thank you.
Thank you, Radhakrishnan.
Yes, it seems my paper is something odd man out paper because most of the papers are related to device, but this is purely a transistor MOSFET based paper.
Yes, so Radhakrishnan,
Yes, sir.
relate to MOSFET, how does your speed compare with the intrinsic delay of the MOSFET?
Actually, we have given a uniform pattern for 3 different configurations. We have selected MAC with the regular FIR, and sorry, the default adder, and we have the MAC structure with the hybrid structure, and we have also taken MAC with the hybrid modified booth multiplier. So for all the 3, we have given the uniform test pattern, and with that we have calculated the delay and as well as the average power. So based on that, we have got some good results.
Okay, and this will be implemented in what technology node? Suppose we want to fabricate a chip based on this. So which 180 nanometer, 250?
Yes, yes. We have implemented all these things, 180, 90 and 45. In all these 3 we have tested. But it seems you are all using even for low nanometer technology. So we plan to go further.
Okay, fine. Thank you.
Thank you. Thank you. Thank you.
Thank you, Mr. Radhakrishnan.
Thank you.
Moving ahead, the next poster is by Akanksha Mishra. That is me. And I am from Center for Applied Research in Electronics, IIT Delhi. So the topic of my poster is geometrically dependent space charge modulation and quasi-saturation effect in superjunction LDMOS device. The space charge modulation phenomena occurs when at high gate voltage, the current density in the LDMOS drift region exceeds the net doping concentration. As a result, the peak electric field shifts from the gate edge to the drain edge. Now, in superjunction LDMOS, which is made by keeping one SJ implant floating in the in-well drift region, this SJ LDMOS compels the current to conduct through the surface of drift region. Now, but the retrograde doping of this high voltage NVIL, it is depleted across SJ implant, leaving a narrow path for density. So this causes higher current crowding near drain, which attributes to the early onset of SCM. So this work provides an insight into the superjunction LDMOS behavior in off state as well as on state, as superjunction LDMOS offers 4 times higher breakdown voltage while minimum trading of RON. It also suffers severely from space charge modulation when compared to conventional LDMOS devices. So this paper talks about how by optimizing the geometrical as well as layout parameters, the space charge modulation or quasi-saturation in these high voltage devices can be delayed while improving the performance of the device. Thank you.
So any questions? So Akanksha, I have a question. So you are saying
Yes,
geometrical parameters. If I say in terms of gate, the metal gates and geometrical screening of drain electric fields, so can you quickly answer that how it will increase breakdown voltage?
Sir, so we are not changing the gate at all. The gate remains the same for the footprint is same for conventional as well as the superjunction. The
So you are
different
not using
geometrical.
any additional metal gate or metallic field plate kind of arrangement to.
No, sir. The geometrical parameter that I'm talking about is of superjunction implant only. That is thickness, its position from the surface, its doping, and its distance from the drain contact as well as from the gate contact. It basically on that. So that is the geometrical parameter related to superjunction implant. The conventional remains the same.
And how does it affect your ionization rates for electrons and volts?
Sir, so it depends on the actually optimizing these devices is quite difficult. So as if you can see in the figure 6, as the electric field becomes higher, the impact ionization is very intense at certain location where it experiences the high field. So that is what the paper is all about, how we can screen the electric field in these high voltage devices.
Okay, one quick question, So are you using heavy doping?
Of superjunction implant or the NWEL?
Superjunction implant to control breakdown.
Yes, sir, it is highly doped.
How much? 10 to 20?
No, not that. It's less than the contact doping.
Okay, 10 to 18, 19, right? So
yes, somewhere around.
Does it have heavy doping induced band gap narrowing effect?
Sir, so the band gap narrowing effect hasn't been taken into picture here because this is the comparison drawn.
Because that will change impact ionization energy of right. So that's right.
Yes.
Okay. Thank you so much.
Yes, sir. Thank you. So let's move ahead to the next poster now. Next we have Tahir Ahmed. Are you there?
Yes, ma'am.
Please go ahead.
Good evening to all. Today I'm going to present my work over the first principle study of structural, electronic and optical properties of calcium doped strontium barium niobate. In this work I've done first principle studies based on the density functional theory to investigate the structure and the electronic properties of strontium barium niobate, and the incorporation of calcium at the strontium site so that their stoichiometry can be changed to improve its properties, like the electro-optic properties. So basically, in this, I have used the Vienna ab initio simulation package and the generalized gradient approximation with a Bird parameter as the 4 electron volt for the niobium atom. In this case, we can see that we have observed from these density of states that the top of the valence band maxima is composed of the niobium d sites, whereas the conduction band minima is composed of the oxygen p states. So, but the strontium atoms, which composed of 60% of total stoichiometric of the total cationic sites, so the strontium was replaced by the calcium, and we can see that in this tetragonal structure that the strontium can sit over the 5 sites, like there are 2 tetragonal sites, one tetragonal site is vacant and the other are the pentagonal sites. So in this case, I have doped the calcium at the 2 sites, like one is the tetragonal, another is the pentagonal, and it has been observed from the band structure and the partial density of states that when doped at the tetragonal site it increases the band gap, while at the pentagonal site it decreases the band gap. And it has also been observed that the introduction of the calcium at the pentagonal site distorts the structure, which can be seen from these electron localization functions, while doped at the tetragonal site it doesn't give the distortion, and the C by A ratio remains the same in case of the tetragonal substitution. So I have seen that on the optical anisotropy in this material, which was plotted in the first graph, that I have seen that the refractive index towards the lower energy sites, or you can say that towards the lower frequencies, along the 100 and 010 direction, the refractive index shows the same variation, but along the 001 direction, uh, it, uh, it, uh, it, it is different from that of the other 2 directions. So we can say we have
Tahir,
seen
please conclude.
anisotropy. So, conclusion is that this material is good for the applications where we require the refractive indices, different refractive indices along the different directions, like the ordinary and extraordinary directions. So we have seen there from the refractive index variation, and also from the other properties we have seen that when the calcium was doped at the pentagonal site, it differentiates the properties from that of the tetragonal, like the absorption, reflectivity, and the dielectric constant shows a red shift in their properties. Also, the defect formation energy shows that the calcium at the tetragonal site is easy to incorporate as compared to that of the pentagonal site.
Thank you, Tahir.
It changes its properties in that way.
So, Mr. Tahir, you have used DFT, atomistic simulation.
Yes, sir.
Okay, so now you are saying this it distorts the structure, so it does distorts the crystal structure, right, in itself.
Yes,
When
sir. These are the
is in the pentagonal
electro-localization.
side. And how does it affect the if I am doing a measurement of dielectric constant? So I'm looking at macroscopic polarization.
Yes,
So how
sir.
does it affect the polarization of that?
Sir, polarization in the sense that A and B axis, A and B lattice constants are equal in this structure, and the C axis is different. That is of 3 angstrom around. So when the polarization of light is done along the C axis, means 001 direction, it is different from that of the 010 and 001 direction. Means along the C axis, 001 direction is there.
Okay, so is it linearly polarized or is it like it has cyclic or elliptic or any kind of rotation you see?
Sir, basically it is linearly polarized, we should say.
Okay. Now, if you when you are doing characterizing the refractive index, so
Yes.
this extinction coefficient. So can you comment on the extinction coefficient evaluation for your structure?
Yes, sir. Extinction coefficient. Basically, that is the imaginary part of the this complex refractive index. I
Yes.
haven't shown it here, but I can calculate it from the relation, from the
Right.
complex relation by using these epsilon 1 and epsilon 2.
Okay. Okay. So you are studying optical losses and etc. also.
Yes, sir.
Okay. Thank you.
Okay, thank you, Tahir. We can move ahead to the next poster. This is by Rajesh Satyanarayanan. Are you available, Rajesh? Mr. Rajesh? I think he's not present. Okay, sir, should we give this poster time or we can move ahead?
Is he available here?
Sir, he's not here in the participants list.
They were informed, right? About,
Yes, everybody was informed, sir.
maybe you can keep if there's some internet issue or something. I mean, if you have time, if they can also later on, if the person contacts you, they can give during this session only because we don't have time. Okay. Then we can move ahead, and if once again we can.
Okay, sir. Moving ahead, the next poster is by Rushi Jani.
Sir, one more thing, sir. Sir, we have 231. I mean, it's about 15 more, and we have only half an hour. So, should we tell to the? Yeah, exactly, sir.
We will speed up. No problem. Yes.
Mr. Rushi Jani, are you there?
Yeah. Am I audible?
Please, yes, you are. Go ahead.
Yeah. Good evening, all. My poster topic is a computational study on efficiency augmentation in a formamidinium lead iodide perovskite solar cell with WS2 as electron transport layer. So basically, in this study, we have simulated two cells, cell 1 and cell 2, using SCAPS 1D. Both the cells are having FAPBI3 as absorber layer. In cell 1, we have TiO2, titanium dioxide as ETL, and in cell 2 we have tungsten disulfide as ETL, and in both the cells we have spiro as a whole transport layer. Till date, no simulation study is reported which have utilized tungsten disulfide WS2 as ETL in formamidinium lead iodide perovskite solar cell. Also, upon incorporation of WS2 as ETL over the conventionally used TiO2, the theoretical efficiency of FAPBI3 based perovskite solar cell increased from 14% to 16.59%. There is an increment of 2.59% was observed. This increment in efficiency owes to the efficient electron extraction at WS2 FAPBI3 interface and also the higher electron mobility of WS2. Also,
Kindly conclude, Mr. Rishi.
Hence we conclude that upon incorporation of WS2 as ETL, we can drastically increase the power conversion efficiency of FAPBI3 based perovskite solar cell. That's all from me.
Does SCAPS take the recombination lifetime?
Yeah, we have considered the defect density to be 10 power 15.
And what about the complex refractive index of FAPBI3? Do you take the whole spectrum or directly you have given NK value for one wavelength?
Sir, we have taken the absorption coefficient from the available literature.
Okay. Thank you.
Okay, thank you, Mr. Rushi. We can move ahead to the next poster, which is by Prince Kumar Singh. Mr. Prince, are you available? Prince Kumar Singh, are you there? He's not present. So we can jump to the next poster. Next is by S. Pandey. Hello. Yes, this is S. Pandey, right?
Yes, Shubham Pandey. Yes.
Yes, go ahead.
Yeah, thank you, ma'am. Yeah, good evening. So this is Shubham Pandey, PhD scholar from Electrical Engineering Department, IIT Madras. So in this work, we are proposing a BiCMOS process. So this is in alignment with the 180 nanometer CMOS process of Semiconductor Lab Chandigarh. Okay, so in the process flow on the left side, you can see the conventional 180 nanometer CMOS process flow. We have in two additional step number 5 and step number 9. So with using those two additional marks, we could see a significant improvement in the performance of the parasitic BGTs that we use in the CMOS process. So so this is the proposed process flow, and in the conventional in the parasitic BGT base and emitter, and the extrinsic base were isolated through the ST isolation scheme, so that was causing us the footprint area. So here in this work we use the base emitter poly as an for isolating the emitter and the extrinsic base, so that help us in reducing the footprint area as well as some improvement in the figure of merits. Okay, so on the right side you extensive process simulation figure with data. And, here scheme. Okay.
Please conclude.
To get the in terms of RF cap, we are having a gain around, close to 140, and then early voltage of around 20 volt. Yeah, yeah. So we have also drawn some layouts, and finally, what developed the compact model for the structure. So yeah, so that's it from us. Any question?
So Mr. Panda, so for this 180 nanometer CMOS integrable scheme, right? You said the poly, you have avoided STIs by these polys, right? So because
yes,
the emitter based collector contacts should have poly plugs. So how did you segregate this doping of this poly and that contact plug poly?
So sorry, sir. So can you see the region poly overlap over the base here in the schematic? Yes.
Yes. Please.
Essentially, the source drain implantation of the we have a so here you can see emitter poly deposition. Then we have emitter poly doping.
Okay.
Right. So it's not coupled with the source drain implantation of the CMOS process.
So what did you do? You drive in diffusion for example, for this emitter and base region creation, drive in diffusion, right?
Yes.
Because the limitation is getting emitter width and base width because of the subtractive diffusion process. So what was your some scenes profile? What is your depth values from your scenes profile, emitter and base for the intrinsic BJT structure?
So we have a base.
Okay.
And if you want emitter, it is around.
Okay. Okay. And emitter is what is the peak doping of your emitter? Peak doping. Okay, fine. And also I see that the calibration at low VB and high VB has not matched for your base current.
Like 5.
Okay, I think the leakage, the real experimental device is leaky. It has traps. So the combination current is high.
But Icee shows a good level.
Yes. Okay. Thank you.
Okay, thank you, Mr. Shubham Pandit.
Tested in the bias range of, let's say, 0.7 to 0.8. Anyway, you will have Kirk effect or something.
Yes, for silicon.
Thank you.
Exactly. Right. Correct. Fine.
Thank you, Mr. Pandey. Moving ahead, we have next poster by K. Agrawal.
Yes,
please start.
So I, Kavish Agarwal from Ajay Kumar Garg Engineering College. So this study is focused on comparative study of PMOS and NMOS of 180 nanometer channel length with silicon and silicon germanium substrate. Silicon germanium MOSFET of different mole fractions of germanium is also simulated. It has been found that higher current mobility results in lower threshold voltage and higher saturation current. It is reported that greater change in hole mobility is observed as compared to change in electron mobility, and hence change in threshold voltage of PMOS. We have plotted sub-threshold characteristic, and it is observed that silicon germanium based PMOS provide better ion to I-off ratio than silicon based PMOSFET, and we observe there is no prominent change observed in silicon germanium based NMOS. As you can see from the plotted VTC of CMOS, can be seen that silicon germanium CMOS provide better characteristic close to ideal characteristic of CMOS. So by this paper, we propose to use mixed CMOS structure, silicon-based NMOS and silicon germanium-based PMOS, which may in better characteristic due to lower mismatch of electron and hole mobilities. Thank you.
So, Mr. Agrawal, in your PFET, it is the channel region you are making Icee or your source and drains are Icee?
Hole source and contacts are
Can you repeat again? I could not hear. Yes.
Sir, the whole substrate is silicon germanium.
The whole substrate is silicon germanium, and your source and drain regions are?
Of aluminium. Contacts are of aluminium.
Aluminium. Okay. So what is giving that boost to the hole mobility in the channel?
Sir, there is a concept of silicon. Sir, actually, what is happening when in silicon germanium, the atoms are farther apart, so in the semiconductor, due to which the mobility of the carriers increases from the graph. As we increase the mole of germanium, the current mobility goes on increasing.
Okay.
Yes, sir.
Okay, fine. So thank you.
Thank you, Kavish. We can move ahead to next presenter. Next is Bhaskar Roy.
Am I audible?
Yes, you are audible. Please start.
Okay, my topic is comprehensive modeling of GAN heterostructure based sensor and analytical approach. Acetone may produce in variation and lead to the slackness and sleepiness if the level exceeds beyond 500 ppm. So the environmental level of the acetone in industrial area therefore needs to be monitored and detected. In addition, acetone diagnosis can become a good biomarker to track the food and vegetable standards. GAN heterostructure Schottky diode has been employed to detect the acetone efficiency. When the sensing device is exposed to acetone, the electrostatic potential of the ALGAN surface gets modified due to the polarity of acetone, and this change in potential causes the change in the concentration of 2-deg and thus the change in the current. So at the hetero interface, as the high density 2-deg is very closely spaced to the surface, therefore thereby being extremely sensitive to the any modification in the surface states, that is any alteration in the atmosphere. The acetone sensing ability of the ALGAN GAN Schottky diode at low temperature with varying concentration of acetone vapor is being exhibited here. In this work, an analytical model has been developed, which can predict the different sensing characteristics, and you see this is the structure of the proposed heterostructure model.
Please conclude.
Yes, and if you see these are the analytical sensor model, and in this model, this is the delta n is the change of the electronic concentration or carrier concentration, and if the change of this carrier concentration depends on the surface coverage by the gas molecule. So in this curve, you see the surface coverage is depicted with the concentration of gas. So as the concentration of gas increases, as the concentration of gas increases, surface coverage also increases, but after some point this will saturate, and here we are also predicting the sensitivity, which is again gradually increases with the concentration of the gas, and
Please
after a certain
conclude, Mr. Bhaskar.
certain point it will again saturate. So in conclusion, as the gas concentration increases, the surface coverage also increases due to the adsorption, but after a certain limit it will be get saturated. So the sensitivity in the
Yes.
Hello.
Mr. Bhaskar, you are still there? I don't know.
I think he got disconnected.
No, it looks like, yes.
Let's move ahead to next poster now. Next poster is by G. Durga. Are you there?
Yes.
Yes, please start.
Okay. This is Durga from SN College of Engineering, Chennai, and my topic is heavy ion irradiation study in silicon nanotube based inverter chain using 3D TCAS simulation. So in this work, we constructed and demonstrated the inverter chain. We consider both cascaded and then parallel type using silicon nanotube FET. Again, silicon nanotube, we consider both junction-based one and junctionless one. Then we studied the impact of heavy ion radiation on the pulse width of each inverter stage in the inverter chain. And then, so the result shows that the pulse width increases with the number of inverter stages increase in the parallel type. So this is because of the increased node capacitance. And another result is the junctionless tube has more transiently compared with junction-based nanotube, and this is because of the heavily doped channel region. And the first column shows the figure shows silicon nanotube FET. So silicon nanotube FET is one of the advanced CMOS architecture which has minimum short channel effects. So first diagram is the junction base and the second one is the junctionless one. So junctionless advantages, there is no, all the three regions are same doping concentration, so there is no junction and then no doping concentration gradient. So we consider the two devices to realize the inverter chain. And the second column shows the inverter chain. The diagram shows the inverter realized using junction-based silicon nanotube FET, and the output results are shown in the figure number 6 and 7. And the next step, second step is we first verify the operation of cascaded check.
Ms. Durga, please conclude.
Okay. Then we apply that heavy ion strike. The heavy ion strike the first stage N device when the input is 0, and then we observe that so this will create the pulse width, and this pulse width is propagated to the next stage, second stage, third stage, fourth stage, and so on. So we observe that for cascaded and parallel type, we observe that pulse width. So we concluded that in parallel type, the pulse width is more with respect to the number of inverter stages. The reason is the node capacitance, and junctionless has more transient because of the heavily doped channel compared with your junction-based inverter chain. Thank you.
Yes, so G. Durga, these are all nanotube FETs or these are all cylindrical structure? I mean, the thick silica, like silice.
Nanotube structure, so nanotube, so it's having cylindrical structure, so it has both the outer cylindrical gate and inner cylindrical gate. So the channel is a cylindrical one.
It's a thick cylindrical structure of silicon nanowire, right?
It's a 5 nanometers, sir. Only the silicon thickness is 5 nanometers.
Okay, fine. So when these heavy ions are irradiated and you have single event transient you're simulating,
yes.
So
Yeah, I see there is a chain. You have created a ring oscillator, right?
Not oscillated, so only chain, inverted chain.
Inverted chain. So have you estimated stage delay? How does it affect stage delay, this ACT?
Yes, so each stage we measured that the impact of that heavy ion. So it strikes the first stage output, but this impact is observed at the subsequent stages. In the consider cascade stage, it will get reduced in the subsequent stages. But in the parallel type,
Okay, so what is your chosen gate length and what is your stage delay value in picoseconds?
Okay, a gate length is 45 nanometers, sir, and the delay for cascade type is 6.5, around 6.5 picoseconds, and for parallel type it's 11 picoseconds.
Okay, thank you.
Sir, thank you, sir.
Thank you, Durga. We can move ahead to a next poster. This is by Monica Sharma. Are you there?
Yes, ma'am. Am I audible?
Yes, you are. Please start.
Good evening, all. I am Monica Sharma, PhD scholar from the Delhi University. Here we have done the simulation-based study on different doping list-based structures. Firstly, what we have done is the comparison between the three different materials like silicon, InGaN, and InGaAs-based devices. Basically, doping list effect, among which we have obtained like InGaAs-based doping list effect is showing much better characteristics as compared to others. So then we have taken three different interface charges like the positive interface charge that is plus 1e12, negative interface charge that is minus 1e12, and then the no interface charge, among which the positive interface charges shows much better characteristics for all the three materials. Then we have taken these three different materials to further studies like the InGaAs based heterogate, heterodielectric. Then we have merged these two like the heterogate and heterodielectric. Likewise, we can see in the transfer characteristics shows in the second column. Likewise, InGaAs based doping list effect with the heterogate heterodielectric shows the higher on current, and similarly for the InGaN based heterogate heterodielectric also. Then further we have analyzed the AC characteristics, the AC transient analysis for all the structures, among which InGaAs based structure shows much prominent result, as we can see in the last column. InGaN based heterodielectric and InGaN and InGaAs based heterogate heterodielectric shows no peak overshoot, while other structures shows maximum peak overshoot. That basically because of the CV characteristics that I haven't shown here, but this inference came from the CV analysis itself. Like when the capacitance is low, it shows much lower peak overshoot, while when the capacitance is higher, it is any doping list effect shows much higher overshoot, either in the positive direction or in the negative direction. So from
Please
all
conclude, Ms. Monica.
okay, ma'am. So from all the analysis that we have done, we have concluded that the InGaAs based heterogate heterodielectric shows much better performance as compared to others. So it can be used for designing biosensing applications also. Yes, ma'am, I have done.
Thank you, Monica.
Biosensing application, Monica, can you hear
Yes,
me?
sir.
So,
Yes, sir.
biosensing application. So, how do you judge? How would you measure the sensitivity, etc.?
So by like for calculating the sensitivity, we need the change in the threshold voltage. Here, likewise, we can see in the second column for the three different interface charges, we are seeing the different threshold voltage for all the three difference. For positive, it is coming much lower threshold volt as compared to the negative one. So by changing its capacitance value, like the epsilon R, for different materials like APES and other materials, we can conclude it for the biosensing application.
So, your interface, looking at your CV characteristics, can you tell me your interface charges are donor kind or acceptor type?
So it is of both type. Like I have taken both PTC and positive interface charges and negative interface charges. But the characteristics are coming much prominent for the positive one, as it assists the tunneling current from source to drain direction. Because it helps in the formation of channel.
And you have fixed your position of maximum, the intensity of state peak of the interface state and CNL, etc. Your calculation.
Yes, sir. I have fixed the capacitance as to 1e minus 2 femtofarad.
Okay, so
And the right.
what kind of distribution did you take for your interface trap changes?
Sir, I have taken, sir, actually, I have optimized this around the channel interface only, because firstly, I have taken the interface charges over the whole device, but the effect was not much prominent. So then I have taken the effect of the interface charges on the channel itself. Then we can see much prominent difference among all.
Okay, thank you.
Okay, thank you, Monica. Moving ahead, next we have Muli Shashank Reddy.
Yes, ma'am. Am I audible?
Oh, yes, you are. Go ahead.
So myself, I am Shashank Reddy. So I am from IIITM Kanchipuram, and we have worked on the double gate NCFET to achieve the low less than 60 millivolt decay, because as we know, there's in MOSFETs, the drain and source carriers follow the Boltzmann statistics, which states that our subthreshold swing should be less than 60. So basically, our structure, as you can see, our structure, we have taken ferroelectric capacitance and oxide as well as semiconductor capacitance. So we have followed a bottom to top approach. So we have first calculated the semiconductor capacitance, and later using a Launder theory of equations, and we have calibrated the VGNC value. So basically, first we have taken our MOSFET voltage as an input and got the VGNC as an output. As you can see, we have calibrated different characteristics of it, C versus VQ versus V, and ID versus VGNC. So we can see that the ID versus VGNC, it's similar to the MOSFET. Like first it follows the triode region, then it reaches the and we can see that we have calculated the subthreshold swing, which we got is as a 28, so which is less than 60. And we can see that ferroelectric, what happens is due to its polarization, it steps up the voltage between our semiconductor and the oxide, so that even for a low power, it satisfies our Boltzmann statistics, as well as it can be useful for determining the low power high frequency devices. Yeah.
Mr. Shashank, okay. So we can have questions.
Yes, Asang. So you said you're using ferroelectric NC, negative capacitance FET, right? Ferroelectric.
Yes, sir.
Gate oxide. So how does that voltage transformer action takes place? You just explained there's a boost up of voltage, right? Near the semiconductor
Yes, sir.
surface potential.
Yes, sir.
So how does that polarization, the positive feedback within the ferroelectric gate oxide leads to that? This polarization is I am talking about dielectric polarization, the ferroelectric dielectric.
Yes, sir. Like there will be many dipoles in that ferroelectric, right, sir? So whenever we give an input voltage to that, so all dipoles tend towards one direction. So that what happens is, due to the electric field, the charge carriers goes from one end to the other end, so that we get an extended voltage, step up voltage in the other side.
So that happens because of regenerative positive feedback effect within the that dielectric.
Yes, sir.
Yeah. Okay. So what is your subthreshold swing that you got from your calculation?
28, sir. Around 28 points. 28.2. Like.
And do you think if you go to low temperature, the same subthreshold swing you will obtain? Suppose you just reduce temperature from 300 Kelvin to 100 Kelvin or 50 Kelvin.
I haven't calibrated the structural effects, sir. So, but I think due to if you decrease the temperature, I think the energy decreases. So I think so we get an higher subthreshold swing than this one, sir.
Okay. Okay. So now why I'm saying, because electron wavelength will increase at low temperature.
Yes,
So
sir,
that will affect your tunneling, the carrier injection from source to channel. Okay. So that can affect subthreshold swing.
Yeah, sir. But I haven't included that consideration, sir. I have taken at room temperature. So.
Okay. Very good. Okay. Thank you.
Thank you, Mr. Shashank. Next, we have Preeti Kumari. Ms. Preeti, are you there? I don't see her present.
The internet issues might be there.
Yes, sir. So we can we move ahead, sir?
Yes, yes.
Okay. So moving ahead, the next poster is by Chaya. BM. Chaya, are you there? She's not here.
Yes, then go to next. Maybe you can go proceed to next poster.
Next we have Marsha and Parmar.
Hello, am I audible?
Yes, you are. Please start.
Good evening, everyone. My name is Marsha Parmar, and I'm a postdoctoral fellow at Nanomagnetic Laboratory at Department of Physics, IIT Delhi. Today, my poster is on fabrication and characterization of two-dimensional electron gas-based magnetic sensors. With these sensors, we want to detect the change in geomagnetic field due to the presence of ferromagnetic object. The material used for Hall sensor is the heterostructure of indium arsenide and aluminum antimonide, which is 20 nanometer below the surface. Hall measurements show the carrier sheet density of the order of 10 to the power 16 per meter square and Hall mobility of 1.8 meter square per volt second at room temperature. Our simulation shows that the magnetic field of a ferromagnetic sphere with a relative permeability of 1000 and a radius of 5 centimeter falls to about 5% if we move 10 centimeter away from the surface of the sphere, which in our case is 5 microtesla. We also perform noise spectroscopy measurements on our devices to determine the sensitivity, which is 1 microtesla per root hertz for our fabricated devices. Thank you. Now I will take any questions.
Thank you, Marsha.
Yes, so Marsha, I have a question. So the geomagnetic field, I remember, is 50-60 microtesla.
Yes.
That's what, and it depends on longitude, latitude. So you are saying that this can be measured so small. So what is your sensitivity of these Hall sensors?
Sir, we perform noise spectroscopy measurement, and we have found that at 100 hertz bandwidth, the sensitivity of our sensor is 1 microtesla.
Okay. Suppose just a quick answer. Suppose I send your sensor on a spacecraft to land on Moon. Okay? And on Moon, Moon surface undergoes oxidation because of our oxygen molecules from atmosphere reach Moon because of our geomagnetic field. So can your sensor gets engaged that this Earth's rare geomagnetic field, how much oxygen it is dumping on Moon and oxidizing Moon surface? Can that do that?
Sir, if we attach a permanent magnet with our sensor, then it will be easy to detect the. So if we attach a permanent magnet, there will be more change in magnetic flux.
Okay.
So then I guess we can detect the change, even a very small change we should be able to detect.
Are you doping these materials or?
So there is a delta doping at the spacer layer of aluminum antimonide of terpene.
And how does it help in your sensitivity?
So it increases the carrier concentration, and that directly relates to the sensitivity of our sensor.
Okay, thank you.
Thank you, sir.
Thank you, Marsha. Now we have our last poster for this session. This is by Shivani Rani. Miss Shivani, are you present? She is not present.
So that's all for today's poster session.
Sir, P2. Sir, I am present, sir. P206.
I think some people have joined, I think.
Yes, sir. Mr. Atanu is present here. Atanu, could you please tell me your poster number?
206, Akansha, 206.
206. Okay. Please start.
Yes. Good evening. My name is Atanu Purugasta. I am from Department of Electronics and Electrical, IIT Guwahati. So basically, what I'm going to present is that I have simulated that means I've simulated tandem solar cell based on tin perovskite solar cell. Actually, you know that the maximum efficiency that we got from lead perovskite is 26%. But the presence of the lead is hindering the commercialization of perovskite solar cell, and the maximum efficiency that we got from tin perovskite solar cell is 9.9%. So we know that in tandem configuration, if we stack high band gap material with tin perovskite, we can increase the efficiency as well as the stability. So with this MATLAB simulation, we have optimized the thicknesses of all the layers of the tandem solar cell, and also we have generated the maximum current density so that mismatch error can be reduced to 0.2 milliamp per centimeter square. So in this coding algorithm, what we have used, first of all, we have optimizes the thickness of non-active layer. So non-active layer means ITO, P dot, PCBM. These all are non-active layers, and we have varied the thickness of non-active layer from 0 to 200 nanometer, such that the generation can be maximum in the bottom subcell or FSNI3 subcell. After that, after we got the thicknesses of non-active layer, we have varied the thickness of active layer such that the from 0 to 500 nanometers, such that the generation of the current in both the subcell is less than difference of the generation of both the current in both the subcell should be less than 0.2 milliamp per centimeter square. So what are the
Mr. Atanu, please try to conclude now.
So what are the finding is that in all combinations we got the maximum current density 15.56 from this configuration serial number 3, and the serial number 9 and 8 is showing that they are the worst in terms of combination with low band gap subcell. Their spectral overlap less is loss, and reflection loss is also more. Thank you.
Thank you, Atanu. Yes.
Atanu, I see that there is a fraction of light absorbed versus wavelength. There you have only used two structures, right? You have compared two.
No, sir. No, sir. This is for the best combination. I have given the.
Okay. So what is happening for the sudden drop beyond visible light spectrum, the light absorbed in that structure, the black line?
Black line is, sir, because it's a high band gap material, so its absorption spectra is around 750 nanometer. After that, it suddenly drops to 0, and rest of the absorption is going on the FSNI3 subcell because it's a low band gap material.
So what is the effective band gap for that black structure, black line?
Sir, its band gap is around, sir, 1.8.
1.8. Okay. And the red curve?
Sorry?
For the red curve, what is the structure?
It's a, sir, FSNI3. Its band gap is around 1.4, sir.
And how long that stage doesn't drop significantly in the long infrared range?
Actually, sir, the refractive index value, NK value, that is available for all the materials up to 900 nanometer. So properly, if you want to simulate, we should have the NK value for all the range, for all the wavelength range. It is not available. So it is all based on the literature survey. We didn't do the ellipsometer spectra.
So it can go beyond 1 micron, right?
Yes, sir. Yes, sir. It can go beyond 1 micron also.
Thank you.
Okay, thank you.
Sir?
Yes.
Hello, sir.
Pragya, yes.
Sir, there are 3-4 orators who were not available at those times. So can we recall them, and if they are available, they can present?
Yes, please.
So Dr. Rajesh is there?
Okay.
Dr. Rajesh? No. Mr. Prince Kumar Singh? Mr. Prince Kumar is there?
No.
Okay. Then we have Miss Preeti Kumari is there?
No. No.
Okay. And then Megha M.
No, she is also not here.
Okay, so and the last one is Miss Sivani Rani.
No, she is also not here.
Okay, so we have 5 candidates who are not available for their presentation. Sir, there were 2, 3 students in the beginning when you were not there. So, what to do
Yes,
about
if
that?
they can present, that will be fine because I'm here to grade. So is
Okay,
there?
sir. So,
I don't know.
I am one of them, sir.
Okay, please go ahead.
Okay, Akansha, please can you share my slide? The first one, 200. Yeah. So, sir,
Yes, go
in
ahead.
my work, what I did it for the different growth condition leads to the different concentration and energy of the surface states. So, though it is legitimate that there is not much variation in surface states for the single devices when it got fabricated, but still when the growth condition change, it's change. So to capture the effect of the surface states in terms of concentration and its energy, we have analyzed its effect on the conduction band of the barrier layer and 2-deck channel. So when we increase the concentration of the surface state, the electric field which got generated get exceeded, and inbuilt electric field is bring down the conduction band of the barrier layer. And while it's bring down the conduction band barrier layer, the more electron will get transferred from the surface to the tube. We can see from the figure that there is a jump in the conduction band slope while we are changing up to certain concentration of surface states. While we are changing the energy of the surface state, there is no sudden change. There is a smooth transition for let's say from 0.2 electron volt to 1.4 electron volt. So what we are trying to say is that when we are changing the concentration of the surface state, there is a hump, there is a change, sudden change happening in the 2-deck concentration as well as in the slope of conduction band. Whereas in when we are changing the energy of the surface states, there is a linear relation between energy of the surface state and 2-deck electron concentration and the slope of the conduction band. That's all.
Yes, Pragya. So I can see that you are saying some surface states they can act as donor to your 2D electron.
Yes, sir. Yes, sir. Yes, sir.
And under how do you induce these? How do you introduce surface states which can act as donor?
Sir, we have in TCAD facility we can define traps as a donor surface trap, and I have just introduced as a silicon nitride 1 nanometer layer, and I have just filled that layer by these traps.
And where did you pick your CNL, charge neutrality level, within the energy?
That is approximately, sir, 1.52 around. I think from.
Okay. And have you analyzed the CV and how does this charging of
No,
this?
sir. That was not the part of the study, sir.
Okay. Good. Fine. Thank you. And what is the conduction band valence band offset in your heterojunction structures?
It was approximately, sir, 48% of total band, sir. That I have not put it over here, but it was approximately 49%, sir.
Okay, fine. Thank you.
Yeah, thank you, sir. So could we wind up, sir, now?
We can wind up. I think there are no more presenters, right? So
yeah,
we can
definitely,
thank all the participants and all the research scholars and scientists and students who presented.
Yes.
We have Icee 2020. We thank you all for participating and illuminating us with your excellent research work we have been doing. Thank you all. Thank you all.
Thank you very much, sir.
Thank you, sir. Thank you, everybody.
Yes, thank you, everybody.
Thank you, sir. And you will.
Welcome everybody to this session. Invited talk by Professor Jabour. We are awaiting him to join yet. Welcome, Ghassan. It gives me great pleasure to introduce Professor Ghassan Jabour. He's our scheduled speaker for this particular talk. He's the Canada Research Chair Tier 1 in Advanced Materials and Devices and Professor of Electrical Engineering at University of Ottawa. Professor Jabour has spent the last 14 years building research and development centers of excellence from the ground up in various locations in the world. He was the founding director of the Solar Photovoltaic Engineering Center and Professor Materials Engineering and Electrical Engineering at KAUST. Professor Jabour was the founding PI for the large $50 million plus proposal at Flexible Display Center at Arizona State University. And in addition was the director of Flexible and Organic Development at FDC, of Advanced Photovoltaic University, while being a professor of School of Materials at University. He has many distinguished honors and awards, including SPIE Fellow, Fellow of the European Optical Society, Distinguished Professor of Finland, Academy of Finland, Al Rawabi Endowed Research Chair Professor, and numerous keynote plenary seminars and other invited talks to his credit at various international and national conferences, and has done a lot of work with companies, especially startup companies. He he is an MRS Symposium X speaker, has won several Best Poster awards over there. He has an award from the US National Academy of Engineering from 2006 and Japan America Frontiers of Engineering Symposium. He's sufficient to say that he has raised over the past 16 years more than $540 million in competitive research funding, SPI, COPI, and Collaborator. And his research and development advances have been highlighted in numerous international journals, magazine, newspapers, ranging from Angewandte Chemie, Nature, Nature Photonics, and MIT Technology Review. And without further ado, since we are starting a little late, I would hand the floor over to Professor Jabour. One note to the delegates: if you need to pose a question, please use the Ask Question control on your screens. Professor Jabour, over to you. Please share your screen and get started. Professor Jabour, we can't hear you. Ghassan? I think there's some technical issues. Let us wait a while. Thanks for your patience. the second entity.
Okay.
Yeah, there you go.
I can you see my screen or not yet?
Yes, something is coming through, but it is hazy.
Yeah. Oh, that's because my camera is closed. But let's see. Did that do it or no? And of course there is snow, so the what do you call it? The weather doesn't help here. Let me turn on the light. Okay, so I don't see the share option anymore that you talked about.
It should be at the beginning, at the bottom, where it says start video and then share.
It is there, but so I share it through WebEx. Yeah, it is there, but it is not. I cannot choose it anymore.
You might want to disconnect and then try to reconnect and
Like restart the whole computer.
Yeah, we'll wait. No worries.
I'll restart the computer.
And you try it through the app this time.
Do you want me to restart the computer? Leave the meeting?
Yeah. Please disconnect and then reconnect. Yeah, you're there.
But the share is not possible anymore. It's what do I do?
Have you tried it through the app?
I am in the app.
Okay. So share screen should work. If you can email me your presentation, I can put it up.
Okay, but please, I don't want it to be published. Okay.
Sure. No, I'll take care of that.
Okay, I'll try. It's a huge, but I'll try PDFing it.
Okay.
Cisco. Can you see this one? No? Oh man.
Gasan, it shows you as logged in from two different locations at the same time. That might be interfering.
It's too large to send. Right.
Try to do it through Google Drive.
Huh? Anybody there? Hello?
Yes, sir.
Let's see. Why it's not sharing, eh?
Zan, I got your Zoom link. We can't use that with the conference, unfortunately.
Hello? Darn. Oops, the Zoom is banned. Oh no. Sorry, buddy, I'm trying here. It doesn't seem it's working. It says join meeting, I'm joining. Share. Connecting.
Hello. 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 Mr. Singh, I am audible for you. Hello. Hello, Mr. Singh. I am audible for you. Hello. Hello. Hello, Mr. Singh. Can you please unmute yourself? Hello. Hello. Mr. Singh, are you there? सर मैं बात कर रहा हूँ कोई मिस्टर सिंह सुन नहीं रहे ठीक है ओके ओके ठीक है अभी अभी करवा रहे थे ओके ठीक है ओके प्राइवेटली मैसेज डालोगे तो उसके जवाब हेलो यही पर हूँ मुझे टाइम लगा 9:30 बजे वेट क्या करना है नहीं अभी दोबारा मैंने
Welcome back, Gasan. Can you try sharing your screen now, if it works? I think they need to make you presenter. There's something going on here. Gasan, we can't hear you. Yeah, better.
This is depressing. Can you hear me? Oh, now it works. What the? Hello? Raja. Well, I guess my time is out, eh? Hello? How come I can't hear anybody? Hello?
You can finally see your screen.
Yeah.
But the audio is not coming through now.
How about now? Is it coming?
No.
Hello?
I think
Hello?
the volume is set to 0 at your end. Probably.
Oh man. Yeah. Okay. Let me see what I could do here. I have it at maximum volume. I can hear.
Because we can see that your audio is activated. It is actually making some sounds at that end, but no actual signal is coming this way. Your visual is coming through fine right now.
So what do I do?
I think you need to increase the volume of your audio, like your sound card settings or whatever.
It is at maximum.
Then for some reason, the audio you need to then unmute yourself. Maybe try to mute and then unmute yourself.
Mute. And then unmute. How about now? Gee.
No, it's not coming through. It is like the visual feedback is that you are saying something, but no sound is coming through actually.
Okay, I could see there is an X on the screen, but how do I go back to this to unmute using the program, not my computer buttons, mute, unmute?
Yeah, it has that right next to share. There is a start video control, and then there is an unmute control.
Okay, let me escape this one. Oops.
That's what you need to do. You were actually coming through on audio earlier, so I was even able to hear my own voice over the phone.
This is strange. This is very strange, man. Here we go. Let's see. Co-host. No, that's you, not me. You cannot unmute me yourself, like in Zoom?
No, I can't.
Here's my host. Oh boy. So I have to re-exit and do it again?
No, don't do that. We finally got your signal through. We don't want to lose that.
Why it's not letting me, man? This is.
Your voice is not coming through. That's all.
pretty retarded system. This.
It's not.
Ah. Oh boy. Okay. Thank you. Right. Hello. And now I don't want to have problems here now. Okay. Well, thank you very much. Can you all hear me, Raja?
Yes, we can hear you. Yes.
You can hear me? Okay. So
Yes.
I'm sorry about this, but let's move on to talk. I'd like to thank the organizers and the chair of the session, Dr. Madhusudan Singh. And then my talk will focus on how to use basically reactive printing for the self-assembly of nanoparticles and how do we go from there, hopefully to push it to quantum dots. And I'll show one early result of using this approach to make quantum dots on certain structures. Now this is not cooperating. Okay, I guess different modes. Okay, I'll skip this one just in the interest of time. We do have many kinds of research, but I'd like to acknowledge the people that contributed in one form or another to the success of this area in my group. They're all right here, and the funding agencies that are relevant to this particular talk. I will start the talk with a little bit of a reminder what is inkjet and what is in particular passive inkjet. Then we go to reactive inkjet and talk about how to make self-assemble gold nanoparticles and move on to show you early result of how do we push the boundaries to make nanoalloys and some compound nanoparticles. And then show you also a couple of slides on our results on roll-to-roll, how we move this particular field from an inkjet format into roll-to-roll. And so our aim in the group here in this particular research is to take inkjet as a pointer or as basically a demonstration of principle before companies can go in and spend a lot of money to make it into roll-to-roll. As you could see, this roll of paper here in Finland, and the people are under here. So we want to start with inkjet, optimize the process, and hopefully send all the parameters of the experiment to roll-to-roll. Of course, they're not going to be all the same, but the basic ones about the chemicals and the chemistry and the wetting and all would be almost the same with some tweaking to this different process, but the inks are particularly relevant to this process. The inkjet we used is a Dymatics Fuji inkjet, although you could use many other inkjets if you wish, but this is the one that we used. We started by filling the cartridge, and then we print on top of the substrate. I'll just move on with the talk that way. So what is passive inkjet? Passive inkjet is that you take the things you want to deposit, let's say nanoparticles, or in this case quantum dots. You make them first. You make the quantum dots. You make the ink that's going to host the quantum dots. Inject the ink in this cartridge, and the cartridge will print out of these nozzles right here. Okay. And as you could see from the previous slide, we have 16 nozzles with spacing 254 micrometer in a single row, and the nozzle opening is on the order of 21 micrometers. And then you put, this is a single ink, so you have to use 3 different inks to print red, green, and blue for a display application. This is a micro display done in our group for the first time to demonstrate many years ago in 2010, to demonstrate the power of inkjet in realizing a DC-driven quantum dot LED, as you could see here. So the bottom line is you have to make the quantum dot first and the ink and inject it and print. We want to go away from that and not make anything first, just put the starting materials in the cartridge of the inkjet and somehow allow the chemistry to happen on the paper or on your substrate of interest. Now, the current approaches for this particular topic, gold nanoparticles, basically for plasmonics, if you are in plasmonics, is that you buy or you make your nanoparticles with traditional chemistry, and then you deposit the resulting nanoparticles onto the substrate. And the way you make them, you just mix starting reducer and the starting material for certain metals, gold precursor or silver precursor, or whatever have you. And this shows the traditional one approach, which is the Turkovich method, where it's a pot chemistry. Basically, you mix the chemicals together. This is the ratio between the reducing agent and the starting material or the metal source. 1 to 2, 1 to 1, 1 to 2, 1 to 3, 1 to 4. And in this particular case, after 30 minutes, these ratios, we can see the SEM here, you could see different size of nanoparticles. So you have to stop the reaction at some point fast and extract those nanoparticles at the size that you need. And even with that, these nanoparticles are not all uniform size. You still have to do certain approaches to clean them from any debris or foreign or remaining chemicals that you don't want to stay in your ink. And then centrifuge, if you have very high centrifugation, and if the nanoparticles are really large in size, you could centrifuge pretty well and isolate the size you want. But pretty much this is a simple, straightforward process. Our approach is to really use the inkjet. Like I said, we won't use more than one cartridge because this is a single ink cartridge. In one of them, in this particular case, we put one ink, and in the other, we put another ink, and we print on top of each other and allow the chemistry or the self-assembly to happen. Why do we want inkjet? Inkjet allows us to use almost 99.9% of the materials that we put in it and get products out. That is, it's environmentally and low carbon footprint, basically, therefore environmentally safe and friendly. We can also not only do a reaction, we can also pattern in situ. As your reaction is happening, you can also pattern with the inks that you are printing. Therefore, reducing the complexity of the experimental steps. It is possible to do combinatorial approach with inkjet to optimize the reaction space and get to the discovery of properties or to the size optimization very quickly, as opposed with the pot chemistry method or the Turkovich method. And you could, of course, use the inkjet, as I said, in our approach. We want it to be a pilot, basically, or a pointer for the roll-to-roll approaches. In this particular example, it's really powerful example, in my opinion, that shows beautifully how reactive inkjet can succeed. We have one cartridge. In it, we put ink A, and that ink A is made out of 1 milliliter oleamine in 10 milliliter of dichlorobenzene, okay? And then we prepare another ink separately, and that is obtained by dissolving 0.12 millimole of gold chloride trihydride. This is the gold source, okay, or the precursor that I would use in 10 milliliter dimethyl sulfoxide or DMSO. So we have two inks here. We take this ink, put it in one cartridge, and we take this ink and put it in another cartridge, and we print. The cartridge we use is 10 picoliter droplet volume. So each drop has the size of 10 picoliter. Okay, we printed for about 22 micrometer in diameter, and this cartridge is placed at about 0.25 millimeter. That is the surface of the nozzle is, or the nozzle itself is above the substrate that much, just 0.25 millimeters. Everything is done as far as printing is concerned at room temperature, and we use all sorts of substrates. In this particular case, silicon is going to be, but you will see later that we can also print on paper using roll-to-roll, not this self-assembly is not limited to very nice crystalline structure of a substrate. The nozzle voltage was 6 to 9 volts to drive that nozzle. The pattern in this case was chosen as a square-shaped matrix that has 30 micrometer spaced drops. It is, as you could see here in the first, these are the drops right here, and this is the end picture of what's in them, showing the self-assembly of these nanoparticles. Okay, so we are here. We put the dichlorobenzene oleamine in cartridge A. This is the first cartridge. Then we put the starting material or the precursor, the gold chloride trihydrate in DMSO in the second cartridge. And we so this would be this first we print, then we print this precursor on top of it. And what happens is, this is pictorially, this is here showing you the two prints, the two different prints. You need to optimize the wetting and the surface tension of each of the inks in order to have relatively good coverage of the layers on top of each other, so that you don't end up getting in one place particles forming, and in one place nothing is forming. And also in one place the particles are so different in size, and in the other they're a bit more uniform. So having good wetting and comparable surface tension would help a lot in obtaining nice nanoparticles. And as I said, we are substrate independent as far as this is concerned. So again, you print ink A, then you print ink B on top. You do some sort of, in this particular case, post-heat treatment, about 120 degrees C for 3 hours. Take the substrate to the scanning electron microscope, and voila, you see self-assembled nanoparticles of gold on your substrate. Well, what happened is when you print the first, in this particular, the first ink and the second ink, you start the process with the heat. What happened is there is at first a partial reduction process, that is the trivalent gold ion is gaining a couple of electrons, and then we have gold chloride oleamine like this. Then there is a slower reduction process happens as time goes by, and this particular ion gains one more electron, and gold atoms start forming. And these gold atoms start nucleating and growing into eventually a nanoparticle. And there is different mechanisms at work. There is, of course, the traditional nucleation and growth, and there is, of course, afterwards a coalescence of nanoparticles with each other to make bigger. So here is the actual photo from the SEM. Of the patterns, you see these nice circles are the printed patterns, okay? We did not print continuous with the inkjet over the surface of the substrate. And the scale here is 30 micron from center to center between these prints. This is the SEM picture of one of the dots. And if you zoom closer to it, you will end up seeing very nicely packed, almost very uniform 8 plus or minus 2 nanometer nanoparticles of gold being formed or self-assembled in there. Now, we did further transmission electron microscopy to see the structure from the electron diffraction pattern here. And voila, you could see this diffraction pattern is reminiscent of the FCC structure, face center cubic structure of the gold. So we are making beautiful gold nanoparticles indeed. Well, there are certain twinnings and stuff, but that's beside the point right here. The X-ray diffraction again confirms what we saw with the electron diffraction pattern from the TM, and here are the plane locations for the gold in this particular case of our nanostructures. We did EDS, that is part of the SEM study, and you see a huge peak of silicon. This is the substrate coming from the substrate. Then the gold peak is coming from the actual self-assembled gold nanoparticles. But we see this carbon peak right here, and this is intriguing. So we went back and calculated the spacing between these particles. As you could see, there is large spacing between them. And it turned out that this is coming from the ligand that automatically connects on top on the surface of the nanoparticle. So we're not only making nanoparticle, we are also functionalizing the surface automatically during the inkjet process. So the carbon is coming from the organic ligands on top of on the surface of the nanoparticles, therefore allowing them to be stable and not coalesce into each other and merge into larger particles. So this is a stabilizer in a sense for the size. We did take the optical spectrum, and we saw that the plasma peak for this particular condensed phase of or uniform film, thin film, which is really high density compared to solution or colloidal suspension, and the plasma peak is shifted to 602 due to the fact that you have plasma-plasma interactions from one particle to the other, and that shifts a little bit the peak to the red in this case, which is at 602 nanometers. Let's see what can we do. We did this particular in 3 hours, right? Remember, we heated it up at 120 degrees C for 3 hours. Can we expedite the process in order to make it more commercially attractive? And indeed we can, down to 1 minute almost. And with the laser, we expedited it to sub-second, basically, in some cases. We don't have yet a full understanding of the mechanisms. We're collaborating with people that are working on laser treatment of materials. But in this particular case, we used a flash lamp that's used in semiconductor industry a lot, and we used that to anneal at about 1 minute time. And here we printed with different ratios between the oleamine and the gold precursor, as you can see, 1:1, 1:2, 1:3, and 1:4. And this is the power used for treating the print. And in all cases, you see nanoparticles being formed. But when we increase the ratio from 1 to 4, you go from circular peaks, circular nanoparticles, all the way up to non-circular ones, as you could see here. And in between, you will have hexagonal or multifaceted, but in a polygon type order of the nanoparticles, which confirms to a lot of chemical studies people published where the ratio of the gold starting material impact the final shape of the nanoparticle. And of course, we reversed the course here on the bottom. And as you could see, that the change of the oleamine does not impact a lot the actual shape, but rather it impacts a little bit the size of the nanoparticle. Well, can we carry this approach to make different nanoparticles, not just metals? And can we make nanoalloys? And it's beautifully shown right here. This is a zinc oxide nanoparticle made with reactive inkjet. And here, just to stay on zinc oxide, this is zinc oxide nanorod. I'm sorry, this is the gold silver, but this is the zinc oxide nanoparticles and nanorods, as you could see here, grown with the reactive inkjet. Yeah, they're not aligned straight up to the substrate yet, but that's a start at this point. So we can make not just gold or silver or whatever metal have you, we can make inorganic, non-metallic compounds at the nanoscale and different nano sizes, nano formats or nano geometries, from round to nanorods. Now, can we make nanoalloys? And this picture here for the plasmonic peaks shows beautifully that these nano particles of gold silver are indeed, as you increase the ratios from 5 to 1 of gold starting material to silver starting material, all the way down to 1 gold starting material to 5 portions of silver starting material, the plasmonic peak shifts as you go to more gold-like, depending on the addition of the gold starting material, which you should expect, and one would expect from these nanoalloys. So these particular particles are indeed nanoalloys, and they do get influenced as far as their plasmon peak is concerned by the way you prepare them with the inkjet and adjusting the ratios. That means the prints from your different cartridges. And in here, I'll just show you one picture about our early result on how to make making quantum dots of lead sulfide. This year we have this sponge, or we call it nanowall structure of zinc oxide that was grown in our labs using laser pulse deposition. And we used the active inkjet to grow lead sulfide quantum dots. As you could see here, these quantum structures on top of the nanowalls, magnified, of course, here. This is not the same magnification. And this is about 500 nanometer scale from here to here. These nanoparticles are indeed quantum dot lead sulfide. Luckily, lead sulfide quantum dots are usually and can be more than 12 nanometers. And in this case, we indeed show that you can form quantum dots growing on the wall. And we are currently investigating more and more this process, optimizing it and moving on to other quantum dots that do not include lead in their makeup. Just to show you quickly, because I know I'm running out for roll-to-roll, that is transitioning to roll-to-roll. This is the first result of our Gravure roll-to-roll process on paper, and this is the substrate, this is the print. You could see the pinkish color of the gold inks that have been printed, indicating this is really, there are nanoparticles in here. And we went to the SEM and look at the beautiful 10 nanometer nanoparticles packed, absolute, almost absolute, I shouldn't say 10 plus or minus 2 nanometers. And you can get this with the Tirkovich method. This is a very fast roll-to-roll. Basically, all you have to do is scrub these off with a certain chemical process at the end. Or if you're trying to make devices, you don't need to just use roll-to-roll to make these devices. For example, glucose sensors with certain nanoparticles, or other sensors. As you will see soon, I can't say much about this new result because it's in publication and we don't want to get in trouble with the editors. Here we demonstrated also blade coating on a roll-to-roll basis, basically. And the blade coating is simple. You put the ink and you just use the blade. And in this case, we indeed got very nice uniform nanoparticles using a roll-to-roll compatible blade coater with very nice X-ray X-ray diffraction that overlaps with and agrees with the published and the results I already showed you about gold nanoparticle X-rays. And the plasmon peak in this case is about this much for this particular size nanoparticles. Well, I hope, just to wrap up, I hope that in this difficult talk, actually, that through the connection problem, I was able to convince you that reactive inkjet is a new area, and we will make it, and others will make it penetrate different research fields, and it can be used to self-assemble nanoparticles and quantum dots, and also nano rods and discs, whatever shape you want, at any place or location of your substrate. It's not location dependent, and that's the beauty of it. You could use it as a substrate where you have already devices and circuits and you want to build a particular quantum dot structure or nanoparticle on that same substrate. And it is really, that's the aim, is for us to demonstrate that whatever you find in small scale inkjet in the lab, I'm not saying inkjet is not large scale printers. There are tons of larger scale printers that can go more than 20 kilometers per hour in inkjet these days. But what I'm saying, we want to use it in our lab as a pointer for roll-to-roll processes that can be transferred to manufacturing process. And I'd like again to thank the people here that contributed to the realization of this. I mean, of course, you see Professor Singh's name here. He worked on the early parts of using inkjet to print, passive inkjet to print macromolecules and such. And these are the universities that allowed me to do this: Ottawa, KAUST, the Optical Sciences Center. Now it's called the Wyant Optical Science, Jim Wyant Optical Sciences Center, Arizona, Oulu in Finland, and ASU in Arizona again. And thank you very much.
Thank you, Ghassan, for a very enlightening talk regarding reactive inkjet
Raja,
printing.
can you hear me?
Yes, yes. So thank you once again for a very nice talk regarding reactive inkjet printing. And I'm sure the delegates who were present have learnt a lot. At this time, I would like to open the floor for questions. They should appear in your chat box, or they should appear in the host chat box.
I can't hear you, Raja.
Hello? Hello? Can you hear me? Hello, can you hear me?
Yeah, now I can.
Okay, so there are some, I think, connectivity issues maybe at the conference end. Really apologize for that. So thank you for the very interesting talk that I think a lot of us have learned from. So I would like to request the delegates who are watching this talk to pose any questions that they might have through the Ask Question control. They will appear in the chat box for the speaker as well as possibly the host, and I would be happy to relay any questions I receive.
That would be great if you can read them, because I cannot see the chat box on this Mac or on my laptop, Mac laptop, whatever.
Okay. Okay.
I'm really sorry about this. I know I wasted some people time there, but this Mac is not cooperative when you have so many different restrictions from the university on what programs you can load and what programs you can.
Yeah, it's a tough
So
situation.
we don't use your program. We use Zoom and Teams.
I see. We use Teams and WebEx. We don't use Zoom. Zoom is actually banned in India.
Wow.
Yeah, so we're not even allowed to use Zoom, even though it's a fairly nice interface. So it looks like we don't have any questions, and it is possible that many of the delegates have already left for the evening lecture.
Yeah, that's okay. I really appreciate your patience, and thank you very much for the invitation again.
I think we need to thank you. Woke up early in the morning and put up with this difficulty here. And
No problem. My pleasure. I really appreciate you rescheduling, because that flight I ended up being pulled because of my hair now and my beard. So pulled by the immigration and asked few questions. So that delayed me further.
Very familiar with that particular part of the experience. Okay. Thank you, Ghassan. Thanks again.
Yeah, thank you. Bye-bye. Have a good day.
You too. Now we would like to note that the next lecture is at 7:30 p.m. local time, and at this time the evening lecture is on. So I would invite you all to attend the evening lecture, and we'll meet in the same hall and Hall 8 at 7:30, which is in exactly 30 minutes from now. Hello, Mohammed.
Hey, how are you?
I'm fine. How are you doing?
I'm
Big
fine.
move. Big move. Have you finished with the move finally?
Yes, effective is actually from 1st of January, but I'm
Oh,
teaching already from this semester.
okay.
So I just got back on Sunday night. So kind of like, in a goofy situation, and we had to unpack many things, and some boxes arrived. Okay, I want to do some testing. If it is fine with you, I would like to share.
Sure, please do.
So how are you? How is everything?
Well, trying to survive these strange times.
All right.
Earlier this week, one of my students got diagnosed with coronavirus, and so we
Oh,
had to shut down our lab and everything.
oh, yeah. That's very unfortunate. At the beginning, very beginning, two of my students, they were suspected, they were on quarantine, and then they were released. Fine. However, I have actually lost my like friends and families. My
Really sorry to hear that.
family, around 16 people.
Oh my goodness.
So
How are things in Bangladesh?
Bangladesh actually situation is not good because the first of all they do not maintain the statistics more accurately.
Right, you can't trust
And
the numbers.
correct. And many people they just ignore that they're having wedding parties and this and that picnic.
Right.
So uh, those are the things like
So
keep
it's a
them
very
posted.
rough situation for a lot of colleagues, actually.
Correct.
Anyhow, your move makes you one of the rare people around. Most people are these days trying to escape California, and you're moving to California.
No, actually, this is something San Francisco area. We have done very well. I was here from 16th of March until uh, 5th of October,
Yeah,
and I saw firsthand that people actually here they maintained social distance, mask, and all these kind of things
right.
because I think like the economically they're in far better shape because they can work from home, so they
Right.
didn't need essentially that kind of things. And in our case, the lockdown was defined in such that you can go in your car and you can roam around and come back, but don't get out of the car. So now, because we are in the Bay Area, people like they can drive and they can still take a breath.
Hmm.
Yeah. So whenever next time you come to the Bay Area, just let me know, okay?
Will do. Will do. So I think it's time to get started almost. So I will do the. Yeah, it's time. Okay, it gives me great pleasure to welcome Professor Mustafa Hussain, who's now just moved to UC Berkeley, as we were discussing from KAUST. A bit about his bio. He received his PhD degree from UT Austin in December 2005, and he's a jointly appointed professor in EECS at UC Berkeley and electrical engineering. From 2006 to 2008. His research is focused on heterogeneously integrated CMOS electronic systems for multidisciplinary applications, with more than $50 million in support from Boeing, Lockheed Martin, GSK Novartis, McLaren, Siemens, Aramco, SABIC, Intel, IBM, Texas Instruments, Samsung, Panasonic, TSMC, UMC, HP, and the US Department of Defense. A portion of his PhD thesis was adopted by Intel Corporation in all their microprocessors since 2008. He has served as lead author, inventor of more than 450 journal and conference papers, and US and international patents for which he has received at least 45 plus international awards, including the Edison Award in this year itself, several IEEE Outstanding Achievement Awards, and UT Austin Distinguished Young Alumni Award in 2015. Recently, his lab innovation Bluefin has received the Best Innovation Award in the world's largest consumer electronics show, CES 220. International media, including Washington Post, Wall Street Journal, CNN, Fox News, MSNBC, Time, Forbes, National Geographic, IEEE, Spectrum, etc., have highlighted research more than 500 times. Scientific American ranked his research as one of the top 3 world-changing ideas of 2014. Applied Physics Letters have selected his papers as best featured articles in 2015, 2019, and 2020. 17 of his PhD graduates are serving as faculty and researchers at MIT Media Lab, Stanford, UC Berkeley, Caltech, UCLA, UC Davis, EPMA, IIT, FUPM, KFU, KKU, Intel Corporation, TSMC, and many other places. He's a fellow of IEEE, American Physical Society, Institute of Physics, UK, for his contributions to flexible and stretchable CMOS electronic circuits and high-K metal gate planar and non-planar CMOS electronics. So without further ado, I would like to turn over the floor to Mustafa and also request the audience to pose questions using the Ask Question control on their screen, and we will go through them at the end of the talk. Thank you. Over to you, Mustafa.
Thank you so much, Madhu, for inviting me. And I know that this is particularly very difficult to organize all these events in a very unique circumstance all over the world. But I would do my best to actually to inform everyone who is participants here. Thanks to everyone to what we are doing for this specific area. I have chosen an area which is quite relevant to overall South Asia and all over the world. And we call it the augmented interfacing. What it means is that can we basically get in touch with nature in an unprecedented manner that was not possible in the past. And to do so, I have used CMOS electronics. It's particularly a physically flexible version of it, okay? So the environment around us that we know of, if you look at the coral reef or you go to a forestry, they should look like this. Unfortunately, that is not the case. If you go to the, I think 2 years back, Madhu was one of my hosts. I was in the Juhu Beach area in Mumbai, and I saw, like any other popular beach areas, that how they are being uh, environmentally polluted. And that is the case even if you go and if you're a diver, go underneath the water, you will see that that is the same situation. You go to the forestry, then you will find that many places the forests are gone. Now I live in California and I know that I've seen the wildfire, how it's ransacking everything. Okay. So now understand the implication and to mitigate those kind of adversarial effects. Nowadays, we are using high tech, and in this case, the electronics are the perfect vehicle because they have the sensors, they have the data management capability, they can communicate the data, even randomly dispersed electronic systems. And then we can have a more educated, more informed knowledge base to make an understanding and to make right policies and to take actions to basically address these environmental challenges, irrespective of which aisle you are in context of your political ideology or whatever, that everyone believes that there is something that we can do for our environment. So now, if you look very carefully, then you will see that most of these electronics are rigid and bulky because they're using traditional high performance integrated circuits, which are used as the smart devices. These are some of these invasively attached to these animals for ocean monitoring. These are some of these that you can find in Amazon, which are being used for the environmental monitoring, especially for plantation and agricultural field. Now, if you look very carefully, that all these electronics, they're basically made with this kind of the different electronic components encapsulated with multiple pins. They're mounted on this printed circuit board. It can be still flexible, but these elements are still, they're rigid and bulky. Now, in the last 7 years, we took an extraordinary step to basically make each of these components completely flexible. So from rigid to physically compliant, you can see that a version where you have the antenna, you have the batteries, you have the BLE chip, you have the microprocessor. The sensor is on the one side like a coin, the antennas and the solar harvesters are on the other side. And in between this polymeric medium, every single components for data management and power storage, they are all of these components are physically flexible, and they are made with silicon mostly. Wherever needed, that traditionally rigid and bulky monocrystalline material have been used. So now, what is the benefit if we can actually transform these kind of electronics that you are seeing in the screen at the moment? Then you will see that we basically have, this is a and Stingray, where you can see the same sensory system that was here, and then the same kind of environmental monitoring is having on the leaves of these plants in a much more intimate fashion, non-invasively. And this is the way that we are augmenting our interfacing capability with nature. So we are part of nature, but we need to actually get closer to them so we can understand and learn and can apply them in our engineering, come up with much better solutions that we have today in our world. I will start with the ocean monitoring system, where if we can measure the pressure and depth and temperature salinity, then we can understand many of these facts that's happening within our ocean environment. And the deeper we can go, the better we will know. So today's solution, which are telemetry tags, you can see that they are invasively planted on these the species. However, the accepted maximum weight of the sensor should be at 1% of the body weight, body weight, but this is actually not the case. They are heavy. Even the smallest one is 2.5 kgs. Nowadays, you can find some of the smaller one, but they come in many more of the components. They're expensive, at least $1,000 per unit, and they're invasively attached. And that basically hinders the movement of these species. So now, if we can have those, not only we understand the coral, the situation, what's happening in the ocean, we can do also monitor these the species, how do they live, how they grow up, what really causes them to be extinct. And you might remember the unfortunate event of the Malaysian Airlines many years back. I think 4 or 5 years back, it got lost and never could a trace was found. So what if we can make what I showed you, then we can accommodate the animal comfort. We can dramatically reduce the weight by 40 times. Performance and cost improvement over performance over cost improvement can be 10. So we would like to maintain the same performance, but we would like to reduce the cost by around 10 times. We need to have complete physical compliancy and the integrated data processing, logic, and storage. And nowadays we are seeing the light that we will be able to do the communication using optical communication. Okay. So now this is what we did. As you can see that these are some of these, the temperature sensor, these are resistive principle based, pressure sensor, they are capacitive principle based. These are some of the salinity sensors. So depending on its contact with the saline water, its conductivity changes, which is essentially resistive change. Only thing at that point we used is like this battery, which was the initial one, which had the solid component, but we tried to minimize it as much as possible. This is a comfortable design. This can be actually tagged to the animal non-invasively, ultra lightweight. It has multi-sensory capability, as you're seeing. It's a low-cost approach, and it was definitely packed with biodegradable material system. So now I will show you that National Geographic made an article, a feature on this technology. I'm going to show you one version. I'm not showing the other version for time's sake. So this is in Bahama, and this is exactly, these are wild sharks. They come back every time, every day at a certain time frame. These both of them, they are marine biologists, and they have befriended with them, and they are going to actually try to put the tag on them. You can see the video They are trying to actually get them in. So one of them, they have got, now they're going to actually use the dental enamel as their the glue. We used a bulky battery here. What was important for me, you can see that there's a pitting going on here so that it actually doesn't move. And then these kind of glues have applied, and this is essentially when they've been done, then it will be released and it's actually moving forward. Okay, so these are the things that have been done. Now, when we compare with the status quo, then you can see that we have documented all the different things those are available. From sensory perspective, not only we provide the same sensory mechanism like any other things, we are not less. Our the thickness is definitely much lower than most of these, and obviously it's being called the high. And then the weight also, we are less than 6 grams in air and 2.4 grams in fresh water. One of the important factors is that you can see the tag deployment life for them is essentially 730 days hours, 151 days. However, we are doing the data processing every 5 milliseconds. They are doing 1 second. So essentially, circuits and systems design, how we are planning to operate these kind of devices is going to be hugely helpful to understand and to keep the power consumption under lead. Because when there is nothing versus when there is something, we can take advantage of the fact that there will always be an opportunity for further optimization. And within this time, we can actually go with some even the lower rate and can get the information that we are looking for. Okay. So to summarize on this portion, this is eventually became the bluefin, which got the best innovation award, as Modi was suggesting, in this year's Consumer Electronics Show in Las Vegas. And we have done the low power long deployment up to 1 year and continuously functional at 1.5 kilometer to 2 kilometer depth. Nowadays, we have achieved that for more than 6 weeks. It's no more 4 weeks anymore. But yet, we are still working on many other aspects of it so that we can do instant data communication, which is underwater unless you're using sonar technology. That is very difficult. Now I will shift the gear to for the food security and smart agriculture. 1 in 8 people suffer from chronic hunger. South Asia, as one of the largest consumer at the same time largest producer of the agricultural products, and 1 in 3 children we do know faces malnutrition in developing countries. An annual net forest loss is 7 million hectares. None of this is good. We would like to see our green belts everywhere. So the question is that, is it possible to halt the deforestation while increasing the agricultural productivity? So nowadays, more and more, those people who are working on the cyber physical system, they are and using UAV, which is one of the fantastic vehicles to actually deploy and to monitor. It's the remote monitoring of the agricultural field. And then these are some of these microclimate monitor. Then again, you can see, you can find them in Amazon, including nowadays in most of the places in the back here, there are lots of these greenhouses, hobbyists. And then you can find like, the cell phone or smartphone control, the sensor system, which you can buy even today is the following day after Thanksgiving. And some of them are actually cheaper, but not that cheap. Now, how do we actually design and fabricated our butterfly? First of all, the design we chose intentionally because butterfly has larger wing span, so we can put different kinds of the sensors both on both sides of this wing span. So we use silicon substrate, and we did exactly use the CMOS technology because it's kind of my so-called comfort zone. But more importantly, they are reliable and mature technology. But more importantly, they provide unprecedented performance, the data management, data storage, data processing, data communication, energy savvy, reliability, and seemingly far more cost effective. And they come as a comprehensive solution. Their only challenge is they are not physically flexible and stretchable. That we have tried to master so that we can have completely integrated solution, which you won't see anywhere, that every single component is completely physically flexible without compromising its performance, integration density, energy savviness, reliability, or anything. So it's a nature-inspired design. It helps us to do area conservation. We have integrated temperature, humidity, and the growth sensing. We have taken always the minimalist approach by actually playing with the game that how we can minimize the data communication and the as much as possible single chip solution if possible, and then reduce the power consumption just by from the application side, lower cost. It has a lower footprint so that we can actually use the battery, which although we have now used micro lithium ion battery which are flexible, but as you know, the battery technology is a volumetric technology. The larger, the weighty, they are better, but we cannot continuously use that. And that's why we are eagerly waiting for the natural breakthrough in the battery technology where we can use flexible, stretchable, and ultra lightweight and ultra capacity the battery. So yeah, leaf texture can vary, and we can make intimate interfacing because they are soft and there will be on their the plants, and they basically do the data management and in situ power supply because sometimes we have integrated the solar cells. Bulky ICs are not intended. Solar and wind power both can be used. The question is, can every component be biodegradable? Because when they are done, when there is rainwater, when there is sprinkler water, when at some point after 2 or 4 or 6 weeks of continuous usage, we would like them to be completely dissolved within our environment without any further challenge. So you can see that how we are measuring them from the temperature sensing perspective. We have always benchmarked ourselves with the commercially available sensors, the best theirs and the modest performer one. And you can see also that how the relative humidity has been changed and how we have been able to actually monitor them using the both kind of the sensing mechanism. Plant growth monitoring, we have used a stretchable architecture. So it means that when the plants are growing, because of the stress, they will be stretched, there will be physical deformation, and just using the many of these Wheatstone ridge configuration as well as the Poisson's equation, it's very much connected. We can actually figure out that how we can electrically monitor the plant growth. These are some of these, the barley, the plants, and you can see that growth of barley plant over 2 hours and 35 minutes, how it's actually being changed because of the strain, the elongation. Some of these plants, they are very responsive when you actually water them. I can see them. I am an avid gardener and I have the many of these herbs and plants. And sometimes if you don't water them for let's say 3 days, 72 hours, you will see that the meat plants, their leaves, they get actually wrinkled up, dried up. But when you water them down, then within 30 to 40 minutes, they are lush green and they basically come back to life. Okay. So these are some of this lucky bamboo growth over the 24 hours. If you can actually change the saline water system, and it shows that substantial growth that we are looking at. We now have different technologies to actually monitor it remotely because you can have even the electromagnetic interference so that the UAV goes and can actually do the monitoring on its own. Now, UAV, those are being used. This is from the Nikon last year, where we had the keynote podium for this work, where I'm going to show actually we have now trained the UAV, so which goes somewhere and does not know exactly the terrain, but can do the color identification. So let's say you have rose plants, you have the green fields, you have the mustard plant areas, which are yellow, red, green, yellow, and then you have the lakeside, which is blue. It can go and can actually drop off its sensors, which automatically, when it sees the yellow area, mustard areas that it was looking for. So I will show you the one of these techniques. So basically, this UAV has flown, and it goes, and then whenever it sees these areas which have definite color, the difference from the areas which is the concrete areas, then it's going to go and will actually start dropping off some of its sensors. So this is the way that we are without any kind of human interfacing. These are artificial intelligence, the version 0.01, the cruise control It has the scripts, the sensors, feeds, and all different kind of things that you can see here, that it's actually trying to figure out that which color that it should choose and detect, and then it's dropping off. So now, because there are wings, so the drop off cannot be exactly on the area. So that's why we would like to actually minimize the cost. It can be dispersed in a wide area, and we have done it and then the UAV goes and can actually monitor and can gather the data back, and now we can do an whole field monitoring that was unavailable in the past. So to summarize, physically compliant electronics can be enabled to enhance our agricultural productivity as well as for the oceanic environment monitoring. The present demonstrations that we have shown the temperature, humidity, and growth monitoring. We are also now have incorporated acoustic sensors, standalone system with battery and data management. So we call this a zero fuel, the plant copters. Some of these that remember that we used to make the paper planes. So we are now accessorizing them with this kind of sensors so that they basically have the aerodynamic ability to go farther and to spread around the way that we want. So the future studies that we are doing right now are more functionalities in our sensors, biodegradation, the studying the plant biology, wide-ranging deployment, cost effectiveness, and simplified monitoring. I'd like to conclude my talk by acknowledging my past and present group members, collaborators, my grant agencies, and the industries who have been supportive to put their confidence on us. So with that, I will conclude my talk and will be happy to respond to some of the questions that will come on our way. Thank you so much.
Thank you, Mohammed, for a very inspiring talk, I should say, given the applications and the gamut of different applications that you have shown. So at this time, I would like to open the floor for questions. The questions will either appear in the chat box directly with the speaker, or with the host, or with myself, in which case we will relay those questions. Um, Again, to the delegates, please use the ask question control on your screen to pose the questions that you need to.
I'm paying attention to the chat box also, if there is anything. Okay, there is something coming up. I think Sena. Yeah, hi Muhammad. Yes, hi. How long does the sensor need to last for the plant growth applications? Can you elaborate on the specifications? So depending on what kind of plants that we have been using, these can actually be useful for about a month, because the way that we have chosen the encapsulation material, it takes time for them. If we are using the pH level within 5 to 9, then with that kind of the liquid that we expect them to be pH equals to 7, but yet then the overall dilution or the biodegradation of these can be around about a month. And definitely depends on if we are in a flooded zone, then these are unusual circumstances. So they will be biodegraded far more faster. The plant growth applications, again, one of the things is that how quickly the plants grow. Some of the plants, they take time. Sometimes they take weeks to even show just a millimeter to a few millimeter growth. And but these are mostly for like the plants which are seasonal. It means that if we are talking about the rice, the wheat, the corn, the barley, and sugar cane, as well as the garden vegetables and the other plants. These are for the plants which are essentially the bigger one, which is going to be there for 100 years or so. It's going to definitely take much longer time. Okay. Modhu, I cannot understand because something happening with your mic, I guess. Yes, now it's fine.
If there are no further questions, let us thank the speaker again for a very informative talk. And Mustafa, we hope to see you again, hope in person when things improve.
Yes,
It's a
yes,
really
yes.
great time for all of us. And as experimentalists, this entire idea of social distancing itself is a problem because you can't distance yourself from the devices you're trying to make. So,
There's no problem. So I think like that hopefully soon everything will be better for this world, and I
yeah.
look forward to seeing you very soon. Okay, so until then, stay safe, everyone, and enjoy the holiday season coming. Okay,
You too.
thank you so much. Bye.
Thank you. Bye. So the next
next speaker will join at 8:30.
actually she's already here. She joined early, but we will
Okay, so
start
then
at 8:30, which is the
we can,
scheduled time.
okay, all right. Then we can start right now.
Yeah,
So,
hi.
hi, Tina. So thanks for accepting our invitation.
Hey, no problem. Thanks for the invitation.
I understand it's rather early in Bay Area at this time, or in
It's
Southern
okay.
California, more accurately in your case. But thanks for coming in.
Yeah, we had Thanksgiving holiday yesterday,
I know
so it
it's the
was
worst time of the year in which to drag somebody out of the bed. So,
uh
and
we
today
have
being,
early night.
I know, so today being Black Friday, early morning should be spent somewhere else. At least that we several times. But
Yeah, these days Black Friday is always online anyway.
yeah.
Okay. I'm trying to share screen and it should be coming up.
So um,
Is this all right? Would you be
yes,
able to see?
clearly visible.
Okay. So, thank you everyone for being
Hold on,
here.
Tina.
Yes.
Actually, we scheduled your talk for 8:30,
Oh,
and
okay.
so I think we should probably hold to that schedule if possible. So, Khare, can we do it early if possible?
Actually, Masudan, we can do that because I just saw the statistics. 123 persons are observing the talk. So we
Okay.
can start right now. This audience you will certainly get right now.
Okay. All right. Thank you. So I will briefly
We
introduce
can
Tina.
continue because the speaker is already there. So we
Yeah.
can go ahead. That's
Okay.
good because
So
the audience are already there.
yeah. So Tina, I would apologize ahead of time if I mispronounce your name, but I am going to make a best effort. Dr. Sena Nig is an associate professor in the Department of Electrical and Computer Engineering at the University of California, San Diego. Her research focuses on devices and fabrication methods of flexible printed electronics. She received a PhD in physical chemistry under the supervision of Professor John Marone at Cornell. Subsequently, she worked at Palo Alto Research Center before joining UCSD in 2015. Her work on printed systems has received the 2012 Innovation Award from FlexTech Alliance, was named runner-up for the Wall Street Journal Technology Innovation Award and received second place in the 2017 Bell Lab Prize, and is named a Hartle Investigator in 2017. She's on the editorial board of the Journal for Flexible Printed Electronics and ACS Applied Electronic Materials. Over to you, Tina.
Thank you so much for the introduction. Yeah, so nice to be here. Thank you for the invitation. And for today's talk, I want to focus on two areas on organic infrared sensors and supercapacitor based on narrow bandgap polymers. So for the use of infrared detector, there are quite a few desirable features. For example, right now for autonomous navigation and a lot of spectroscopy, we want to go beyond visible wavelength. One example here is if we have infrared in the shortwave IR, region, the penetration depth is much deeper than in visible, for example, in the fog here. And so you have much better contrast. So for a lot of material scientists here, you might already know silicon can only go up to 1.1 micron. And so we cannot use our conventional camera for infrared detection. And for the rest of the materials, for example, InGaAs, they are really expensive to heterogeneously integrate onto silicon CMOS. And that's why you don't see much infrared cameras on your cell phone, even though it's highly desired. And then for the past 2 decades almost, we have been looking for alternative materials such as using quantum dots. But still, the performance for that material is not quite up to the conventional compound, 3-5 compound semiconductor. So there is still room to look for alternative large area processable material. And in organics, which I'm really working on this area. The prior works mostly in near infrared for solar cells, but there is room to tune our molecular structure to cover this region. And so I'll show some of the work extending the spectrum for organic material for shortwave infrared applications. So one of the key points is actually the materials, and I collaborate with Professor Jason Asolay at Mississippi to get some wide, narrow bandgap absorption polymers. So to do that, he tuned the donor acceptor polymer moieties. For example, substituting different acceptors. He has shown polymer going even into mid-wave infrared. But then the challenge is for narrow bandgap material, we see decreasing performance. So an example is for now, visible wavelength or in organics almost as good as silicon. Actually, there's a paper in Science that just say it's exceeding the silicon performance. But then as we go to narrow bandgap, we have the whole field have seen that the performance is much more degraded. And so in this class of material, you can see we extended the absorption from silicon edge of 1.1 all the way out to cover the whole 3-5 spectrum out to 1.8 micron. But the problem is we can absorb but do not transduce this into a photocurrent, and hence the EQE is very low. So this talk, I will show some of the technique that we use to enhance the EQE and subsequently the signal to noise ratio. And in the work here, we use the conventional bulk heterojunction and to point out the specific difference between visible wavelength and infrared. In bulk heterojunction, we purposely design a type 2 heterojunction with an offset between donor and acceptor. And this offset actually helps your exciton that has been absorbed to split and dissociate so that they become free carrier that can be collected. But when we look at the band diagram, as we go from this is what we call charge transfer state. As we go from visible with a larger charge transfer state to infrared, by definition, we have to go for narrower band gap to absorb long wavelength light. This band gap shrinks, and so the recombination probability become much higher, and this is one of the bottleneck why infrared detector has been less efficient. I won't go into the detailed optophysics here, but this is the general concept of why dissociation is very difficult. And so once we identify the bottleneck step, we look into how do you increase the dissociation rate. And one term you can look at is the binding energy, exciton binding energy. And for that, we can either delocalize the exciton over a longer length A, or we can also tune that internal knob or we can also tune the external environment with the dielectric constant to decrease the binding energy. And with that, we use this external knob, added some high K dielectric material such as this camphoric acid in, which can use the polarizability to stabilize the charge to help it to dissociate. We improve the efficiency as shown here without versus with this camphoric acid. So we raised the EQE to 26% even without bias, which is at that in year 2018, that was state of the art. And then now we improve it further, and the field has been moving into the infrared regime. And another technique to improve the EQE is actually by using charge multiplication. And in organics, we know charge trapping, and actually you can leverage it in order to inject more photocurrent. So here, the schematic shows when we shine light, because we purposely designed two blocking layer, this is electron transport only, but not whole collection. So then the holes are trapped inside this material, and we use that to narrow our injection barrier compared to without light. And so that allows us to inject more electrons and creates this photomultiplication effect where our EQE can reach above 100%. So this is typical to other photomultiplication process, even in the visible light range. And the caveat is that we can achieve over 100% EQE, but you will require longer multiplication time. So the gain in current is offset by the speed at which you can operate this device. So another method shown here is similarly using transistor structure, we can also inject charge to improve our photocurrent. So naively, in the beginning, we were just putting that bulk heterojunction onto the transistor device structure, but we don't see much photocurrent actually. And then once we just draw it out, we realize, yeah, the transport between source and drain is pretty bad, as you can see all the grain boundary here. So then we use a transport layer for the channel, and effectively this is a backgating effect. When light shine, the exciton split, holes are trapped, electron get transported and injected and cycled through. And again, because of that injection phenomenon, we can get high EQE above 100%. Again, with the trade-off in operation speed. So these are capable to operate in 50 hertz, but higher speed would be beyond that video rate would be much lower EQE. And so besides, I have been mentioning EQE, but in a sensor, the important metrics is more than that. It's actually signal to noise. So as shown here, the detectivity D star. So to increase detectivity, EQE is important, but we also need to lower the dark current noise. And so with narrower bandgap polymer, just like it's harder to dissociate, we actually have more thermal generation as well. So the denominator could get pretty big. And in this work, we try to reduce noise by looking at using different acceptors. So the field is generally using PCBM, buckyball, fullerene, but recently, non-fullerene acceptor is very under investigation and popular. So we also look into variation of those small molecule from ITICM, ITICF, shown in green and blue here. So ITICM have a wider, slightly higher HOMO and LUMO, and so that's why its energy is over here. And even in the normalized spectrum, absorption spectrum, you can see there is a trend in that the non-fullerene actually have a broad tail. The or the slope, band tail slope, is much shallower than the polymer itself or the small molecule. So noticing this, we also study and measured the noise spectrum. We can see that with fullerene, the noise is highest, while ITICM is the lowest because it's the widest band gap with the sharp band tail slope. We use capacitance frequency measurement to extract the actual density of state. I won't go into detail, but if you're interested, we can refer to here. And we see that the band tail really, just like in absorption, we could follow the dark currents based on those band tail characteristics we measured. And so absorption is actually a good screening method to see what will give us a lower dark currents device. And then if we use the measure noise and our measure EQE, we ended up seeing that ITICM as an acceptor will give us the best detectivity. We also actually study quite a few other polymer in addition to that one I showed in the earlier slide. And throughout the whole series, we actually see that the shunt resistance across the diode would be higher, which is good because higher shunt resistance will be lower dark current for the non-fullerene series. And so with this, we can actually decide and predict that if we have a sharp band tail for our acceptor, it would be a good thing for decreasing dark currents so that we can improve signal to noise ratio. So for the material, it's actually quite useful to use for imager and scale to larger area size. And the typical way to scale it up to become a imager is to put it on pixelated backplane, which is still the default. But we also want to use another method to visualize the infrared light right away. So we use this conversion process that's actually published by other people, but haven't been using as much for the long wavelength light in organic. So the way this works is actually electronic, not the optical Stokes shift, but electronic in operation principle. So what happened is in the dark, they this back-to-back diode and OLED light emission device actually have a barrier, electron blocking barrier. So we bias it. This is under reverse bias. This is forward bias. But without light, the charge is blocked from recombination. And so we actually don't have any current running through. So the device will be dark. But when there is infrared light shining in the photodiode, we create an electron hole pair. The holes can be transported to recombine in the OLED to emit visible light, so we can up-convert the invisible infrared light to visible images. And this rely on local emission, that the charge, the exciton does not diffuse laterally too much, but rather recreates the same light pattern, the same infrared light pattern in visible wavelength form. And so we did this. We use our infrared material, combine it with green LED to up-convert this into a visible image. And you can see with dark, with no infrared impinging on the sensor, we wouldn't have much luminance from the backplane. But when we impinge the light pattern, we could see luminance from the visible OLED. And actually, the signal to noise ratio here is interesting in the sense that the up conversion imager show a little bit higher here because we run it at higher bias. So with the higher bias, we actually can achieve comparable signal to noise as a single photodiode. The efficiency, usually people quantify it as well using photon to photon conversion efficiency. Right now, the device is a bit low at 0.2%, but there is room for improvement and we are working on that. And this is another image trying to image the blood vessel here. And this is the nail. Actually, you can actually see the nail bed here with the cuticle, and we can see the blood flow through the imager. And here, this is the vein, and we are trying to improve this sensor. So with that, this is the first part of the talk. We use narrow bandgap polymer for infrared detection. And in addition to infrared visualization, I actually want to point out you can use it for spectroscopy. For example, fatty tissue at 1200 nanometer actually has a significantly different absorption than lean muscle. So in a way, you can detect fatty tissue and distinguish it using this wavelength. Anyway, so with infrared sensor, we actually characterize the polymer quite a bit and realize that it has application can be used in supercapacitor as well due to a special property of this polymer with the extensive delocalization property that makes it quite stable and unique. So it's in a way it's a happy accident that we were characterizing it and realized it has another use. So to go into the next topic, I just want to give the introduction, the motivation for why we want to use capacitor, supercapacitor. As we use a lot of Internet of Things device right now, all of them need some energy source, and the default is to source power with battery. But some of the low energy circuit can potentially be powered by energy harvesting devices from solar cell to RF energy harvesting. But those intermittent sources need to store the energy harvested in a storage device. We can store it in battery, but battery has a low cycle life. Usually battery has a 1000 cycle life. And so if you cycle it every day, it would degrade by 3 years. And then you need to replace that device pretty quickly. And so to avoid those replacement issue that's involve manual labor, we want to use supercapacitor that allow us to have a longer cycle lifetime. But as seen here, the power density of supercapacitor is good, but the energy density is lower and actually should remain below battery. But for those low power application, low energy density application, this should be advantageous with a longer cycle life with sufficient energy density. So we do still want to improve the energy density, and recall in our physics class, energy density proportional to capacitance and voltage square. So increasing our operation voltage window would be very advantageous. You can quadruple your energy density by doubling the voltage. But a lot of times we are limited to water electrolyte because a lot of the polymers are not stable when we go use more negative potential window, wider potential window. But in the narrow bandgap polymer I just showed you, we accidentally see that it has a wide potential window. And so we pursue this and see whether this polymer can be beneficial for increasing the energy density. So for using active components in supercapacitor, it's not new. Other people have used a radical polymer with the redox group on the end of the chain to make radical battery with high redox potential. For our conjugated polymer, the property is a slightly different in that we have extensive delocalization along the whole chain. And you can see in our current voltage CV plot, cyclic voltammetry plot, we do have redox peaks at a quite negative potential compared to regular polythiophene, aniline, etc. And this extensive delocalization actually helps a lot to stabilize the material. When we add or subtract, when we subtract or add the electron in, the whole the electrons delocalize along the whole backbone, and so it's less reactive and makes it much more stable compared to other materials. And so we use this as the active redox polymer in our supercapacitor in a pouch cell here, and we run the potential up to 3 volts. Typical polymer supercap has been run up to 1 volt for the water reaction window. And more interestingly is that this material really have good Coulombic efficiency and capacitance retention. Up to 4,000 cycle, we retain more than 80% of the retention. And this is interesting because prior N-type polymer, such as this one, such as other fullerene polymerization, has died pretty much by 1,000 cycles. So it gives you higher energy density, but it doesn't retain the good property of long cycle life that's needed for supercapacitor. And so we compare this polymer to the other N-type polymer here. It does have higher energy density. And the more excellent point is actually the long retention time. As we see other N-type polymer die pretty much by 2,000 cycle, but we have been cycling it to 5,000 and still retain up to 80% of the capacitance. And we actually use this, we are developing to use the polymer. And another issue in supercapacitor application and integration is the self-discharge and leakage issue. What that means is battery, you usually charge it and let it sit, it's okay. But for supercapacitor, for example, the potential in open circuit actually would drop by half over this 16 hours. So you fill it up, but it leaks out the charge pretty quickly. Another flip side of this is you have leakage currents, for example, measure up to about 1 microamp here, 0.1 microamp. And so as you charge it, it could be leaking out 0.1 microamp of your charging current. And in a lot of the low energy charging source, in the energy harvesting source, some of the charging current could be pretty low. So if we leak out more currents than we input, then you won't be storing the charge. And so, for example, in our RF integration work, the charging current is only 0.4 microamp. And so we need to make sure our supercap will have lower leakage than that in order to fill it up. Otherwise, you're filling up a leaky sieve and the charge won't stay. So self-discharge is not talked about as much, but it's a very important thing to overcome for any practical application. So there has been studies on how to suppress this, and the mechanisms for graphite-based, carbon-based, activated carbon-based material is actually based on redistribution. And initially, when we charge the pores, the ion comes in to balance charge. But once you settle it down, this is a higher energy than this portion, right? So it redistributes and the voltage drops from the surface to the bulk, and that's where some of the voltage drop occur. The other knob to turn is actually to decrease the impurity. So since we do Faradaic reaction, redox reaction, if we have any redox impurity in the electrolyte, it could be taking away the stored charge and decrease our stored charge on the electroactive material. And we can examine this behavior just by current voltage plot. Different mechanism will have different dependence on time. And we notice that our supercapacitor tend to follow the redox Faradaic problem. And so we devise a way to reduce the impurity, not just by purifying the active material, but we can put a separator with impurity retention capability so that we can reduce those self-discharge redox reaction. So we look into the wastewater management field actually, and notice that there is a cation exchange resin, pyrrolite, that we can coat onto our seal guard separator. And this separator with the resin will look at the property and whether it can reduce the retention, the self-discharge mechanism. Let me move to the next slide. Okay. And so we have a supercapacitor with a separator that's commercial and with the one that's modified with this cation exchange resin. And nicely, we see that the self-discharge curve did reduce. We retain more potential over 10 hours. And the mechanism really is that in the ion exchange resin, it has this sulfonate bond that can bind to the impurity in our electrolyte, and so it does not migrate and diffuse through the separator as easily as compared to the commercial separator. And so we take out some of this impurity away from our electrode to retain the charge much better. And this cation resin is operable in aqueous and organic electrolyte, and we tested it over the whole pH range, and all this condition it's compatible with this resin. And so for the diffusion mechanism, we also study this using temperature dependence. And so with the resin, we can feed to the curve at different temperature and find the activation energy. And the model shown here, this is the diffusion control, this is activation control, and most of the time the M term, the diffusion control term, is dominant. And when we vary temperature, we see that with the resin, the activation energy for diffusion is much higher. So that means it retains the impurity better. And so diffusion is slower and suppress our self-discharge inside this device. And lastly, we integrated this with energy harvesting board. So the super cap is here, and we can use RF energy to charge and discharge the board. In this board, it's basically lighting up the LED. Not doing much right now, but at least we can charge and fill up the super cap, discharge it to light up the flashing LED, charge, discharge multiple cycles, and see that it's integrated and working properly. And then again, comparing with the commercial and with a modified separator, we have a different behaviors. And in the commercial separator, we actually cannot charge it up fully, even over hours. We cannot get the voltage up to the 1 volt operation for triggering the circuit. Because of that self-discharge and leakage current, as we charge it, it leaks too much current, and so we cannot reach the final potential. But with the added resin, we are able to reach our final potential, discharge all the energy out to power up the circuit. So with that, I want to summarize this work. That the semiconductor is capable of both optoelectronic application and energy storage application. For the infrared detector, we've seen that actually lower band tail slope would reduce detector noise, and we are working on the upconversion imager to visualize that infrared to visible wavelength application. For the redox active polymer, we have seen that the narrow bandgap material can be very stable N-type polymer due to the extensive delocalization phenomenon, and we can also suppress self-discharge to integrate it with an energy harvesting circuit by using the ion exchange resin separator. And finally, I want to acknowledge my collaborator and my students and the funding agencies. And thank you so much for your invitation to be here. And thanks. I'm open for questions.
Thanks, Tina. So it was a very interesting talk. Usually, you're focused on two different areas of polymers are typically not thought of being useful. The most of the work in the energy storage regime has been focused towards lithium-based materials, and so that was really informative. I would like to open up the floor for questions at this time. I would request all the delegates to use the Ask Question control on your screen to pose the questions that you may have. The questions will either appear in the chat box directly with the speaker or with me or the host, and we will relay them in that case.
This is late for you. It's
Okay, so still there are 112 delegates are watching your talk. So, yeah. So,
We'll take our late
time.
so that's not a problem.
Can I ask you a question?
Yes, please.
Okay, so actually in one of the slides you showed the noise measurement of a device.
Oh, sorry. Can you repeat that?
In one of the slides you showed the noise measurement of the device.
Mm-hmm.
Noise measurement. So what information you can get from that noise measurement?
So what information I can get from the noise measurement?
Yes.
Oh, okay. Yeah, so the noise measurement, it's basically the spectrum. You plug in the device in the dark and measure what current density output versus frequency. So what information we want to get, if we run it at bias, then it would be giving you the short noise. If we run it at zero bias, which was what the curve was, then it would be the thermal generation phenomenon across the band gap. So a lot of times, actually, this is a good question because in the thin film detector field, a lot of the noise are just using the short noise assumption, and so now our field is realizing that that's a lot of times it's underestimation. So actually, we need to properly measure it. And so whether it's in the thermal generation regime or short noise regime, we can clearly see that in the measurement rather than just using the assumption.
but I saw it's more like a 1 over F noise in the lower frequency region.
Right. There's both. There's let me try to share screen again. Let me see. Um, oh, okay. So yeah, there is 1 over F noise. Your eyes are sharp. So in the 100 hertz and below, there is 1 over F noise. And because this is at zero bias, most of these are thermal generation noise. So if I measure it at bias, it's actually higher. And in our device, it's actually at bias actually ended up having less signal to noise ratio because of the higher noise problem.
Okay. Okay, thank you.
I have a question, Tina. So typically for upconversion, a lot of the literature has looked at lanthanide-based upconversion materials, especially NYF4 and its derivatives. What are the advantages that you were looking for when you looked at organic upconversion materials, besides the fact that they have obviously lower cost?
Yeah, so for this upconversion mechanism, it's a little bit different from the lanthanide Stokes, anti-Stokes optical upconversion. So there we actually do absorb two of those energy level, like, and then require that to convert it to the higher visible wavelength. But
It's an
here,
it's an anti-Stokes process there. So yes.
right, yeah. So this actually does not use the Stokes process. It's really just a charge transfer process. So it's a bit different in that sense, and the upconversion efficiency is different in that sense. It really is just the whole getting transported into the OLED. So it's a back-to-back diode instead of that optical conversion. And so if we try to compare that, it's the upconversion can be localized if you use organic material because the lateral mobility is slower. So you could have a more reproduced image compared to quantum dot, where the transport can be faster. But there's also a trade-off, right? If your operation speed is slower, that means at least you for human eye is okay. But if you're gonna go for a camera to capture this image, then that's
A lot of
become
energy. Yes,
right. Yeah.
So do we have any questions from the delegates at this time? So if not, let us once again thank
Yeah.
Tina for a very interesting talk so early in the morning on Black Friday, which is perhaps the worst morning to actually wake somebody on.
No.
So thanks once again, Tina, and we hope to someday see you here at IIT Delhi when things get a lot better and we are finally able to travel.
Yeah, we
Originally, it
hope
was to get you here.
the world will be safer next year, and
Right.
I hope to see you. Thank you so much. Yeah.
Thank you.
Bye.
Bye. This incidentally was also the last talk in the symposium, and I would like to thank the attendees, delegates, and who have patiently sat with us with some of the technical difficulties earlier in the evening, and also posed really good questions to our presenters. So thank you, and hopefully at the next edition of ICEE, if we have the symposium again, we would be able to meet in person, and conditions will be a lot better then. So thank you, everyone, and we'll sign off from Delhi at this point.